Hi, I'm Leo Porter.
I'm Christine Alvarado.
And I'm Mia Minnis. Welcome to this third course in our intermediate Java programming and data structures specialization. Welcome back to those of you who have been with us from the beginning, and also welcome to those of you just joining us. We hope you're excited to learn some data structures and algorithms in the context of a really interesting project.
If you're with us for those first two courses, you've already learned a number of essential skills for a software engineer. You already know how to organize your code into classes, how to analyze and algorithms for its efficiency, and how to both use and implement a wide variety of data structures. In this course, we're going to be focusing on advanced data structures. Specifically, actually, just one data structure, graphs.
Wait, just one data structure? That's it?
Yeah, it actually turns out that graphs are such a complex topic that they kind of deserve a course in themselves. I mean, graphs are one of the most fundamental data structures in all computer science, and the algorithms associated with them are used in a variety of fields, not just computer science. In fact, graphs are such a big topic that they're actually a field in themselves, and a number of people have been successful in their careers just focusing on graphs.
Oh, I guess it's probably good that we're just focusing on graphs then, especially because our last two courses got a little large. So it also makes sense then that your project is going to focus on graphs. You're going to be building a full-scale mapping application with many of the features you expect from a product like Google Maps, like route planning. And in fact, you're going to get to use real-world street data that you get to choose. You're going to be building this application and then putting it into a front end that we provide that actually uses the Google Maps API. So in a sense, you really will be building your very own Google Maps.
And in the last week of the course, we'll be thinking about some of the algorithms that are needed for graphs and maps, and we'll actually come across some fundamental problems for which there's no known good algorithms. And when we say no known good algorithms, we mean no one in the world has found a good algorithm for solving some of these problems. So if you go ahead and find some of these solutions, you'd end up being pretty rich and famous.
Yeah, I know when I first learned about these problems, I was sure that I'd be the one to find that solution that everyone else had missed.
Yeah, it's so tantalizing. We've all looked for it. The thing is, though, that we still need to solve these problems. So even though there's no known good, efficient algorithms for solving them, we still need to find some way around that. So in this course, we'll be talking about heuristics and optimizations that may not give us the best solution, but still run pretty fast and give us some sort of an answer. So we'll talk about these problem solutions in this course, and we'll also come up with a way of rephrasing some problems and thinking about different ways of modeling the graph so that sometimes something that looked completely intractable becomes solvable. And we'll think about a particular example in bioinformatics that was done right here on campus at UC San Diego.
So thinking back to the logistics of this course, a number of your favorite features from our previous courses are returning. First, you've already heard about the project, and it's again going to be project-based. We're also going to allow you still to find your own path through the course, finding the right mix then of both challenge and support so that you can succeed. We're also going to still have UC San Diego learners talking about the concepts, and we're also going to have Google engineers talking about why those concepts matter on the job.
Ultimately, the skills you learn in this course, as well as the skills you learn in our prior two courses, are going to prepare you to succeed in a number of software engineering roles. Looking ahead to our next course, we'll give you more skills not only to succeed on the job, but also to succeed in the interview process. But that's getting ahead of ourselves. This course is all about graphs. So let's get started with those. Hi again, I'm Christine Alvarado, and in this video, I'm going to give you some information that will help you choose your own path through this course. So when I'm not teaching, what I like to do is I like to build programs and curriculum that help bring in a diverse set of learners to study and work in the field of computer science. And one thing I've learned about reaching a diverse audience is that you need diverse courses with diverse support structures. So we've engineered this diversity into our course and into the whole specialization. We know that you're coming to us with lots of different motivations, backgrounds, experience levels. So one size fits all is not going to work for this course. And that's okay. That's actually great. We love that you're coming from all these different backgrounds. And what we want is for each of you to feel challenged, because otherwise what's the point? But also never to feel overwhelmed. We want it to be the case that when you feel like you're starting to get overwhelmed, you can always have some more support to help you with your learning. What we've designed is a course where we have different video styles, different video series to help meet that goal. So you're not going to want to take this course by just sitting down and watching the videos one after another. What you're going to want to do is pick and choose a path through the videos that's right for you. And to help you do that, I'm going to tell you about our different video series. But first I want to say that at the end of the day, it's all about what you can do. Mia described this really cool project that you're going to be doing throughout this course, and that's really what we want you to be able to do. So what we care most about are these end-of-module assessments, which are a lot of the time going to have you building a piece of that project. So if you're feeling really advanced and really good about the material, always feel free to race ahead and just start working on that project or do the end-of-module assessment. But if you want a little instruction, which most of you will, you'll want to watch some of the videos. So the first video series that I'm going to tell you about is our core content series. So these are the videos that we expect everybody to watch. They're mostly lecture style, and they're going to introduce you to the core concepts and skills that you're going to need to do the end-of-module assessments. Once you've watched those videos, we're going to probe your knowledge a bit more with our Concept Challenge series. Again, we encourage most learners to watch these videos, and what they're going to do is they're going to ask you to think about the material you just learned in a new way. And Leo's going to tell you more about these concept challenges in just a minute. The next series that we have for you are additional support videos. Now, we don't expect everybody to watch these videos. These videos are designed for if after watching the core content and doing those concept challenges, you don't quite feel ready to tackle the end-of-module assessments, you might want to watch these additional support videos. The last two video series that we have, we're really excited about. These are series that aren't designed to deliver content so much as to put the content that you're learning in context. So the first of these series is called In the Real World. And we've got a team of real-life Google engineers talking about why what you're learning is important in their work at Google and in general in the software industry. So that'll be a really good opportunity for you to learn not only why what you're learning is important, but how it's important to these individual engineers. And then the last series that we have for you is called When I Struggled. And what you're going to see in this series is a number of UC San Diego learners, as well as us, talking about our own experience learning the material that you're going to be learning in this course. We'll talk about a time when we struggled with the material that we're presenting. And then we'll talk about how we overcame these struggles. So we hope you'll watch both of those series and that it'll enrich your experience in this course. So again, to summarize, the standard path we imagine a learner taking through this course is that you would watch this introduction with the Google engineers talking about why these concepts are important in the real world. You would go through and watch the core concept videos and perform these concept challenges, maybe watching some videos about when some learners struggled with these concepts along the way, and then perform the module level assessment. And you would repeat that for each module. But if you're feeling more advanced, you might just want to race right through those core concept videos and get to that end of module assessment faster and get developing on those projects. And we encourage you to do that if you're feeling comfortable. And again, if you feel like you need a little more support, you've got those support videos available to you. So anytime you feel like you don't quite understand what's going on, you need a little more help, go ahead and pull out those support videos. And we hope that you'll find the support that you need. So choose the path that's right for you, challenge yourself, and have fun.
Hi again, I'm Leo Porter. I'm a computer science professor here at UC San Diego. One of my areas of research is computer science education. What we like to do in that area of research is look at the best practices for student learning in the classroom. One of the best practices we know about in computer science is peer instruction. With peer instruction, students get to tackle hard problems, discuss it with their peers, and then participate in a large class-wide discussion with the professor. We do this in a number of the courses here at UC San Diego, and we'd like to bring this to you. And we're going to do this through a series of videos known as the Concept Challenges. So let me walk through an example here. So here we have you watching a video. Now let's assume this is from a previous class in Java that you've taken before, where you learned first about for loops. So you watch the video on for loops, and then you get done with the video, and the question becomes, well, did you learn it? I mean, there's certainly areas of the video that you probably understood well, but there may be some areas that you didn't understand as well. So the best way to find out whether or not you really understood the material is to solve problems. So we're going to ask you questions to help elucidate what areas you're strongest in and which areas you're not. So a question might look something like this. So you've just watched a video again on for loops, and here's an example for loop. And the question here is asking how many times Does I less than 10 execute? Now, the reason we'd ask a question like this is because we expect a number of folks will get this wrong. In fact, we want you to get a number of these questions wrong because that means it's an opportunity for learning. What we expected is a lot of novice learners would answer B here. They would say that the loop executes 10 times, so I less than 10 will execute 10 times. But the condition I less than 10 actually executes 11 times. And we'll talk more about that as we go forward. So after you solve the problem on your own, after you've tackled the problem yourself, what you're going to then see, or what we hope you can do, is work with other learners around you. So if you have anyone else in your neighborhood or friends who've taken the same course, this is a great time to get together and discuss the question. And by discussing it with your friends, you're going to find out one of you might say, well, wait a second, does it execute that last time? And then you realize, oh shoot, yeah, it does actually execute 11 times. But if you don't have some friends around you, what we're going to give you is also a series of videos where you're seeing UC San Diego learners discussing the question. And there you'll hear them say things like, well, wait a second, it's really easy to forget that last check. Oh yeah, so the answer must have been 11. And then after you hear the UC San Diego learners discussing it, you're going to hear one of our explanations. So the full course of one of these questions is going to look something like this. You're going to pause, try to solve the problem yourself. You're going to discuss the question with other learners around you if you can. You're then going to watch a video of the UC San Diego learners discussing it. And then you're going to confirm your understanding by listening to our explanation. By solving these kind of hard problems, you're going to understand your material much better. You're also going to identify areas that you might need improvement. And that's where more support videos and the forums come in.
So in this video, we're going to demo the prototype of the project that Christine was talking about. And this project really has two phases. So in the first phase, we're going to think about the different transportation networks that we have when we compare driving around a city on roads in a car, as opposed to flying around the world, hopping around from one flight to another. And what we'll do is we'll translate these different transportation networks to this data structure of graphs and look at the underlying graph structure and see how it relates to these real-world applications using real data. And then the second phase of the project will focus on the road data and the intersections and think about enriching the data structure that we've implemented in Java so that we can really start implementing some algorithms that lead to the functionality that you'll be building for the Google Maps-like application that you'll do. So what we're going to do now is switch to the code and take a look at the prototype that you will be building. So let's jump into this Google Maps application. And what we're doing here is using a front end to see the familiar presentation of Google Maps, but really leave the algorithmic and data structures questions at the heart of this course to you to implement in Java. And so when we open up the front-end application that we've given to you as a prototype, and thank you to the Google Maps API and our development team here for this course for creating this and allowing us to use this functionality, what we've got here is the same features and user experience that you might expect from Google Maps. And what we'll do now is take some real-world intersection data, we'll stick to close to campus here near UC San Diego, and look at the intersections around here and try to figure out how to plan routes around this region. Now in this project you'll be able to fetch data and look at the intersections around your hometown or any part of the world that you're interested in, and we'll guide you through that process in a little bit. But in order to see the functionality, what we'd like to see here is that we can pick any of these intersections as our start position for a route that perhaps we're planning to take, and pick any other intersection as our goal. And now we can ask the algorithms that we'll discuss in this class to give us a route from the start to the goal, and there it is! Isn't that amazing? Now, not only do we have a route that goes along the roads, follows the intersections to go from the start to the goal, we can actually ask how this algorithm came up with this route. And so we have a visualization available to you for thinking about the nodes in the graph, the underlying graph structure that have to be explored in order to find a path from the start to the goal. Now this visualization isn't usually something that we would expose to a user of a route planning application, but it's very useful for us as a developer when we're thinking about the performance of the algorithms that we use for route planning to try to compare the features of different algorithms in terms of how long they take and perhaps how far off course they explore before finding the correct path. Now, speaking of comparing algorithms, let's look at one other algorithm that we'll be talking about in this class, and we'll see that it also finds the route from the start to the goal destination. But when we visualize the region of the graph that it explores in finding this route, we notice that it explores nodes a little bit differently and in a different order from that first algorithm, the breadth first search algorithm that we saw in the first time that we ran this example. And so throughout this course, you'll be thinking about how these algorithms compare and what their relative merits are when we might want to use one rather than the other. And what we'll do now is move to the other phase of the course that I mentioned at the very beginning of this video. Not only will this course help you think about transportation networks with real-world road data and thinking about route planning in a city, we also want to think about other transportation networks and other ways in which we might capture their properties in terms of graphs and graph data structures. So in this second visualization that we have available for you, what we're going to do is read in the intersection data that we had before in that Google Maps-like application. But now we're going to think of these intersections as a graph, a collection of nodes with edges between them. And what we'd like to do is think of the abstract structure of this graph. So members of the Google team have helped us build this graph viewer, and we're very grateful to them for doing so. And when we read in a data file that has this representation of a graph, what we can see is the number of nodes, edges in the graph, and also the degree distribution. Now, if you don't know what words like degree and edges means just yet, that's okay. That means you're in the right place. This is the course where you will learn all about it. But what we're going to be doing is connecting the real live data of streets, of flights, of airlines, and these abstract mathematical notions of graphs to understand how the two can inform one another. And so just to see that connection once more, let's pick a node and view it on Google Maps. And throughout this course, we'll be going back and forth between the applications and the abstract theory and seeing the power of combining the two. And so let's get started.
This week is all about a fundamental data structure called a graph. Most of this course is about a graph, but in this week you'll learn what a graph is, its fundamentals, and what it can be used to represent.
This week's project is all about this new data structure called a graph. This week you'll learn about graphs from Mia, but I want to give you a quick overview of what you'll do in your programming assignment this week. So here's an example of a graph, and Mia again will introduce this in much more detail, but basically what a graph is, it's a way of representing entities in the world, those are the circles that you see here, and the relationships between them, those are the arrows. So here's a toy example. This is an example you'll get to work with as part of the programming assignment. And here's another. Now in general, the graphs we'll be working with have many more circles and many more arrows in them, but these are just some toy examples that you can use to debug your program. What you're going to be doing is you'll be implementing two representations of this graph structure in Java code. That will involve writing code for two different classes that we provide you with as starter code. Next, you'll be calculating some properties of these graph structures. So you'll calculate something called the degree sequence of the graph. Again, Mia will explain much more what the degree sequence is, but just to give you some examples here on the two examples that I provided, the degree sequence of this top graph is 4, 4, 2, 0, while the degree sequence of the bottom graph is 4, 3, 3. Once you get through this week's videos, you'll understand why that's the case. Then the next thing that you'll be doing with these graph structures is you'll be taking a node or a labeled circle in the graph and determining how far you can get from that node in 2 hops. So for any given labeled circle in the graph, where do you end up if you take 2 arrows away from that node? So for example, for that top graph, if we start at node 0, in 2 hops we can get back to node 0, or we can get to node labeled 3, and that's it. For the bottom graph, if we start at node 2, then the only place we can get in 2 hops is back to node 2. That's it. So again, you'll be writing the code to do both of those calculations. Once you've got the code to do both of those calculations, you can start to explore some real-world data, and we provide some data sets for you. So for example, if you look at the degree sequence for some data that represents some streets in La Jolla, near where we are, here at UCSD, you can see that it looks very different from the degree sequence for some data that represents United Airlines routes. You can see that in the street data, the degree sequences are very small and somewhat uniform, while in the United Airlines routes, they're very large at first, but then they drop off very quickly. So what you'll see is that this degree sequence is giving us some measure of the structure of the graph, and these structures are going to make sense once you learn what these are and think about what the data represents. So we hope you'll have fun this week working with and exploring some real-world data, as well as getting warmed up with the graph structures that you'll use throughout this class. But right now, let's get started learning about graphs.
So this whole course is going to focus on a new data structure called graphs. And what we're going to do in this video is introduce the idea of graphs and why we even need such a data structure. So by the end of this video, you'll be able to explain why this abstract data type is useful and compare this graph abstract data type with the other ones that you're probably familiar with. So let's think back to the data structures and the abstract data types that you've worked with already. We may have collections of objects that really don't have links between them and don't have a lot of structure at all. And so we might organize these objects into a set, which is basically just a collection of these things. But often when we're organizing our objects, we like to have them in some sort of sequential order. And so arrays and linked lists let us organize the objects that we're talking about in a line, one after the other. And so we could do things like traverse that list, iterate over it, search by index, for example, and pick out elements in that ordered array or ordered list of objects. But in the previous course, we had applications where there was a hierarchy amongst the objects that we were organizing. So you can think back to organizing dictionaries of words. And in those dictionaries of words, there was common structure in those words. For example, we could have one word that's a prefix of another word. And so we want our data structure to mirror that common structure. And trees are really great for that because you can indicate when nodes are connected to one another. And in this tree structure, we have that one node is a parent of another node if that parent is a prefix of its child. And so we could organize our data structure in this way and have the nodes be linked by this prefix relationship. And so in all of these different viewpoints and all of these different applications, what we're thinking about are these objects and then whether they have some explicit connections between them. So we have these basic objects and their relationships. And that's really at the heart of what we need when we're talking about graphs. So graphs really generalize this principle of organizing a whole lot of objects together so that we have objects and relationships between them. And now we want to think more generally about what all the kinds of relationships we might have. So really, when we define a graph, what we need to do is define those basic objects and those relationships. And those basic objects are depicted in our representation of a graph as vertices or nodes. And so each object is one vertex in our graph, also known as a node, and we draw that pictorially as a circle. And then when we want to denote a relationship between two vertices or two nodes, then we can draw an edge between those vertices or an edge between those nodes. And those edges sometimes are called arcs or links. So let's think about where we might use these graphs. So if we want to think about objects that are related to one another, a really good example is the internet. And we have in this internet all sorts of websites. Each of us can, create our own website, write up some HTML code, upload it to some server, and maybe connect it to other websites using hyperlinks. And so we can imagine and visualize this entire internet as a graph where each of the basic objects, the vertices in our graph, are the websites. And then there's an edge between two websites if there's a link that connects them. Now, there's other contexts in which we have objects that are related to one another. And we can think about in the physical world when we want to connect up to a cell phone network. And we can think about the coverage of the network depicted by a graph. And so we want to represent the coverage of that cell phone network across the whole city, and that's going to determined by which towers have overlapping coverage areas. And so we can imagine a graph whose vertices are the cell phone towers, and then there's an edge between two cell phone towers if their coverage area overlaps, and so they could hand off a call to one another. But we could also think about a different situation in which we have basic objects and relationships, and this situation could map something much more sociological. So we could imagine that the basic objects are people, real live people in the world, and the relationship between people could be a friendship relationship. And so we can imagine a huge graph where each node on the graph is a person, me, you, each one of us is a node on this graph. And then there would be an edge between two of us if we were friends with one another. And so you could imagine the questions that we could ask about this graph that would tell us how communities are formed and evolve in the world that we live in. And these social networks, as just a quick peek, are what we'll be focusing on in the capstone project for the specialization. So stay tuned for those. But for now, we're actually going to think about a different graph for this course's project, and this graph is more geographic. So we can think about a graph that represents how we move around in the world. So our basic objects in this graph could be cities or locations in the world, and then we might want to go between one city and another. And so the relationships between cities could be, for example, a nonstop flight. And so if you've been in a plane and you've flipped through the Seatback magazine, there's often a picture of all the flight paths of that particular airline, and you see that there's edges between two cities if there's a nonstop flight offered by that airline between those two cities. And so then we can think about this graph is telling us information about how to plan a route throughout the world. So we'll talk a lot more about that in the project, but I want to mention that if we think away from the flight context, there's more than one way to get between two cities. So for example, we could think about driving, having a road trip between one city and another. And so we could have a graph that is richer than just the flight plan and have different kinds of edges for different ways of transportation between the two cities. And so in our graph, we might have multiple edges between two nodes, between two vertices. All right, one more example. We could have a graph where the basic objects aren't physical things. They're not cities, they're not people, but rather they're tasks. So think about a big complicated project that you might want to produce, perhaps with a big team. And in this project, there's lots of individual tasks. So maybe it's a software engineering project, maybe it's a big cooking project, it doesn't matter. It's a really big project that is split up into small tasks. But some of those tasks require another task to be completed before we start it. And so there's relationships between certain ones of those tasks which are dependency relationships. And so we can picture those relationships in a graph where we have the vertices are the tasks, and then we have an edge from one task to another if we need to complete that first task before we go on to do the second one. And then what's useful about having this dependency graph is that then solve the scheduling problem. How do I take all of these tasks and put them in order so that I can complete my project successfully while respecting the dependencies? So these graphs are super powerful. It's a really general notion that can be used and manipulated to represent a lot of different problems. And so if we think more generally about the problem that we have, in each of these cases, we're asking some questions about a graph. And then afterwards, Christine and Leo are going to come back and think about how do these general questions actually map down to the concrete route planning that we want to do in the project. So for graphs, in general, we want to create a graph. We want to ask about two vertices in the graph. Are they close? Are they far? Is it possible to get from one to the other? We can ask also global properties of the graph. Are there lots of edges? Are there lots of relationships? Are things tightly woven together? Or is it a pretty sparse graph? And then we can also ask about, can we break up the graph into connected components, into different pieces? Are there pieces that really don't interact much with one another? Or is everything really intertwined? Are there paths between every two vertices? So we'll be thinking about each of these questions, but before we do that, first of all, we have to define the graph. So that's what we'll do next. So in the previous video, we started talking about graphs as this general data structure where we have nodes and we have connections between them. And what we're going to do now is really hammer down some definitions and see how these definitions come into play. So by the end of this video, you'll be very comfortable with these basic definitions that are associated with graphs. So as we mentioned, in order to specify a graph, all we need to talk about are what the collection of basic objects are, and then what the relationships between them need to be. And the terminology that we use for the basic objects are the vertices or the nodes, and then the terminology that we use for the relationships between them are the edges or the arcs or the links. Now, the vertex set is often denoted by capital V. The edge set is often denoted by capital E. And something you want to keep in mind is that when we're talking about the size of a graph, which is going to be important when we think about performance, the size of the graph really depends on both the size of V and the size of E, the number of vertices and the number of edges. And we'll talk more about that as we develop more algorithms. Now, so think back to the example with a friendship graph. If I'm your friend, you're my friend, we're both friends with one another. It's not like I can be your friend, but you can't be my friend back. It doesn't work. In that situation, our edges between vertices are undirected. They don't have arrowheads. They don't point from one vertex to another. A way of saying that in math speak is that the edge relationship is symmetric. Now, we have other graphs that ordering really does matter for, and think back to the example that we talked about before with dependencies, of task dependencies. And in that situation, the arrows really do matter. And so we can have graphs that are directed, which means that for every edge, we want to think about its endpoints. So we've got 2 endpoints for each edge. Each of the endpoints is a vertex, and it makes a difference whether the edge is pointing from one vertex to the other or vice versa. All right, so we've got a notion of undirected graphs, we've got a notion of directed graphs, and then we can also think about enriching these graphs a little bit, and sometimes our edges can carry with them more information. So sometimes we want to label our edges perhaps with weights that might determine, or they might represent something like the cost of going across this edge, and you'll see the weights coming into play again and again when we develop algorithms in the future modules of this class. So we've got these vertices, we've got edges, and they're coming together to build up this data structure. So let's start by thinking about the neighborhood relationship of a particular vertex. And so one vertex is a neighbor of another vertex if there's an edge between them. And so take a look at this particular graph and think about what the neighbors are of the vertex 4. So let's talk about one more notion that's going to be really important about graphs, and that's the notion of paths. So when we're thinking about a big graph, what often we want to do is find a way of getting from one part of the graph to another. And so that might be useful in the route planning project that you're doing in this class, but it could also be useful for thinking about global properties of the graph. And so a path in a graph is a sequence of vertices and edges that depicts, you can imagine yourself hopping along the edges in the graph to get from one place to another. And so I'm only ever allowed to move along edges, from one vertex to another along an edge. So let's think about this particular directed graph and think about for which pair of these vertices is there a path in the graph that goes from the first vertex to the second. All right, now we're going to tweak this example just a little bit and see whether things will change when we drop those arrowheads from the edges. So think about the same pairs of vertices, the same underlying vertex set, but now when we've dropped the arrows on the edges, which pairs of vertices can be reached from one to the other. So the moral of those two examples was that directionality really matters, and that when we're thinking about moving along the graph, what we need to think about are those edges, but also the directions on the edges, and as we see, any other information that we've encoded into those edges. So in the next few videos, what we're going to do is think about moving away from this abstract depiction of circles and arrows, and think about how do we actually bring this graph data structure to Java.
Graphs are used at Google in a lot of different ways. One of the most obvious ones from your studies is probably going to be maps, where if you try to establish what the best route is to get from point A to point B, we're obviously using a graph behind the scenes. We're storing possible destinations, or we're treating possible destinations as vertices on the graph. And then the connections between them are the roads or flights or public transport connections or other stuff like that between those points. And what we're doing then is executing fairly sophisticated algorithms to find shortest paths, with the times being one possible source of weights for the connections, or road distance being another possibility, and so on. But there's other places where we use graphs as well. There's this entity called the knowledge graph that we use to establish relationships and information about different things. For example, if you're to ask your phone, who is the President of the United States? Okay, fine. We go off and there's this entity, President in the United States, that can be used to establish, currently that's tied back to another entity within the knowledge graph, Barack Obama. If you then ask, how old is he? Okay, we remember that the last query had been about Barack Obama, and we can go ahead and find the information that's associated with your query, an attribute of that node, Barack Obama's age. If you then ask your phone, how about his wife? Now we've got to go ahead and say, well, the entity we were dealing with before is Barack Obama. There's presumably, because of your question, there's an relationship between that entity in the graph, Barack Obama, and some other entity, which is labeled effectively spouse or wife. We traverse that connection from the original node on the graph to the new one and say, oh, it's Michelle Obama. Okay, great. And based on your previous question, we understand that what you're looking for is the attribute age that's associated with Michelle Obama, and so we can find your answer. So graphs are useful in lots of different ways. Some of them obvious, some of them less so. And there's a lot of other places that we use them as well. But it's the same data structure, and just more data and interesting algorithms.
I'm Aaron Schur, and I work in Google Shopping. My team manages lists of products for sale coming from merchants like Sportsman's Guide and Zalando. They send us information about their products, and we tweak it so they'll make the most effective ads. In order to do that, we manage a graph of processors, where each processor does various things to the product, like making sure it says red and not scarlet or carmine or ruby. Some processors take multiple inputs, like product info and price in 2 different files. Some have multiple outputs, like splitting the products into different languages. We use graph algorithms to optimize our performance, analyze dependencies, and for many other purposes.
All right, we're ready to implement graphs. Now that we have their definitions and some of the motivation behind the graphs out of the way, let's think about how to write some classes to describe graphs in Java. And so by the end of this video, you'll be well on your way to doing just that. So thinking back to what we have to represent in our code, we have the basic objects, which are the nodes or the vertices, and then we want to talk about relationships between them. But now we have to translate everything into objects that the computer can actually manipulate and work with. And so we're going to represent our vertices as integers. And so each vertex is going to be named by some integer. It's going to be a non-negative integer, 0 through some number. And then we can talk about the relationship between those integers as those edges. And so let's start building up our class. And remember that little icon that we've been using throughout the whole specialization to indicate a class definition. And so for our class, we're going to have to keep track of, in a given graph, how many vertices we have and how many edges. And so those are going to be our private member fields. And then as we build up a graph and add more vertices, add more edges, we're going to want to be able to have access to those key properties that we care about, the number of vertices and number of edges, that, as we said before, will determine the size of the graph. We need both of those components. We're going to start by saying any graph needs to tell us information about that. Now notice that the class that we're defining right now is an abstract class. And in the abstract class, what we're doing is we're saying some data that's associated with any graph and some methods that ought to be available whenever we have a graph, but we're going to leave some of the implementation not completely specified, and we're going to leave it to our subclasses to specify how we implement some of the key functionalities of the graph. So in particular, for a graph, we're going to want to add vertices. And so any graph ought to be able to do that. So we have a method in our abstract class that says we ought to be able to add a vertex. And notice that there's no arguments to this method, because what we're going to do is just say, however many vertices we have now, those have certain indices. Now add a new vertex and just give it the next available index. And how do we do that? How do we represent vertices? Well, that's going to be an implementation detail that's decided by the subclass that we'll write a little bit later. And so as part of our add vertex method, the first thing we do is we're going to call the implement add vertex method that at this point we're going to leave abstract. We're going to say whichever class fills in the specification, fills in the implementation, will have to tell me how to implement adding a vertex. But any graph ought to be able to do that, and as soon as I've implemented add the vertex, then I need to increment my count of how many vertices there are by 1. Okay. Now we're going to do a similar process for adding edges, and for our abstract class definition, we're going to specify that we need at least one other method that should be available when we have a graph, and that's the getNeighbors method. Now, why is that important? Why do we care about getting neighbors? The reason we have a graph is not just for the nodes and thinking about them as objects, but we care about the relationships. And so if we have a particular node that we're trying to think about, then we want to know which vertices are adjacent to it. And thinking back to the project and thinking back to the application that we care about, if our nodes are cities, then what we'd like to know is which other cities could we get to just by following a single road? Or if our edges represent airplane routes, then which cities can we get to just using a non-stop flight? So the getNeighbors method is a really important method that we would like to implement in our graph. And so what our next step will be is thinking about the subclasses that we'll define in Java to fill in some of those abstract methods, and in particular to make decisions about how to represent our vertices and our edges so that we know how to implement those methods. Okay, so we've got the abstract class spelled out in terms of what methods our graphs ought to be able to implement. And now let's think about how we would actually go ahead and implement some of those methods. So in this video, you'll be able to see how to do at least one implementation using something called an adjacency matrix. So let's think back to an example of a graph that we've been going back to a little bit in this sequence of videos. And so this is a small example. Most of the real-world examples that you think about will have many, many, many more nodes and many, many more edges, especially when you're thinking of the applications we care about, for example, in the project, where the nodes are representing cities or intersections of roads, and then we have the edges indicate ways of getting from one place to the other. So think about the number of cities in the world or the number of roads in the world, and you start getting to really big graphs. But when we're doing the definitions, it's good to have a toy example of just a few vertices, a few edges, so we can see how the definitions play out, and then afterwards we'll scale up to the realistic problems. So with this example, we just have 6 vertices with some edges between them, and we could label the vertices 1 through 6. We could use these labels of vertices to index into some array structures. And so if we think about representing the relationships between these vertices, so we can think of a grid. So this grid would be indexed by the labels of these vertices. And what we'd like to do is store information in a particular grid location based on whether these two vertices do or don't have an edge between them. So for example, if we think about the vertex labeled 1 and the vertex labeled 2, in this graph, there's no edge between them. And so we'd like to store that information. And so in this grid representation, we're going to say there's no edge and represent that with a 0. Now, there are some edges in the graph that we're trying to represent. And so, for example, if we look at the vertex 0, it's adjacent to the vertex 1, namely there's an edge that starts at 0 and goes to 1. And so we'd like to record that, and we're going to record that with a 1. Now notice that at this point we've got 0 and 1 as the entries that we've used in this grid. It's possible to have bigger integers, and that might indicate multiple edges from one vertex to another. Now notice that in this graph there's an edge that goes from 0 to 1, but there isn't an edge that goes from 1 to 0. And so in the symmetric location in the grid with row 1 and column 0, we put a 0. If we were thinking about representing an undirected graph, as a matrix using these zeros and ones to indicate whether the pairs of vertices are related or not, then in those undirected graphs, this grid would be symmetric. Namely, if we tried to imagine flipping it across the diagonal, then we'd get the result of the flip would look exactly the same as the original matrix. So with undirected graphs, we get more structure in this adjacency matrix. But for directed graphs, we need to think about every single grid point on its own independently. So if we want to fill in the rest of this adjacency matrix, and matrix here just means 2D array, then we notice that we are going to get a 1 for every single edge in the graph. And there's 1, 2, 3, 4, 5 edges. We see 1, 2, 3, 4, 5 ones in the array. And the rest of the entries, well, they're just zeros, because the rest of those entries indicate pairs of vertices that happen not to be adjacent in this graph. And so we indicate that in the adjacency matrix by putting a 0 in each of those locations. All right, so we've got a representation of this graph as this 2D array, this grid of zeros and ones. But really, our computers, don't really get as input this grid of zeros and ones. We still want to translate how we're doing this representation to Java. And so let's think back about the class structure that we have to write in order to represent the graphs. And from the previous video, we saw we've already set up an abstract class, and now we'd like to define a subclass of it that's going to implement those abstract methods. So in our new class, graph adjacency matrix, so graph adj matrix, we're going to extend that abstract class we started with, and the new piece, the new field that we're going to define for objects that are of type graph adjacency matrix are these adjacency matrix that are going to be 2D arrays of integers. And so what we'd like to do now is implement those add vertices and add edge and get neighbors methods using this idea that the relationships in the graph are encapsulated in this matrix. So let's think about how to do at least one of these methods to start, and let's think about implementing adding an edge. And so for adding an edge from a vertex v to a vertex w, and each of these vertices is encoded by an integer, then really what we're doing is setting that location in the matrix to say, yes, there's an edge between my two vertices. So in row v and column w, there ought to be a 1. Now notice here we're saying this flag is set to 1, which means that we're not going to take into account multiple edges between vertices. We're going to say that if we are adding an edge between two vertices, we're going to assume that there wasn't an edge there before, or if there was an edge, we're not going to double count that edge at all. We're just going to say if there's an edge, it's going to be set to 1. All right, that wasn't too bad. So what about some of the other functionality that we wanted in our graphs? So in particular, how do we add a vertex to the graph? So think about how vertices are represented in this graph, and we don't have a dedicated data structure that tells us about all the vertices. The way that we have access to the vertices is as the row labels and the column labels of the adjacency matrix. So if we want to add another vertex, what we need to do is add another row and add another column to correspond to that new vertex. But that means increasing the dimensions of this adjacency matrix. And so that's a little bit tricky. Now, what we want to do is we want to say, okay, so if the vertex that we need to add has to really increase the size of our adjacency matrix, then we're going to plan ahead, and we're not going to change this adjacency matrix just by adding one row and one column at a time, but we're going to say if we're adding one vertex, then maybe we'll need to add more vertices later, and so we're going to make our new adjacency matrix much bigger. So in particular, we're going to double the number of vertices, double the number of columns, and that way, at least for a while, we'll be set as, while we're adding more vertices, we won't have to increase the size of our array each time. Because if you remember, when we want to increase the size of our array, we can't just take our old array and fiddle around with it. What we need to do is create a new array of the new size and then copy over all the contents from the old array to the new array. So that takes a bunch of time. And so we don't want to have to do that too often. And so our idea is going to be to add a vertex. We're going to, if we need to change the size of the array at all, we're going to change it by a lot, double the size, so double the number of rows, double the number of columns, and then copy over all of the values from the old adjacency matrix to the new adjacency matrix, and then figure out how to deal with the new vertex that we're dealing with. Namely, we're going to think of adding this vertex and not connecting it to any other vertices. So there's not going to be any ones in the row or the column corresponding to that new vertex. Okay. So we saw that adding an edge was really very quick. Adding a vertex had to be done with a little bit more care. And we can think about filling in the rest of this class definition. We need to, of course, define a constructor, which is going to initialize our adjacency matrix, and we're going to fill in some of the other methods as well. Now, in particular, when we're talking about graphs, a useful method to keep in mind is to think about whether two vertices are, in fact, neighbors of one another, if there's an edge that goes from one vertex to another. So thinking about this implementation of the graph, where we have our edge relationship defined through this adjacency matrix, how long will it take to test whether there's an edge between one vertex and another? Okay, so let's come back and think about how to finish off this adjacency matrix representation of the graph. And in particular, let's reflect on what properties we've seen as we've built up this class. So you'll write up some of these other methods as part of the project, and also will guide you through some of them in the support videos. But as you're writing these methods, you want to think about the performance implications of the data structure that we've chosen. So we've chosen a data structure that is very algebraic. It's a 2D array, which we can think of abstractly as a matrix that we can do linear algebra on. And so it turns out that once we represent a graph as this algebraic representation, then the linear algebra tools are very powerful. And you'll see one example of that in a later on video. But as you go on and think about more graph algorithms and more applications of graphs, you see linear algebra coming in again and again and again. And so thinking of the adjacency matrix as a crucial representation of the graph is indeed very powerful. But it does have a lot of drawbacks, because even though it was really fast for us to implement the test for edges method, as you saw in the in-video quiz, and even though it's really fast to add and remove edges because we're just dealing with a single entry in the 2D array, if we want to change the big structure, the underlying structure of the graph by adding vertices, that took a lot of time. And the most important piece that is a drawback for the adjacency matrix is that when we think about the storage that's required in an adjacency matrix, we need to store a 2D array whose dimensions are the number of the vertices. And so that means that we're storing n squared pieces of information if n is the number of vertices. And that can get really, really big. So think back to what these vertices represent. These vertices are cities, or their intersections, or in biological representations, they might be genomes, or they might be little pieces of genomes, or if you think back to like the World Wide Web analysis, then each of these vertices is a unique URL, a unique website, or if we're thinking about social networks, then each of these vertices is a person. And in all of these, in all of these applications, the set of vertices is huge. Not only is a set of vertices huge, most vertices are not related to one another. So most people are not friends with most other people in this world. Our communities don't encompass the whole globe, don't encompass the whole world. Similarly, most cities don't have nonstop flights to all other cities or to many, many other cities in the world. Usually we have to think about going out gradually and doing lots of shorter flights in order to get from one place in the world to another. And so even though when we have a lot of vertices, there's a lot of potential edges, there's a lot of potential relationships, many of those edges just aren't in the graph. Whereas storing the adjacency matrix of a graph requires us to store information about every single pair of vertices. And that can take up a huge amount of space. And so if space is a concern, if we're trying to depict a big graph, then often adjacency matrices are prohibitively big. We can't store the whole adjacency matrix. And so we're going to think about another implementation of the edge relation description of the graph that will lend itself better in many practical applications. Okay, so we're ready to see a different implementation of graphs, this time using something called an adjacency list. So by the end of this video, you'll be able to think through the implementation of graphs in Java using adjacency lists and think about comparing adjacency lists and adjacency matrices, which were the focus of the previous video. So let's think back to that example that we keep using of a small graph. And remember, this is just a toy example in the project, and in all the applications, the graphs will be much, much bigger. But just to illustrate some of the definitions and the questions, we're going to keep it small. So our vertices are labeled by integers from 0 through 5, where we have 6 vertices. And we want to think about representing the edges between the vertices. So we've talked about an adjacency matrix, which was our 2D array of zeros and ones, 0 indicating that there's no edge between the vertex in the row and the vertex in the column, and a 1 indicating that there is such an edge between those two vertices. Now we talked about how this 2D representation required us to store a whole bunch of information about a whole bunch of edges that might not actually even be in the graph. And so let's think about a different way of representing these edges. Instead of storing a 2D array of integers, what we'd like to do is say, for each vertex, what are its neighbors? Where can we get to from that vertex in one hop? We're going to have as our basic data structure in this class a map that associates vertices labeled by integers and lists of other vertices, lists of integers. Gives an adjacency list, a list of vertices to which we're adjacent. Okay, and so let's think about how this corresponds to our toy example. So, for example, the vertex 5 ought to have in its list of adjacent vertices both 3 and 4, because there's an outgoing edge that starts at 5 and then goes to vertex 3, but there's another edge that starts at 5 and goes to vertex 4. Then we can think about, for each vertex in our graph, what its set of neighbors looks like. Now notice that I said outgoing edges, and when we're talking about neighbors, we're talking about neighbors that we can get to starting at the current vertex and going out. And because our graph is directed, that directionality and that asymmetry is important and is going to come into play. And you'll see how in just a little bit. So first of all, notice that we can capture the whole graph relationship just from understanding these relationships. Every edge will be pictured at some point, or will be depicted in this adjacency list collection at some point, because we can just look up an edge by saying what's its start point. That's going to tell us which adjacency list to look in, and then the end point will show up in the list of neighbors of that starting point. Okay, so now we want to translate this back to Java, and we want to think about implementing those two abstract methods that we talked about in the abstract class that defines what a graph ought to be able to do. And so, for example, we want to add a vertex and we want to add an edge. And when we've got these lists, well, these lists are easy to change dynamically. And so, for example, if we want to add a vertex, all we need to do is to put a new association of an integer to a list of integers in our map, namely our data structure that stores these adjacency lists. And so we just create a new array list of integers that's going to be the set of neighbors of, or the list of neighbors of the new vertex. And we're going to put an entry in the map that says, for this new vertex v, associate this set of neighbors. Okay, not too bad. Similarly, to add an edge, then we can use in a lot of the built-in functionality and say, I want to add an edge between v and w, so that means I have to add w to the list of neighbors of v. So I have to get the list of neighbors of v by using that map data structure. So I'm going to get the object associated with the key v, and then that object, which is a list, I'm going to add to it the new neighbor that I'm asserting that w is a new neighbor of v. So I go ahead and do that. So what we're seeing is that it's easy to add vertices, it's easy to add and remove edges. And if we think about the storage requirements for these adjacency lists, they might use a lot less memory than adjacency matrices, especially if we have what's known as a sparse graph. So a sparse graph is one where there aren't a lot of edges between vertices compared to the maximum possible number of edges. So if we do a little bit of counting and we think about the number of edges possible in an abstract graph, if we have n vertices, then there's n squared many possible edges between them if we allow self-loops and we allow an edge to go from any vertex to any other vertex and not allowing parallel edges. So n squared can get really big compared to n. A sparse graph is one where the number of edges asymptotically is closer to just the number of vertices. And if you think about most applications do lie in the realm of the sparse graphs when we're depicting the website graph, which is connected via hyperlinks. Again, most websites don't have that many hyperlinks out to other websites, and so again, that graph is going to be a sparse graph. And then going back to our project with the transportation networks, most cities don't have all that many outgoing roads compared to all possible roads in the world, and so this as well is going to be a sparse graph. And so lists seem to be winning out. Adjacency list representation seems to be winning out really well, but we talked here about easy to add vertices, easy to add and remove edges, and that might be a bit selfish. Like, as programmers, it was pretty easy because we were able to use built-in functions. But if you think back to performance analysis, when we're trying to think about the performance of methods, we want to talk about them being fast, not just how easy was it for the programmer to code up this particular method. And so we used in built-in methods of the map class and of the ArrayList class. And so what we have to do is look at the documentation for those classes to get insight into how long those methods actually take and how much that time scales with the size of the input and the size of those data structures. And so we can do that. We can look up the documentation, and what's really nice is that in this documentation for the ArrayList class, it's spelled out right over there that the operations of looking for the size of a list, or asking if something is empty, or getting an element from the list, or adding an element from the list, all of these are roughly constant time operations. Now for the add method, it's a slightly more complicated analysis. Its amortized time is constant, but for our purposes, what we want to get out of this documentation is that all of these operations are very efficient. And so not only was it easy for us as the programmers to write these methods using the built-in class methods, those methods that we wrote will also be very efficient. So why use anything else? And the reason we still like having adjacency matrices in our back pockets is for that algebraic structure that it encodes. And for more complicated analyses and algorithms about graphs, that algebraic structure turns out to be really useful and very powerful. And so we'll see a little bit more of that later on.
In this concept challenge, we're going to be looking at how much space is required to represent a graph. So remember the concept challenges, you're first going to think about this on your own. You're going to discuss this with other learners if you have them around. You're going to watch our UC San Diego learners discuss it, and they're going to answer the question again. And lastly, you'll get to confirm your understanding with us with our discussion. So first, a warm-up question. What I want you to do is think about how much space is required to represent a graph as a matrix. So this is big O, tightest bound. Go ahead and think about this on your own, answer the in-video quiz. I'll see you back in a moment. So I'm hoping you saw when you work through this problem on your own was that if you're going to represent this as a matrix, what you end up is with the number of vertices is the number of columns, and the number of vertices is the number of rows. So if you do the number of vertices as columns times the number of vertices as rows, you're going to end up with O of V squared, which is the correct answer for this question. Now, as a quick aside, I want to ask you, what would change if I made this a undirected graph? Well, not much changes actually. So what you'll notice is I've already changed our graph structure here to be undirected. And all you'll notice is that it's essentially a symmetric matrix. You're going to see that half of the information here is essentially redundant. But it's still big O of V squared. So the next question is, when we start working with adjacency lists, how much storage is required for that representation? Go ahead and work on this on your own. Listen to the UCSD learners discuss it, and I'll see you back in a few moments.
Hi, my name is Huang.
My name is Paul.
My name's Yume.
So let's get started.
So I think adjacency list has to be different from adjacency matrix. So I don't think that D or E are right because they are still squared for the magnitude of both the vertices and the number of edges.
Yeah, I agree with you. I think the answer should be one of A, B, or C, because in order to store the graph, you have to store edges or vertices, but I'm not sure if you have to store both.
Well, each vertices should know what edges are connected to, right?
Mm-hmm.
So what if there's no edges?
Welcome back. I hope the UCSD learners discussing it was helpful. What we're going to do to solve this is just look at the representation. So if we have this representation for this graph, what you're going to recognize is that the number of rows here are the number of vertices. So this is essentially O of the number of vertices. Now if you start trying to think about how many edges are represented per vertex, this gets fairly complex. But if you just realize the sum of all the edges represented here is just the sum of edges, it's a lot easier. So what we have here is the number of vertices as the rows, the number of edges essentially as what's contained within all those rows. And what does this end up being? Well, this is going to be O of V plus E. So, and again, the way to think about this is if there weren't many edges at all, this would be dominated by the number of vertices. If there were tons of edges, this would be dominated by the number of edges. But you need to have both terms in there. Now, what I want you to realize is that this is much more efficient if you have a sparse graph. So if you're comparing the amount of storage space required for an adjacency list versus the amount of space required for a matrix, for a sparse graph, easy, hands down, adjacency list is better. And if this were a dense graph, so there's tons and tons of edges, well, there may be as many edges as essentially order v squared. Well, that just makes this basically as bad as a matrix, not much worse. So in general, adjacency lists are used quite heavily because of their space efficiency.
Generally, when software engineers think about measuring performance, usually the first thing we turn to is thinking about measuring speed. How fast is it going to run? Because that's what users generally care about as the most obvious measurement of performance. But there's other things that can matter too, depending on the environment you're working in. If you're writing software that's going to run on a cell phone, then you may have to give up a certain amount of speed in order to take advantage of the fact that you've got a limited amount of memory in there, or a limited amount of storage. And so you may be willing to trade off raw performance in terms of CPU cycles in terms of getting better performance out of the memory that you have. I'll use a slower algorithm because I don't have the RAM to make the faster algorithm work. I may be willing to take a performance hit because I'm going to be fetching data over the network more often rather than downloading it all and storing it internally so I've got it ready to play whenever or use whenever I'm ready to go. Because if I'm tying up 12 gig of memory on your iPhone, then you're not going to be real happy about that. But if I tell you, well, you need to be network connected in order to make use of this functionality because we don't want to tie up 12 gig of memory on your iPhone, then that's a trade-off that I may be willing to make and that most of the customers for a piece of software are probably likely to make. There can be other things that people care about too. Power consumption. People may worry about things like the heat that's produced. If it's something that's going to go into an environmentally sensitive area, like something that's implanted in the human body, then that's an issue as well. So there's different kinds of performance that you may care about depending on constraints. Again, the default is speed, because that's easy and obvious, and for lots of engineers, that's the one that we really care about because that's what the users see. But other constraints exist, and we've got to worry about those sometimes too.
Hi, my name's Kevin, and one thing that I really struggled with was the memory of graphs and the big O of the memory requirement. So as you can see, some of these graphs, adjacency lists, have big O of V plus E, and I really struggled with that when learning with this course because it didn't really make sense to me why it was V plus E. So one thing that I tried myself was to do some examples by hand, and I drew these graphs out on my spare time and looked at them very carefully, and I noticed how big O of V wouldn't work for all of them and big O of E wouldn't work for all of them either. So I learned a lot just by doing examples on my own time, and I hope you do too.
All right, so we're ready to bring together some graph properties and implementation decisions and see the trade-offs between them. By the end of this video, you'll be able to implement a method to talk about the neighbors of a vertex in 2 different ways, each of those ways depending on the implementation that we have for the graph structure. Now, what we'll want to do in this video is think about the ramifications of the decisions of the implementation, and then how do we build other features of the graph based on those implementations. Now, you'll see more details of the Java code in a support video that comes along with this. And so stay tuned for that. All right, so let's think about what the notion of neighbor is really getting at. And we have our graph example that we've been working with. This is just our toy 6-vertex example. And if we want to think about a neighbor in this graph, we're talking about the relationship between one vertex and other vertices. And so a neighbor of a vertex is a vertex which is adjacent to that one. And adjacent here means that there's an edge between them. And so let's focus in on vertex 4 over here and ask which vertices are adjacent to 4. Now we can see that there's 2 edges that are related to 4 in some way. There's one outgoing edge and one incoming edge. And so if we drop the directions altogether, then both of the vertices 3 and 5 seem to be related to or adjacent to or connected to 4 in the same way. But for directed graphs, we're going to tease apart the relationship that 3 has to 4 from the relationship that 5 has to 4. And so let's focus on the relationship between the vertex 5 and the vertex 4. And we notice that the vertex 5 is the start point of an edge that ends at 4. And so we can talk about the in-degree of the vertex 4 as the number of incoming edges to that vertex. And so then in order to look at all of the neighbors of 4 that are neighbors by virtue of being the start point of edges that end at 4, we want to count all of the incoming edges to 4. We want to count the in-degree of that vertex. We could also talk about the out-degree of the vertex. We could talk about all of the vertices that we can get to starting at 4 and just going by one edge over to a new vertex. And so, for example, from 4, we could follow the edge to 3. And now let's start actually thinking about methods to implement finding these in-degrees and out-degrees. So for the out-degree, what we're trying to do is count all of the edges that are outgoing from the vertex 4. And one of our representation for graphs is the adjacency matrix representation. So we have a grid of 0s and 1s, and we have as many rows as there are vertices, we have as many columns as there are vertices. And each entry in the adjacency matrix denotes an edge which starts at the row vertex and ends at the column vertex. And so if we're looking at the number of outgoing edges from the vertex 4, we just need to look into that 4th row of the matrix and see how many edges start at vertex 4, namely how many 1s are in that row of the matrix. And so we can go along and see that there's exactly 1, 1, and so our out degree is 1. All right, we had another representation of graphs as well, a representation in terms of the adjacency list. And so in the adjacency list representation, we have a list that's associated with every vertex. And so for the vertex 4, we have a list that contains just 3. And what that denotes is that there's an edge that starts at 4 and goes to 3. And so if we're looking at how many edges start at the vertex 4, what we need to know is the size of the list that's associated with 4 in the adjacency list representation. And so now what do you think? Which of these representations of graphs makes it easier or more efficient to find the out degree of a vertex in the graph? All right, welcome back. Let's now ask the flip question and think about the in-degree of a vertex. And so if we're thinking about the in-degree of the vertex 4, in the adjacency matrix representation, things are very symmetric, and the incoming edges are just denoted along columns instead of along rows. And so if we want to think about the number of incoming edges to 4, we need to read off that 4th column in the matrix and look for 1s in that 4th column. Each one of those 1s has 4 as its endpoint. But in the adjacency list representation, we have a slightly different situation. Our markers or indices for which lists we have in the adjacency list representation are the starting point of edges. And so if we're looking for the incoming edges to 4, what we need to do is look in each one of the lists in the adjacency list representation and ask which one of those lists contain the vertex 4. Because if a list contains the vertex 4, that means that 4 is the endpoint of the corresponding edge. All right, so we have two different representations. Which one makes computing the in-degree of of a vertex more efficient? Alrighty, now what's next? We've talked about in-degrees, we've talked about out-degrees, we've seen how they both contribute to this notion of a neighbor of a vertex. And now what we're ready to do is implement some of these notions in Java. So in this week, we're focusing on the differences in performance based on implementing graphs using adjacency matrices and adjacency lists. And then in future weeks, you'll build even richer class structures for representing graphs. And you'll want to take these performance considerations into account as you're building these more complicated structures.
All right, in this support video, we're going to write some code. Mia has talked to you about two ways of representing a graph, using an adjacency list and using an adjacency matrix. And she's also talked to you about the out degree of the vertices in a graph. So in this video, what we're going to do is we're actually going to write a method where we get all of the nodes that are 1 degree, 1 hop away from a particular node in the graph. And we'll be writing this code for both an adjacency matrix as well as an adjacency list representation. So by the end of this video, you'll be able to write this code. We're going to do it together, not actually in Eclipse. We're just going to write it out on these slides. And the reason I'm choosing to write by hand rather than writing the code in Eclipse is that sometimes when you're writing on paper or on a tablet computer, you're a little bit more thoughtful about what it is that you're doing because you're not able to run the code and test it. So that's why I'm going to show you this code written out on a tablet. All right, so let's review the adjacency matrix representation for the graph. As you may recall, there's a row for every vertex in the graph. So these rows correspond to vertices 0, 1, 2, 3, 4, and 5. And then in each row, there's a 0 in the entry if there's no edge from that vertex to the vertex represented by the column. And there's a 1 if there is an edge. So for example, if we look at this edge right here, we can find that 1 for that edge in row 2, go over here to entry 3, and there's our edge. There's a 1 there. And 2 doesn't have edges anywhere else, so there are no other 1s in 2's row. So we're going to use this information to write the getNeighbors method in our graph representation. So we've got the start of our graph representation there on the screen. We've got our matrix representing the edges in the graph. And our goal now is to write getNeighbors. So let's go on and actually do the writing. Although before we do, let's actually go back for 1 second and look at this graph and think about how could we tell what nodes are neighbors of a particular node? Well, all we really need to do is we need to look at the row. So we just look at this row right here. And if there's a 0 in that entry, then it's not a neighbor. But if there's a 1 in the entry, then it is a neighbor. And that's the essence of the algorithm that we're going to use to implement our method. So here's the header for our getNeighbors method. We're going to return a list of integers, and that list of integers is going to contain all of the vertex integers that are neighbors of the particular node that we pass in. So we're taking an int v, which is a vertex in our graph. We're going to return the integers representing all of the neighbors of that vertex. So let's get started. Well, what's the first thing that we need? We need to return a list. So we're going to need to have a list to return. So let's go ahead and create that list. And I'll make my list an array list. Okay, now we've got our list, and we're just going to implement that algorithm just like I described. V is going to be the row of the adjacency matrix that we're looking at, and then we're just going to iterate all the way through that row, looking for the 1s and adding them to our list to return when we find them. So we're going to need a loop. Our loop is going to go as long as I is less than the number of vertices in the graph. So I should be less than, and I'm saying here we have this getNumVertices method already defined for us. So I will be less than getNumVertices, and then I plus plus. All right, so now what do we need to do? We need to check the entry in the particular row that we're looking at, figure out if it's a 1, and if it is, we'll add it to our list to return. And in fact, I'm going to look to see if it's a 0, and if it's not a 0, then I'll add it to the list, just in case somebody's using some non-zero value to represent an edge, like a weighted edge. So if my adjacency matrix in row V at position I is not equal to 0, then I will add it to my neighbors list. And that's all I need to do. That'll collect all the neighbors of V. And then at the very end, of course, I need to return the neighbors. Oops. And that's it. That's our implementation of getNeighbors for our adjacency matrix. So let's now look at the implementation for an adjacency list. Here's our adjacency list representation of the very same graph. So let's look at how this works. We have basically a map that's going to map the integers, which are the vertices in the graph, to a list of all of their neighbors. Okay, so you might be thinking, this is actually pretty trivial. All we need to do is look up the index we're looking for and return the list of neighbors. And you'd be pretty much right. It really is almost that simple. So here's again our method header. We return a list. So now I can just, one idea is that I'll just go ahead and return the adjacency lists map. That's this variable right up here. So I'll return adjacency list map dot get to get the index V. So is it really that simple? Is that all I need to do? Take a minute and think about that. Is that an implementation that'll solve this problem? All right, now that you've thought about it, well, the answer is yes, and well, not quite. Yes, it actually does return a list of neighbors of the particular node V that we're looking for. But the danger is it returns the list of neighbors that we're using for internal storage inside our graph. We've just exposed this list that's supposed to be internal to our graph representation. So anybody out there could now modify this list and change our graph structure, and we don't want that to happen. So we can fix this problem by, instead of returning the list that we take right out of this hash map and return it to the user, we can return a copy of this list. So instead of just returning the list directly, let's just change it slightly so that we return a new list. And we can pass it in the thing that we were returning before. That implementation there is just a little bit safer than what we originally had. Both will return the correct list, but one will protect the private data inside our graph. All right, in the last support video, we looked at code for finding the one-hop neighbors for nodes in a graph that's represented as an adjacency list, as well as an adjacency matrix. But in your assignment, you're going to have to write some code to generate the two-hop neighbors. So all the neighbors you can reach in not just one edge hop, but two edge hops. So what we're going to do in the support video is give you some help with that task. Now, spoiler alert, this is going to give away most of the code that you'll be writing on this part of the assignment. But it's also going to introduce you to a really cool trick for doing matrix multiplication for finding these two-hop neighbors. So if you don't want the spoiler of the code, but you just want that cool trick about the matrix multiplication, you can jump to part 2 of this video. So by the end of these 2 parts, you'll be able to write the code for generating the two-hop neighbors in both the adjacency list implementation as well as the adjacency matrix implementation of a graph. And you'll also be able to describe how matrix multiplication in an adjacency matrix representation can generate the two-hop neighbors for all the nodes in the graph. So let's get started. Let's go back to our graph representation. Here's a graph. It's a fairly simple graph that you can see here. That's the graph example that we're going to be working with in this part, in these 2 videos. So our problem again on the assignment is to write a method that, given a vertex, say vertex 0, comes back with a list of all of the neighbors that you can reach in 2 hops. So not 1, but 2 hops away. So if we start with that vertex 0, we can see that, well, we can't reach node 0 in 2 hops, but we can reach node 1 in 2 hops. We go down through node 2 and then up to node 1. We can't reach node 2 in 2 hops. We can only reach it in 1 hop, but if we go 2 hops, we go away from node 2. But we can reach node 3. And in fact, we can reach node 3 in 2 different ways. We can go through node 2 down through the bottom, or we can go through node 1 up across the top. So there are 2 different paths from 0 to 3. So that's the problem that we're working with. Now our solution is going to be similar but slightly different depending on our graph representation. So let's get started right away with our adjacency list representation. So here's our adjacency list representation of this graph. You can see that each node is an entry into this map, and the values of the map are just the lists of connected vertices. So we looked at the code for finding the one-hop neighbors in the last support video, and it looked like this. And we saw that this code was actually almost trivial. It was extremely easy to find the one-hop neighbors using the adjacency list representation. Turns out that finding the two-hop neighbors is really not that much more complicated. So what you're going to do to find these two-hop neighbors is, well, you've already got a way to find the one-hop neighbors. Here it is. So instead of just returning the one-hop neighbors, all you need to now do is, from each of the one-hop neighbors, just loop through them and find their one-hop neighbors. So the one-hop neighbors of the one-hop neighbors are the two-hop neighbors of the original node. So that's a pretty big start on your two-hop neighbor implementation for your adjacency list representation of your graph. So next, let's go on to consider how you would do this for an adjacency matrix. So before we do that, I want you to take a minute, pause, and actually draw the adjacency matrix for this graph example here. All right, welcome back. Hopefully this is the adjacency matrix that you came up with. You know that each row corresponds to the neighboring vertices in the graph. So for example, in row 0, we have a connection to vertex 1 and vertex 2 because we have edges from vertex 0 to vertices 1 and 2, but not to 0 and 3. Now let's look again at the code for generating the one-hop neighbors in this adjacency matrix representation. It was a little bit more complicated than the code for generating the one-hop neighbors in the adjacency list representation, but it wasn't terribly difficult either. So what we did was we went to the row V for the vertex that we're looking for, and then we just looped through that row, and for every entry that we found that was greater than 0, we knew there was an edge to that vertex, and so we added it to our neighbors list. And in the end, we just return the neighbors list. That's the code that we looked at. But if you look at the starter code, what you're going to find is that the code looks just a little bit different. So it actually looks like this. So there's a change. Instead of that if statement, we now have an inner loop. And that inner loop starts at 0, and it goes up to the value stored in the adjacency matrix at position VI. So my question for you that I want you to think about is, what is this change doing? All right, so you see that we've made this change. What in the world is this about? Well, it seems like what we're doing is we're going into the adjacency matrix and we're getting the value there. And if that value is 1, we'll only add the neighbor once. But if that value is greater than 1, we're going to add that neighbor multiple times. So the question becomes, why would the value in the adjacency matrix ever be greater than 1? And the reason is when we have multiple edges between nodes. So it's entirely possible that in a graph, we actually have 2 edges between, say, node 0 and node 1 in this case. And so the way we're going to represent that in the adjacency matrix is we're just going to change the value of that entry to represent the number of number of edges between that pair of nodes. So in this case, we'd have a 2. Between the vertices 0 and 1. And you'll see that actually this does happen in our road data. So sometimes there's a street that actually makes a loop, and there's an intersection here and an intersection here, and you can get from this intersection around this way and this intersection around that way, and we have 2 edges between those 2 nodes. So this is real world data here. And so what we want to do is for our get neighbors is we want to count each neighbor the number of times that we can get to it from the particular node. So because we can get to vertex 1 twice, following 2 different edges from vertex 0, vertex 1 is going to go into that neighbors list twice. We're going to maintain this convention in our get 2-hop neighbors. So if you can reach a 2-hop neighbor via 2 different paths, it's going to go into the 2-hop neighbors list twice. So let's go back to this original example that we were working with and talk about how to turn this getNeighbors method into a get2hopNeighbors method. And again, it's pretty straightforward. We already have the code that gets the one-hop neighbors. So now, instead of just adding I, as we did for the one-hop neighbors, to our list to return, what we want to add instead is the neighbors of I, the one-hop neighbors of I. And if you think about it, you've actually already got some code that will do that for you. So it's just a matter of calling a method that already exists. So again, here's your spoiler. This is a lot of the code that you're going to need in order to solve this part of the assignment. Okay, so you've got the code to solve this part of the assignment, but here's where things get really interesting, because we can do it the way I described. But if you have an adjacency matrix representation, there's actually a really cool way to solve the two-hop neighbor problem, not for a single vertex, but in fact for all the vertices in the graph. And this is using matrix multiplication. So I'm going to take our matrix and I'm going to represent it a little bit more mathematically. So instead of a table, I'm going to make a matrix that looks like this. And it turns out that if I square this matrix, the resulting matrix is a matrix whose entries represent the two-hop neighbors for each vertex in the graph. That's pretty cool. So let's take a look at how this works on this example. So here's the matrix I want to square. I'll just write the same matrix next to each other, and then I'm going to go through and perform matrix multiplication. And you may know how matrix multiplication works. You may have forgotten how matrix multiplication works. I always forget how matrix multiplication works, so I have to look it up every time. But the way we do matrix multiplication is we're going to take, for example, here, the top row in the first matrix, and do a dot product of that top row with the first column in that second matrix. And then we're going to put that in the upper left corner of our resulting matrix. So there's our dot product. We have 0 times 0 plus 1 times 0 plus 1 times 0 plus 0 times 0. So what's going to go into that first entry is just a 0. And if we think about that, that means that there are 0 ways to get from node 0 back to node 0 in 2 hops. And that's true. You can't get back to node 0 in 2 hops if you start there. Moving over a column. Now this is going to be the next entry over. It's the dot product of the top row with the second column. That's going to give us 1. And if we think about what's happening here, what we're saying is that there is a path starting in node 0 that takes 2 hops and reaches node 1. And in fact, we saw that path at the beginning of this series of videos. If we keep going, we see that there is no 2-hop paths from node 0 to node 2. There's a 1-hop path, but if you go 2 hops, you go away from node 2. And then something really cool happens with this last entry, because that value of this dot product here is actually equal to 2. And what that's saying is that there are actually 2 paths from 0 to 3 in 2 hops. And those are the paths that we saw at the beginning, the path across the top through 1 and the path across the bottom through node 2. We can continue to fill in this table, and we get the values that you see here. And if you look at this matrix, you'll see that it is, in fact, all of the 2-hop paths from all the vertices to every other vertex in this graph. So that's really cool. It's cool for a couple of reasons. One reason is we did it for all the vertices at the same time. So we didn't have to just loop through and do every single one separately like your method would do. We could do them all just in one fell swoop. The other reason this is really cool is that matrix multiplication is a very well-studied problem. It's extremely important to be able to do matrix multiplication fast for a lot of different problems. So there are a lot of algorithms and hardware as well that are optimized to do matrix multiplication extremely, extremely fast. So with those advances, with those algorithms, with that hardware, we can solve this problem very, very quickly when we have our graph in an adjacency matrix representation. All right, that's just for your enjoyment. You don't have to implement matrix multiplication for your assignment, though you can if you like to have a general solution. And we hope that you have fun with this part of the assignment.
Welcome. In this video, I'm going to walk you through your first programming assignment for this class. In this programming assignment, you're going to be implementing some basic graph structures, filling in our starter code, and working with real transportation data. So this video is going to assume that you've already followed the setup guide and you've got the starter code. So let's dive right into the assignment details. The assignment has two parts, and in both of those parts you'll be implementing some functionality in some graph classes. And you're actually going to be working with three classes. You'll be working with an abstract class, graph.java, and then two concrete implementations, extensions of that graph class, graph_adjacency_matrix.java and graph_adjacency_list.java. And if we go over here to the starter code, I'll show you where to find those classes. So we go over here into Eclipse, and we can see that it's inside the package basic graph. You'll see graph.java, graph_adjacency_list.java, and graph_adjacency_matrix.java. These are the files you'll be working with this week. Now you're going to see a whole lot more classes here. We don't have all the code yet into the starter code project, but you'll see a whole lot more stuff, but basic graph is still going to be the same. So find the basic graph package and work with graph.java, graph_adjacency_list.java, and graph_adjacency_matrix.java. Now, where are you going to find the methods that you need to implement? Well, you'll find the method that you need to implement for part 1 in this graph.java class. So you'll be implementing this method here called degree sequence. And you can find this method by clicking on this first to do over here. So I click on this first to do, and I see that the first thing I need to do in part 1 is implement this method degree sequence. So you're going to implement this degree sequence method. And what this method is going to return is a list sorted from largest to smallest, possibly with repetition, of the degrees of all of the vertices in the graph. So that's all you need to do, just like Mia described in the video. And you'll find a few of the methods that we already have implemented helpful for this method. So let's go over here to the write-up, and you'll see that we say that, in fact, there are a couple methods that are going to be useful. So the getNeighbors method, it's abstract in the graph.java class, but it's actually implemented in the subclasses. So we implemented that for you, and you can use that in the degree sequence method. We also provide for you a method called getInNeighbors, which is, again, already implemented for you in both of the subclasses, so you can rely on it in the graph.java file. And it's just like the getNeighbors method, only it returns the inNeighbors, so all of the nodes which have this node, v, as a neighbor. So both of these methods together will be very helpful for you in implementing the degree sequence method. So after you've written your method, you'll need to test your code. And to do that, we've provided you with some code and some data files that will help. So again, the starter code front-end orientation guide gives you an overview of all the data we provide for testing. And I'm also going to talk about some of that right now. So what we recommend starting with is the simpletest.map file, which is a file that contains a pretend map. So it's not real-world data, it's just a pretend map. Effectively, it's just a graph representing the following fake street map. And this is in the folder data, test data, simpletest.map. I'll look at it in just a moment. So this is what that test graph looks like. And you can calculate the degree sequence for this test graph. And you can make sure that the degree sequence that your method is returning is in fact the correct sequence for this graph. Now this picture shows an undirected graph, but when you look at the file, which we'll look at in just a moment, you'll see that this is actually a directed graph structure. So there are two edges in between each node, one going in each direction. So let's take a look at that file, and then we'll take a look at how that file gets loaded in the main method of graph.java. So we'll go over here into data, test data, and we can open up simpletest.map. So what you can see here, the format of this file, is that there are pairs of points. So this is a fake, in this case, latitude-longitude pair, another latitude and longitude pair, and then the name of the street, and then the type of the street. So latitude-longitude pair, latitude-longitude pair, those are the two endpoints of an edge, and then here's the name of the street and the type of the street. And you'll see that there's one edge in each direction for each of the edges in that graph that I just showed you. So if you want to change the graph structure, you can simply make a copy of this file and then modify it by adding the edges of the graph that you want to think about and you want to test with. Just make sure you always include a start point to the edge, an end point to the edge, and then a street name and a street type. Those fields are all required. So let's look at how this is used and how it's loaded in graph.java. So we go down here to graph.java, go down to the main method, and you'll see that we've already provided you with a lot of code for testing. So let's skip over the first part of this method here. I'll talk about this part later, but let's just take a look at how we're actually loading these data files. So if you look at this line right here, this graph loader.load roadmap, you can see that we're passing in the path to that simple test.map file I just showed you, as well as a newly created graph to test with. So here I'm creating a graph adjacency list object. So I just create a new one, and then I pass it in to this load roadmap method, and it's going to load up all of the data from this file into this graph. And then I can test with this graph. I can print it out, I can print the degree sequence, I can do any testing that I want with this newly loaded graph object. So that's it. And by creating new test files, you can load different graphs for testing into your code here in main. And for this method, for the degree sequence method, it doesn't really matter whether you use an adjacency list or an adjacency matrix, because of course it's calling the method from the graph.java, from the abstract graph class. So that's how you'll do your first basic testing. Now, once you get a little bit more confident that your code is working correctly, we encourage you to do some heavier duty testing as well as some visualization of these graphs. So what we want you to do is run not only on this very simple test dummy data file, but we also provide you with a bunch of real-world data files to test with. So if you go over here into data, into the maps folder, you'll see that there are a whole bunch of data collections. Hollywood large, Hollywood small, New York, Newbury small. So all of these are data collected from around the United States. And you can change these, change this file right here, change the path to the file, or add new commands, load up new graphs, print out the degree sequences for these graphs as well. Now, before you do that, we want you to try to make a prediction about what you think the degree sequences will look like with these different roadmaps. You can also test with some airport data. So we have available for you some routes that United Airlines flies, represented in graph form. So you could also load up this data. The way you do that, you can see right here, we've already done it for you. Instead of using load roadmap, you'll use this method called load routes. And then you can pass in this path to this routes ua.dat file. So this is, these are the methods that you use to load the graphs and to test them out. And that'll just give you some printed information about the graph. But what's even cooler is that in addition to printing the degree sequence, what we want you to do is visualize the data. So if you scroll down here to visualizing the data, you'll see that you can run this tool right here. So we want you to download this tool and run it. So why don't we just go ahead and open up this tool, and we can import the data. So you import the data, and you'll see that it's looking for some kind of a file. Now, we provide for you, this is not the same .map file or the .dat file that you used before. The data that you need to paste into this window here are these intersections files. So go over here into data, into the intersections folder, and you can see that there are a number of files here that correspond to the maps files that we just talked about, but they all end in this .intersections extension. So let's just pick here Hollywood large.intersections. I'm going to open that up, and then I will select all of the data in that file, copy it out, and go back over here, and then click here and paste it in. So now when I do this and I click import, it's going to show me the graph. So what you'll notice here is that this is, or you may not recognize this, this is actually street data, a graph of the street data for the Hollywood Hills. So each of the blue dots here is an intersection between the roads, and each of the lines in the graph are a road themselves. And you can do things like explore the graph. So you can see that this is the degree distribution of this graph, and you can see that I can actually also do things like click on an individual node and see some information about that node. So it has degree 6, an in degree of 3, and an out degree of 3, and I can look and see like, yep, that looks about right. So 1, 2, 3 going out, 1, 2, 3 going in. I can even view that particular point on Google Maps. So go over here and I see that, oh, look, that's right here. And the cool thing about this is that if I look at the data area that I've just plotted, it's basically this area right here, the Hollywood Hills. And you can see how this data right here really matches well with the structure of the graph that you see there. So here are the mountains where there's no streets, and here's where the streets become more regular down here. But these are the Hollywood Hills. So we encourage you to explore with this tool. Now, What's even cooler is that you can generate street data of your own and explore it. And let me show you now how to do that. So the way you're going to do that is you're going to be able to go into the application. So you'll run the application just like you saw in that demo video at the beginning, the project overview video. And I'm going to run it from the solutions folder because I have it all implemented in the solutions folder, but it's not yet implemented in the starter code. So let me run it from the solutions folder. I go up here and I go into the application folder and I click on Map App. And then I'm going to run that. So there's the application, and I can zoom in. So let me just zoom in and say I want to get some data around, say, UCSD. So I can zoom in to a piece of UCSD. This is right around where I am right now. And I can then go down here and I can fetch that data. So let me enter in a name for this file. So I'll call it myucsd.map, and I'll fetch this data. And it takes a little while, so I just say OK. It's fetching the data for the current map, and I just wait. And then after a time, you'll see that it was written to a file. And so it's written into the folder data slash, it's actually maps slash myucsd.map. So after the application reports that it's saved that data file, the place you'll find it is in your Maps folder. So you may have to go over here into Eclipse and right-click on Maps. You will have to do this, and then click Refresh. And then you'll see that file that you just saved appear right here. So here it is. However, this is not yet suitable for loading into that graph visualization tool that I told you about. So what you'll do next is you'll go back into the main method for graph.java, and you can see that there are these calls at the top, graphloader.createIntersections file, and then there are some file names. And what I'm going to do is I'm going to change these file names to be the path to that data file I just saved. So maps slash myucsd.map, and then this is the destination file. So data slash intersection slash myucsd.intersection. And then I don't want the .map, so just myucsd.intersections. And I'll get rid of these two lines because I don't really need them. And then I can go ahead and save that and run it again. And if I run this, what I'm going to see is I'll see in just a second. So I run this. There's some output that'll help you with debugging. But now if I go into this intersections file and I refresh it, you can see that myucsd.intersections has appeared. It's this file that I can load into that application, the visualization application. So I select all of these points, I go back over here to the viewer, I click import data, I paste in all that data, and I import, and lo and behold, I can see this data that I just saved. Now, it wasn't a very large region that I just saved, and so if I go back over here and look at this region, there are relatively few intersections. So there's this intersection, so there's very, very few intersections in that file that I just saved, so I see a very, very small graph. But you're welcome to download larger graphs. We recommend that they're not too big. We recommend, neighborhood size or small city size. Otherwise, the files will be very, very large and take a long time to download. But that's the process for how you can use this visualization tool to visualize your custom data. So it's pretty cool stuff, and we encourage you to play around with that. But for the moment, let's finish walking through the project. So that's the end of part 1. And again, this walkthrough was very long, but the actual work you're going to do is not very long. When you're all done and you think your file is working correctly, your method is working correctly, you will zip up graph.java, graph.adjancylist.java, and graph.adjancylmatrix.java. So graph.adjlist.java and graph.adjmatrix.java, and submit this zip file for part 1 of the assignment. We'll run some tests on your code to make sure it's correct, and if it's not, you're going to find some files in the starter code, and you'll see a file called degreegrader.java in the basic graph package. That's our part 1 grader, and you can run that to see what went wrong. Very quickly, just to finish it up, the next part of the assignment is to implement the getDistance2 method in both the graph adjacency list and the graph adjacency matrix representations or implementations. We already have a support video on this, so I won't go into too much detail, but essentially all you're doing is implementing this method right here, public list integer getDistance2, which returns all of the 2-hop neighbors from this vertex V. When you're confident that that's working correctly, again, use the same method for testing your file. You create a zip file containing those same files as in part 1 and submit that zip file for part 2 of the assignment. You can again run our grader. That grader is going to be in the basic graph package, and it's called graphgrader.java. So if you get anything wrong here and you can't figure it out, just run our grader, and that'll help you with your debugging. So that's about all you need to know. This was a rather more lengthy walkthrough than usual, but that's what you need to know, and good luck with this assignment.
Welcome to week 2. This week we're going to look at how to design classes in Java to represent graph structures for particular problems. And we're also going to be looking at some very core graph search algorithms.
In this video, we're going to go over the nice features that you're going to be able to add to this graphical user interface based on your project this week. So first off, how do you load this graphical user interface? To get to this, you'll go to Source, Application, Map App. You're going to run this class file, and that's going to produce the interface that you're seeing here. This interface is written in JavaFX, and it interfaces with the Google Maps API. Using the Google Maps API allows us to see this nice image of the map, as well as zoom in and zoom out. But we're not going to be using the intersection data that Google Maps has. We're going to be producing our own. So let me show you an example of this. So within this interface, you'll go under Choose Map File. You're going to pull up something like the UTC maps and pull Show Intersections. Now, this map file contains a whole bunch of intersections that we pulled from a region right next to UC San Diego. These intersections are what we're going to be able to explore in doing routing. So if I want to go from, say, this point as a start point to this point as an end point, I can now show a route with that using breadth first search. Now, none of these features that I just showed there, being able to show that route, will work until you finish this assignment. You're going to need to make sure that you've written your map graph class, created your hierarchy, and written a breadth first search before that search that I just did would work. So the second piece I want to show you is how you can pull data from an area around you rather than having to use the maps that we provided from around San Diego and around La Jolla. So if we zoom in on an area, say Pullman, Washington, which is where I grew up, and I can zoom in now. You don't want to try to fetch data from a large set of the world. If you try to pull all intersection data from the most zoomed out view, that file is going to be way too big. The application will definitely crash. But if you zoom into a small area, let's say I pull up this small little area of Pullman, Washington, and I would go over to fetch data and type in something like Pullman.map, and I'll press fetch data, and you'll get a pop-up window that looks like this that says fetching data for the current map. In just a few seconds, it'll report back that's found the data. Alright, it has finished pulling the data and now have a Pullman.map that's been written to the file. So if I want to pull up that Pullman.map, I'm going to have to do a couple of steps. So you'll notice if I try to search the map files right now, I can pull up Pullman. I can do show intersections, and we'll see all the data that just got pulled. So this is how you can do this for your region around you, so you can enjoy working with data perhaps a bit more. The next feature I'd like to show you, I'm going to go back to that UTC data that's around San Diego. So pulling back up those intersections, I'm going to again find a route. So let's say going from here as a start point to here as an end point. I'm going to use breadth first search because breadth first search is the piece that you're going to implement this week. You can do show route, and it'll show you the route from the start point to the destination. One nice feature, if you add the hooks that we discuss in the write-up about reporting to this application which nodes you're visiting as you do the search, you can then run start visualization. And what start visualization is going to do is it's going to explore them. It's going to show you the map as it's explored. It's going to show you all the nodes that's visiting and its attempt to try to find that path from the start to the goal. Now that's found the goal, it's stopped. Now this visualization piece is actually going to be much more interesting in next week for week 3. The last piece is that there are some really nice features in this interface, but it's not going to have all the features that you might expect from Google Maps. You're limited to being able to work with the intersection data that you pulled with. instead of being able to say zoom in and zoom out from a huge set of data at all times. Now, if you think about it, Google Maps was developed by a team of software engineers over a number of years, and they have a huge data center that supports all the map data that they have. On top of that, they've had a fleet of cars driving around the world getting this kind of map data for a long time. So it's unrealistic for us to expect that our application is going to look exactly like Google Maps or have all the features that Google Maps has. But being able to find a route from one location to another using your own data structures and your own searches is really cool. So I hope you have some fun with this project. Good luck.
All right, this week is all about class design. You saw what you're going to be doing in the project. You're going to be working with that road data to plan routes on a map. But this week, what you're going to be focusing on is just some very simple search and route planning algorithms. The focus of this week is really on how to take a problem like that, represent it as a graph, and then build some Java classes in order to represent that graph structure. Unlike in previous assignments in our previous courses, we're going to be giving you very little starter code. So this week's going to help you with the process of taking a problem that's well specified but not detailed in Java and writing it up as some Java classes. So by the end of this video, we're going to look at how to take a problem and turn it into a graph representation. And the problem we'll be looking at this week isn't exactly the same as you'll be working with in your project. It's a simple little map that a robot's going to navigate through in order to find some gold. So here it is. Here's the problem we'll be working with this week. We've got a little grid world, and in this little grid world, we've got a robot. And this robot's goal is to navigate the grid world in order to find the gold. And you can see there are some obstacles in this world, represented as walls, and the robot's not allowed to move through those walls. So it has to find a path through this little maze to the gold. And of course, this problem can be represented as a graph. Otherwise, I wouldn't be talking about it right now, because the focus of this whole course is all about graphs. So we're going to use this little example for 3 purposes. Again, this is not the same exact problem you'll be working with on your programming assignment, but it's similar. So we'll use it for 3 purposes. The first is that we will use it to look at how do we take a problem like this and represent it as a graph. It's going to be similar to how you take your problem of navigating street data and represent that as a graph. Second thing we're going to focus on is how do we do some very basic searching through this graph, through this world here, which we'll represent as a graph, in order to get the robot from its start position to the gold. And then the third reason we're going to look at this problem is the theme of the week, the overall theme of the week, which is how do we take a problem like this, which is a graph problem, and represent it as Java classes. So again, the reason we're not using the project directly is that I'm going to take this problem and really walk you through turning it into some Java code. And I don't want to give away the answers to how we would take the project problem and turn it into Java code. So what we're going to be doing this week, or this week, is going to be similar to, but not identical to, the class structures that you'll be developing for your project. So just a disclaimer, don't try to use the class structures we develop directly. Use the ideas of how we translate the problem into Java classes. So let's get started with that first task of taking this problem and representing it as a graph. So as you know from last week, a graph has 2 fundamental components to it. It has some vertices, or I like to call them nodes. You'll hear me call them nodes a lot. And it also has some edges. So in order to represent this problem as a graph, we need to define both of those pieces. Let's start with the vertices, or the nodes. The nodes in this graph are going to represent all of the places that the robot can be. So our robot's goal is to move around in this world until it reaches the gold. And so it makes sense to have the nodes be these individual cells where the robot is allowed to exist. So we'll go ahead and we'll put a node down in each cell in our little maze. So that takes care of our nodes. Next, we have to think about our edges. What should the edges in the graph be? Well, again, our focus is on movement, and we want to move this robot through the world from vertex to vertex, or node to node. So our edges in this case are going to define the legal hops that our robot can take. So what hops can the robot take? Well, in our world, our robot can only move up down, left, and right. And obviously it can't move through walls. In fact, the walls didn't even get nodes because they're not legal positions that the robot can exist. Those walls are completely blocked. So when we add our edges, we'll just add an edge for every direction the robot's allowed to move. And our graph is going to look like this. So we've just got one edge coming out of each node to an adjacent node that the robot can move to in one step. So there's our graph representation for this problem. And the next thing we're going to focus on is how do we take this graph representation and have the robot find a path from wherever it is to the goal.
Hi, I am Ankur. So one thing I had a very bad habit was to hard code everything that I did pretty much during my undergrad. So when I was in my first job, I had to put in production code and I started hard coding everything. And there was this problem about graph, and every node had like 5 properties. And I knew that the first index was something and the second index was that particular thing, but I didn't create any getters or setters for those properties, and I just hard-coded the array indexes for that particular node. And whoever was reading and reviewing my code, he was not able to understand what I've written. So the very thing I realized that hard coding would get us through the course content, but it might not be very practical while doing an industry level or a project.
Hi, my name is Huang. I know a lot of you are working on a mapping application right now, and most of you are writing the design from scratch. I worked on an internal tool for Google Maps when I was interning. My partners and I had to work on the GUI component for this application. When we first got the project, we were all kind of clueless about where to start, but our mentors suggested to look at design patterns. As you progress further in your software engineering career, you'll learn these awesome design patterns that are patterns that software engineers have seen over and over again in their designs. So you don't really have to start your design from scratch. Instead, take advantage of these existing design patterns. One of the patterns I've used heavily in my project is called the builder pattern. Normally, you have a lot of different parameters. You would need different constructors that takes in the combinations of these parameters. But the builder pattern helps you to simplify this process by eliminating the need of all these constructors. You can learn more if you want to by checking out the Wikipedia page. So, yeah, I know, design is hard, but it does get easier as you see more and more designs.
All right, now it's time to get the robot to the goal. In order to do that, we're going to look at some fundamental algorithms for searching graphs. So by the end of this video, you'll be able to perform an algorithm called depth-first search for searching a graph. You'll be able to implement that algorithm, and you'll also be able to describe how the abstract data type stack works, as well as how a stack is used in depth-first search. So let's go back to our graph representation. Here it is. And remember that our goal is to take a robot, which exists at some location in this world, and get it to the goal. Now, I've dropped the background with the walls and the grid and everything because we really don't need that anymore. Our task is fully defined by the graph that you see here. So how are we going to get the robot from where it starts to the goal? Well, in order to do that, we need to really search for a path from the robot's starting point to the goal. And we're going to look at 2 different ways to perform that search. The first is called depth-first search, and the second is called breadth-first search. We'll look at depth-first search first. Now, before we start looking at the search, I want to say that there's lots of different ways we can play around with this problem here. We're talking about a robot in a world. It might be the case that while the robot is searching, it's actually physically moving through the world. Or it might be the case that it has a copy of the map beforehand, and it's doing all of its planning before it starts moving. And which situation the robot is in is going to affect which algorithm it chooses to ultimately find its goal. We're not going to get into those details quite yet in this video, but you'll have the opportunity to explore some of those details a little bit later on in this course. So in order to search this graph, let's be a little bit more abstract. So I'll represent the robot's starting position with this vertex labeled X, or sorry, not X, S, and I'll represent the robot's goal position with that vertex labeled G for goal. And then just so I can have a little bit more concreteness, I'm going to give all these other vertices in the map letters so I can talk about them. Okay, so now we're ready to begin. And let me just show you how a depth-first search on this graph is going to work. So the robot starts at position S, and then what it's going to do is it's going to search all the way deep along a single path until it gets stuck or it reaches its goal. And only then will it decide to go in a different direction. And the way the robot is going to explore from any particular node, it has to be very methodical in its exploration, is it's first going to try to go up if that's a possibility. And if it's not, it's going to try to go left. And if that's not a possibility, it'll try to go down. And if that's not a possibility, only then will it try to go right. So let's look at how a depth-first search with that order of exploration will work. So a robot starts at position X, or S, and it goes up to position I. So now it's at position I. It's exploring from I. So it'll again try to go up. It can go up, it goes to H. It tries again to go up, it can go up, it goes to D. Now from D, it can look and see, well, I can't go up. There is no edge that will lead me up. So let me try going to the left. It tries to go left, and it can, and it reaches position C. It tries to go up, it can't, it goes left, position B. It tries to go up again, it can't, so it goes left, it goes to position A. And then from A, it says, well, let me try to go up, no edge up. Let me try to go left, no edge left. So what does it do? It goes down to E. Now it's sitting here exploring from E, and from E it's going to try to go up, and there is an edge up from E. So it's going to say, hey, maybe I should go to A. But should it go back to A? Well, no, because A's already been explored. We don't want to go back to A, because if we went back to A, we could get stuck in a loop going AE, 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 and that would be no good. We'd never get any closer to our goal. So we have to somehow keep track of the fact that we've already seen A, and we don't want to go back there. So if we do that, then the robot will notice, okay, I've already been to A, so let me try some other direction. Let me try going down, and sure enough, it goes down and it reaches the goal. So you'll notice that the robot really just tried to continue to pursue one path deeper and deeper and deeper until it got to the goal. So that's why this algorithm is called depth-first search, because it searches deep as possible. However, it's not always that simple. So let's modify the graph structure just slightly and try this search again. So we're still going to start at position S, and everything is going to start the same. So we're going to start searching up. We go to I, to H, to D, to C, to B, to A. But now we're at A, and the robot's kind of stuck. So my question for you is, following this depth-first mantra, what do you think is going to be the next unexplored node that gets explored using this algorithm? Okay, if you said F, then you were right. And look at how that happens. So right now the robot is all the way over there in A, exploring from A, but it's stuck. There's no place to go from A. So what it's going to do is it's going to backtrack. It's going to say, well, what about from B? Where could I have gone from B that I maybe didn't go? And from B, it's going to see, oh, I could have gone down. So let me try going down to F. Well, F is a dead end too. So at this point, it's going to do the same thing. It's going to backtrack. It's going to say, B, anywhere else I can go? Nope, not anywhere that I haven't been. So let me try C. Nope. D, nope. H, I, S. Aha! Now from S, I've got new possibilities. So it's going to go out from S to L, to K, to J, and ultimately reach its goal. So you can see the depth-first search did find the goal, but it went all the way to the end of that A and F path before it came back to S and started exploring down the path that would actually lead it towards its goal. So that's the nature of depth-first search. It's going to go all the way deep before it backtracks and tries to go in a different direction. So to end here, I want to talk about the implementation of depth-first search. So we've got a few questions here. First question is, how do we keep track of where to search next? Next question, how do we keep track of what's been visited so we don't repeat and go in circles? And the third question is, how do we keep track of the actual path, since ultimately we're trying to find a path from the start to the goal? So let's think about that first question first. How do we keep track of where to search next? How does the algorithm do that backtracking that we talked about? Turns out that this is really straightforward. We're going to use an abstract data type called a stack. And the idea behind a stack is it's just like say, a stack of books. And you can see a very precarious looking stack of books there. The idea is that in a stack, you're only allowed to put data in and take data out from one end. It's like a list, but we've only got access to a top, just like in that stack of books. If I try to take a book out from the middle, the whole thing is going to collapse. So I'm only allowed to put data on at the top, and I'm only allowed to take data out at the top, which means that the very last thing I put in is going to be the first thing I take out. And that's going to give us this depth-first behavior of the very last thing I was trying to explore from, well, that's what I'm going to go back to try to explore further if I reach a dead end. Next question is, how do we keep track of the nodes we've already seen? We need to do this in an efficient way. Well, a good data structure for that is a hash set. So a hash set built on some sort of hash table is a constant time collection of data where we can add, remove, and find elements in constant time. And if you were with us in our last course, we talked a lot about hash tables and hash sets in that course. Finally, how do we keep track of the path from the start to the goal? Well, that's just a matter of keeping track of when you discover a new node, where did you come from? So you can kind of backtrack your way along the path that you took to get to that node. So in order to do that, we'll keep a hash map, which has a link from each newly discovered node back to the node from which it was discovered. So putting all that together, we come to the algorithm for depth-first search, and here it is. So that first step there, we just initialize these three data structures that I talked about, the stack, the set of visited nodes, and the parent map. Then we will start our search by pushing S onto the stack. So a push is just a way of adding an element to the top of the stack. And we'll also mark S as visited by adding it to that visited set. Then we're just going to enter a loop that says as long as that stack isn't empty, as long as we've got somewhere else to go, let's start exploring. So we explore by popping the top node off of the stack. We'll call that cur. As long as cur isn't the goal, if we've reached the goal, then we should just stop. So if we haven't reached the goal, then what we're going to do is we're going to look at all of cur's neighbors. We're going to mark those all as having been visited now, because we don't need to go back to them. And then we'll put the neighbor into the parent map by putting cur as its parent, and then push that neighbor onto the stack, sort of like stacking it up for exploration should we get stuck exploring. And that's all. Then we go back to the top of the loop, and we've got a new current, which is one of the neighbors of the node that we were previously looking at. And that'll give us this depth-first exploration of this graph. Now, before we end, I just want to say one more thing, which is that this implementation of depth-first search uses an explicit data structure stack, an abstract data type stack in the code. So we're explicitly pushing and popping from this stack. But a lot of times you're going to see depth-first search implemented recursively. So here's the recursive implementation of that same algorithm. And what you can see in this implementation is there's no stack. Where did our stack go? And it turns out that the way recursion works is that there's a hidden stack down in your computer that is managing the recursion itself. So here's the recursive implementation of depth-first search. Don't worry, if you don't know recursion and this doesn't make sense to you, don't worry about it, but you will see this implementation of depth-first search quite a bit because it's very simple, it's very clean, and there's no need for us, the programmers, to maintain this stack variable because the computer will do that for us. So that's all for depth-first search. Up next, we're going to talk about a very different kind of feeling search algorithm called breadth-first search. All right, so to finish our exploration of basic graph search, we're going to look at another algorithm called breadth-first search. So by the end of this video, you'll be able to perform breadth-first search on a graph. You'll be able to implement the code for breadth-first search, describe how the ADT abstract data type queue works, and as well as how queues are used to do breadth-first search. So we looked at this algorithm, depth-first search, last video. And we saw that it would explore all the way to the end of one path before going back and exploring down a different path. And the way we made that happen was to use a stack to store where we've been and where we want to go back to explore next. So that was how depth-first search works, with this stack, just like the stack of books. But in this video, let's consider the question, what if we change just that data structure that we use to figure out where we've been and where we want to go next? So instead of using a stack, I want you to consider what if we used a data structure, an abstract data type called a queue? So the way a queue works is it's just like a line, say at a movie theater. You get in the back of the line and you come out of the front of the line. So in a queue, you're always going to add elements to the back and remove elements from the front. So we're working with two different sides of the list now, whereas in the stack, we are only working with one side of the list. And those operations, just to get some terminology, are called enqueue, that's adding an element to the back, and dequeue, that's taking an element out of the front. We're going to see that this very small change to this algorithm is really going to fundamentally change the behavior of how it searches a graph. So let's go ahead and make that change. So here's our algorithm. It's exactly the same pseudocode as I showed you before, only everywhere where I had stack, I've now changed that to say queue. So those parts in red just say queue instead of stack, or the appropriate queue operation, enqueue instead of push, dequeue instead of pop. And let's trace this code on the graph example to see how things are going to behave. So just like before, we initialize our visited set, we initialize our parent map, which I'm not showing here, and now we're going to initialize a queue abstract data type. So we put our start into the queue, and we mark start as visited. What do we do next? Well, now we're going to enter the loop, and we are going to take S off of the queue. That becomes our current node. That's the node we're currently exploring from. And we're going to explore its neighbors. We're going to go visit its neighbors. So we visit the neighbors. We visit I and L. And in visiting them, we do two things. We add them to the queue, and we put them in the visited set. So we mark them as visited. All right. And then we want to explore some more. So we look at the first node in the queue. The first node in the queue is I. So we take I and we explore from I. At this point, we again explore out from the neighbors. Its only neighbor right now is H that hasn't already been explored. If a neighbor's already been explored or visited, we won't put it back in the queue. So we go to H, we add H to the queue, and we mark H now as visited. And my question for you now is, looking at the state of the queue and where we are in our exploration, what node will be explored next? All right, if you said node L, you'd be right. Because remember, in our queue, we put H in the back, but the node we're going to take out next is in the front, and that node is L. So L is going to become our next current node. So what you can see now, you can start to see, is that instead of going deep down one path, we're going broad out. So we explored I, and now we're exploring L, and our search is going to color the graph in a very broad fashion instead of in a very deep fashion, like we saw with depth first search. So let's continue. We'll just walk through the rest of this algorithm, and you can see how it's going to explore outward, continue to explore outward in the graph. So we explore L. L's neighbor is K. We mark K as visited. We put K at the back of the queue. Next, we take H off the front of the queue and explore from H. H's neighbor is D. We put D at the rear of the queue, mark D as visited. Then we take K off the front of the queue. We explore from K. K's neighbor is J. Put J at the back of the queue, mark J as visited. We go back to D because that's now at the front of the queue. So we explore from D. We pick its neighbor C, put it into the queue, mark it as visited. We now go to J, and don't worry, we're almost done. We now go to J. We take J as our current node. We explore from J. We put G into the queue. Notice we haven't gotten to G yet. We know G is our goal node, but we haven't seen it really yet. We're just scheduling it to be explored by putting it on the back of the queue. So, and we're marking it as visited because we know we're going to get there. But we don't go to G next. We go back up to C because that's at the front of the queue. So we explore out from C, we take B, put it in the back of the queue, add it to the end of add it into our visited set, and only now do we get to go to G and find, aha, here we are at our goal. So as you notice in this example, this did a very different exploration behavior than depth first search, and it was just that subtle change of what abstract data type we used to keep track of the nodes that we needed to explore from. We're going to end by talking about one example, one way in which depth first search and breadth first search produce actually different results on the graph. They both can be used to explore a graph, but some things, some properties of them are going to be a little bit different. So one property is going to be that if we explore our graph, let's go back to that original graph that we could reach our goal by going over the top. And if we look at the path that depth first search found in this graph, we can see that it's fairly long. It goes over the top, but there was a shorter path that we could have found. And that's just because we got going on this original path that went up, and we ended up finding the goal, so we were good enough with that. But that path wasn't great. If you look at what breadth first search does, in fact, it finds the goal from this much shorter path across the bottom. So this is something that Leo is going to explore in much more detail next week when we start to really dig into these graph algorithms. But for now, we're going to switch gears and start talking about how to actually design Java classes for this graph problem.
So one of the big problems when working with real data is knowing whether or not your solution is correct. So there's a real temptation when you start working with a big data set, you start writing some code for it, you start writing the code, and of course everyone runs into bugs, so your code doesn't compile initially, or it might not run correctly, you might get a null pointer exception, but eventually your code is going to run. You're going to get an output from that. Is it right? Well, for you to figure out whether or not it's actually right or not, it's often best to come up with some small sample problems that you can work through on your own, and then test your code to make sure that your code actually comes up with the same answer, and then you can feel more confident about the code's correctness. So by the end of this video, I hope you recognize the value of small examples in testing your code. So let's think about this real data piece. So this is a map of San Diego. If you think about the graph data there's a lot of data, right, for all the roads that connect within the city of San Diego. And if I ran a search and this is Google Maps, if I ran a search within Google Maps and asked, what's my fastest route from UC San Diego to the San Diego Zoo, it's going to give me back this route. And I actually know San Diego pretty well, and this is actually probably the best route. But there is this real question, if you didn't know San Diego really well, how do you know that that's the shortest? Is this really the best route? Well, what you want to do is come up with some small sample cases. And what I have here is an example problem. This is a smaller map than your real data set's going to look like. And this is the one that's actually included in the project write-up. But when both Christine and I started this project, we both did the same thing in parallel, which was come up with small sample problems in order to try to check your own work. This is one of those sample problems. So with this sample problem, I can look at this problem and know properties of it because it's, again, small. So let's try to do just breadth first search on this. So I'm going to start at 1.1, and I'm going to go to 8.1. And what's my breadth first search going to give me? Well, what it should give me as a result is it should give me a path from 1.1 to 4.1 to 7.3 to 8-1. That's the fewest number of stops, which is what breadth first search will give you. Now that I know that for this simple problem, what I want to do then is have my code come up with the same answer for the same problem. And the first step to do that is to convert this graphical representation of it into data that we're going to be able to use. And this is actually within your project folder under a simple test.map. But before we get into the details of how to convert that, let me do a quick example of us actually running this to see how well the code works. So what we're going to do is we're actually just going to try to run this in our code. We're going to take the example that we already worked. We're going to pull in that graph into our code, and then we're going to actually execute our breadth first search to see if it comes up with the same answer as we'd expect. So diving into the code itself, I've written this class called map tester. And the first 5-6 lines of this is code that we provide you as part of the starter code to essentially create a map and pull in the initial data from a map file. So let's walk through those steps. So first, we're going to create a map using the map graph constructor. And then we've written this utility class called graph loader, which allows you to load in a road map just by providing that map file. And we'll talk about the structure of that map file in just a second. Now this class we have written for you to essentially do the parsing, but it is going to call your methods within map graph, which are going to build the map itself. And that's your responsibility as part of this project. After we pulled in this map, I'm going to do two things just to test to see whether or not my small set is actually loaded in properly. I'm going to print out the number of vertices, and then I'm going to print out the number of edges. And then I'm going to call in my solution code the breadth first search. And I'm going to feed it a starting point of 1.1 and a destination point of 8-1. And that's what we did in our simple example that we just worked through. And then what I'm hoping to see is once I've got that route, I'm going to print back out that route, and it should match what we did by hand. So let's try this. Let's run this. And first off, let's focus in on the number of nodes and the number of edges. So in our sample graph, there were actually 9 nodes, and that's exactly what it says here it got loaded. There were 11 undirected edges, which is really 22 directed edges. So that actually makes sense too. And then when I look for the breadth first search path that it finds me a path from 1, 1 to 4, 1 to 7, 3 to 8, -1. And this is exactly what we expect to find based on having worked through this example by hand. So let's go back and look at the structure of how we make these .map files so that you can create your own test cases yourself. All right, so what we saw by running our code on our example was that it actually produces the same result that we worked through by hand. So it found that same path from 1, 1 to 4, 1 to 7, 3 to 8, -1. And that's fantastic. So how do I take that graphical representation that I have here on the left and produce an example that I can actually work with my code? To do this, what you're going to do is create a file just like this, where the format is very particular. Make sure you follow this format exactly. You're going to have a start lat long, followed by an ending lat long, followed by a street name, and followed by a street type. And that is how you denote an edge. And that's an edge between the starting location and the end location. And it's directional. So if you want to have an undirected edge from 1, 1 to 4, 1, you'd actually have to reverse it to have it both be the start and the end, and then reverse the end to now be the start. So you do 1, 1 to 4, 1, and then 4, 1 to 1, 1. And this is how you are going to express these edges when you make these examples. Now, I strongly encourage you to try to do one of these examples on your own. So come up with an example on your own, do the graph by hand, and then convert it into this kind of file and pull it into your own data set. And this is useful for a couple of reasons. The first is, again, it's a great way to test to make sure your code is actually producing the right result. And the second reason it's great is it's an incredible morale booster. It's really satisfying when you work through something by hand and you see your code find the exact same right solution. So again, I hope you do this on your own.
So when I first started taking computer science classes, my introductory class uses a lot of pictures and sounds so I can manipulate the pixels and the little sound segments. But then when I started taking data structure classes, all these things are gone. So they're called abstract data structures, and I was like, abstract, how do I picture these data structures? And it was not until in class my instructor showed us some pictures that I understand what a stack and a queue is. I mean, when you hear stack and queue, they're just names. They don't mean anything or at least to me. But the picture that the instructor showed in class was a stack of plates and a line of people waiting in line. So that's really explains what a queue and stack is, and then he helped me memorize, oh, a queue is first in, first out, and a stack is last in, first out.
So in one of my CS classes, there was this time where we had to do breadth first search. And so I tried to just dive straight into the problem of implementing that. I quickly realized that if I just tried to use the data structures that I tried to use were like linked lists or just trying to configure the nodes after I reached different cases. And what ended up was my function for breadth first search just kept on getting edge case after edge case after edge case. And so I finally went into the resources for the class, and one of the top documents, one of the first FAQ questions was, how do I implement breadth first search? And the answer was just one sentence. It said, implement a queue. And after I saw that sentence, I realized, all this time had been wasted because the answer had been there. Somebody had already solved this problem. And the solution was actually a really good one because it was short, it was concise, and it was really easy to implement. I didn't need all the edge cases that I had actually programmed already. So I guess the take-home message was that if you really use and you really know the data structures that are good for the actual searches that you need, then it'll save you a lot of time and a lot of trouble.
All right, now that we've talked about depth first search and breadth first search, we're ready to probe our understanding of these concepts with a concept challenge. And so as you might remember with these concept challenge, we invite you to pause and try to solve a problem yourself, then discuss with other learners around you if you can. Watch the UC San Diego learners discuss the same problem, try the question again, perhaps with a little bit more confidence, and then confirm your understanding as we come back together and explain some of the key concepts involved. So for this problem, what we'd like to do is think about comparing these two algorithms we have for graph search, namely depth first search and breadth first search. And as you remember from the core videos that Christine presented, these algorithms as pseudocode are very, very similar, but what's really distinguishing them in terms of just the code is the basic data structure that we use in order to keep track of what we've visited and what we still need to do. But what we'll see is how this impacts performance. And so the question I invite you to think about is which algorithm, depth first search, breadth first search, is asymptotically faster in the worst case. And so when you're answering this question, think about the asymptotic notation that we've talked about in the previous courses with big O analysis.
Hi, I am Ankur.
Hi, I'm Kevin.
Hi, I'm Annie.
I think depth first search would be better because let's say there's a graph and it's very deep, but it's not broad enough. So if I have to find the path from the root to a node at the very end, then I can directly reach via depth first search. So I think depth first search would be faster.
Okay, but what about breadth first search, in which there's a lot of nodes and they're really spread out? Wouldn't breadth first search be faster in that scenario?
Well, I think just looking at the code for breadth first search and depth first search, it all looks pretty similar. I mean, it looks like the only difference is that depth first search uses a stack data structure and breadth first search uses a queue. And like, I guess from what you're saying, it just depends on what the worst case actually is, right? So what is the worst case?
So let's say the two nodes are not connected and we are trying to find a path, and then I think that would be the worst case.
Yeah, so in such case, it looks like since we'd have to visit every single node that's unvisited in the graph, then wouldn't it be very similar in terms of runtime?
Yeah, so
I agree.
All right, now let's think through this question together. Let's think about, in particular, what the worst case analysis should look like. And so we have to think about what our algorithm will do in the very worst case. So worst case is when we have to do the most work, and we can think about starting and then we have to visit more and more and more of nodes, and we'd like to get to the goal. And when will that happen in the worst case? Well, it's when we've explored everything else that was possible, and we've gone through all the dead ends that we had, and we still need to keep on going further until we get to the goal. And so if we think about how many nodes we have to visit until we get to the goal, in the worst case, we're going to have to visit every single one of the nodes before we get to the goal. And so the number of nodes that each one of these algorithms will visit will be size of the vertex set minus 1, which is order the size of the vertex set. Now, is that it? Is that just the runtime that we have to think about? And when we think back to the algorithm, in either case, we definitely do something for every node that we visit, but we also, as part of our algorithm, have to keep track of the edges that are possible to us from that particular node that we're visiting or that we're exploring at that particular moment. And so what we end up doing is doing some work for each of the current node's unvisited neighbors, which means going through all possible edges. And so not only do we have to think about which nodes are visited, we also have to think about which edges are traversed by this algorithm. And in the worst case, we traverse every single one of them. And so taking that, the fact that we have to do some constant amount of work for traversing each edge in the graph, we see that our runtime will have a contribution that corresponds to O of the number of edges in the graph as well. And so putting that together, the worst case runtime for both depth first search and breadth first search is going to be O of the number of vertices plus the number of edges. Now, you might stop there and say, well, hold on a second, I know my asymptotics. And I know that if the number of edges is like square of the number of vertices, that's going to be the dominant term. The number of edges might be the dominant term. And I could just drop the number of vertices and say, worst case running time is just O of the number of edges. It's useful to us in our analysis of an algorithm to keep apart this notion of the number of vertices, the number of edges, how they impact performance. And that way we can tune our analysis to the actual graphs that we're working with. So for example, in the graph that you're working with for the project, you might notice that the number of edges that we have isn't anywhere near quadratic in the number of vertices. It's really linear in the number of vertices. And so in that situation, the performance that we have for depth first search and breadth first search is really going to be linear in the size of the graph rather than quadratic.
All right, so now that we've seen a graph representation for the maze world, let's actually turn that into some Java classes. So last week, Mia talked to you about two core representations we can use for a graph, adjacency lists and adjacency matrices, and she showed you Java code for each. But it turns out that when you actually go to represent a real-world problem with a graph, and we want to get beyond representing just integers as the vertex values, things get a little bit more complicated. So even if you understood everything that Mia did last week, this week's assignment of implementing your own graph classes will still likely be pretty challenging. So the goal of this video is to walk you through an example of taking a problem and turning it into some Java implementation of this graph and these graph algorithms. All right, so again, we're working with a problem that's slightly different from the problem you'll be working with on your assignment this week. On your assignment this week, you'll be looking at cities and roads and intersections and connecting them, and then finding paths, which would be essentially driving directions from one point in the world to another. Here we're just talking about a very constrained problem, which is this little two-dimensional grid world where the robot is trying to get from one place to the goal, the gold in this case. And our goal of this video is to turn this problem into Java classes so that we can solve it. So in doing your class design, when you start with kind of a blank slate and a problem to solve, there are some questions that you consider that can help you plan your classes and what classes you're going to need and what methods and data each of those classes should have. So you want to start by thinking about, what am I trying to do with this graph? What is the goal here of this graph representation? Another important question to consider is, what is the ratio of graph vertices to edges? That can help you decide between an adjacency list representation and an adjacency matrix representation. Another question to consider is, how do I need to access the vertices in my graph? What is the user going to be using in order to access the different nodes in the graph? We need to be able to do those operations fast. And then finally, a question you might want to think about is, what properties, if any, about nodes and edges do I need to store in my graph? So let's look at that first question. What am I really trying to do with this graph? Well, we know that we're trying to find paths through the graph. And in particular, here's the output of the program that I'm trying to write. I want to be able to print out the maze. So there's the maze. The horizontal dashes are empty spaces. They're the nodes in the graph. And then the stars are the walls. Those are the nodes that don't actually appear in the grid at all. They're not in my graph. And then I want to be able to do depth first search and print out the path that was found using those little O's. And then I want to be able to do breadth first search and print out the path that breadth first search found, again, using those little O's. So that's my goal. So I'll definitely need a class to represent the whole graph, the maze itself. And I know now what methods, or at least some of the methods I'm going to need to put into that class. I'll need a method to do depth first search, a method to do breadth first search, and a method to somehow print out the graph. Now these aren't the only methods that I'm going to need, but they'll give me a starting point to think about, what do I need to put into this graph? So the next question becomes, what data do I need to store in this class? Well, obviously I need to store some representation of the vertices and the edges in this graph. So that's our next question to consider. Should I use an adjacency list representation or an adjacency matrix representation? Which is better for this particular graph and this particular problem? So take a minute to think about which representation is better here. All right, hopefully you determined that an adjacency list representation is much better for this problem because we've got a very sparse graph. Each node in our graph is going to have at most 4 edges going out of it. And that's an extremely small number relative to the size that this graph could potentially be. So adjacency lists are going to make the most sense. So the next question becomes, how? How do I put that adjacency list representation into my maze class? So one thing that we might think about doing is, Mia was using just numbers to represent each vertex in the graph, but we're probably going to need a little more information for this problem here. So instead of just using a number to represent each node, because it's not even clear how we would number the nodes in this case, I'm going to create a class that represents each node. And my class now is capable of storing some information about each node, like its row and its column in the grid, and perhaps the display character that it's going to print out when we do that printing of the graph with the path. And then I'll have some getters and setters for that, for those internal variables. Now, how am I going to store those nodes in my maze class such that I get both the nodes stored away as well as some information about the edges? Well, we could just take that example that Mia used and extend it so that instead of a hash map linking integers to lists of integers, I'll have a hash map linking maze nodes to lists of maze nodes. So each maze node is going to go in as a key, and then the list that's associated with it in the hash map is the list of all of its neighbors, and that will represent the edges. So this is good, this is fine. We can definitely use this implementation. There's just one problem, which is that if we think about how we're trying to access these nodes, we're trying to call depth first and breadth first search, giving a start position and a goal position. But unfortunately, the user of these methods is not going to know what maze node the start position is. They're going to be representing a start position in terms of the row and column where the robot's supposed to start, and the goal as well in terms of the row and column. So somehow we need to get from a row column representation to the node representation so that we can start doing our search through the graph. So we need quick access to translate a row and column into a node. And this hash set really isn't going to do that, because in order to do this, we'd have to essentially iterate through all the keys in the hash set or the hash map and look at each particular node to see if it matched the row and the column. That's going to take order n, where n is the number of nodes in our graph. That's not really a good thing. We'd rather do this in constant time. So instead of using this hash map to store the nodes, what I'm going to do instead is use a two-dimensional array to store these nodes. So now I can have instant access to anywhere in the grid. And if that position doesn't have a node, then I'll just store null in that two-dimensional array. So the key point here is that we want to make common operations that we know are going to happen fast. But at the same time, we don't need to go overboard here. So do this within reason, consider which operations are really important, and try to make those fast. All right, so we can represent the nodes in this way, but now we've lost the edges, right? That hash map representation before was implicitly encoding the edges. We don't have that anymore. So the question becomes, where should I put them back? Well, I could put them back here into the maze class, just where I lost them before. But there's another place I could put them. Since I'm representing each node as an object, I can put them over here in the maze node class. Which is better? Well, not really one or the other. It's really up to you. This is just a sort of judgment call on your part. Which do you like better? That's a deciding decision you can make. So the decision I made is to put them over here in the maze node class. So each maze node is going to store a list of its neighbors, and you'll be able to access the nodes that are connected to a particular node from the node class itself, the maze node class. All right, so that's really all there is to our class design. And now we've also got a whole bunch of other methods that help load the data from a file, that actually do the breadth first and depth first search, that do the printing, so on and so forth. So we really want you to go check out our code. We've provided you all the code that we've done. This will be a good example for you to follow. It has some parallels to what you're going to be doing in your assignment this week. And what are you going to look for when you're looking at this code? Well, you want to look for things like, do the objects make sense? Do they kind of all hang together? Are the interfaces clean? Are we not exposing private data or data structures that we shouldn't be? Is it easy and fast to do the operations that you need to do a lot? And are methods short and relatively easy to read? And I will tell you now, I'll foreshadow the next video, not all of these criteria are perfectly satisfied. There's some room for improvement in our code as it stands. So in the next video, we're going to critique this code and make some improvements.
So I want to share a story about when I struggled when I was in college. So early on when I got programming assignments, in my first few courses, I could always solve the assignments essentially by thinking it through in my head and then just sitting down and coding it. And most of the time it worked pretty well. But as the projects get bigger, I kept trying to solve it in my head and then started coding. And my time coding versus debugging started to shift. So it used to be lots of time coding, a little bit of time debugging. And over time, it started becoming a little bit of time coding, tons of time debugging. I found problem after problem. I actually got really lucky. Around my junior year, I took a plane flight home just to visit my family. And back then, laptops weren't that common. I didn't have a smartphone. I didn't have a tablet. And I had this big programming assignment that I was supposed to solve for my classes. And I sat there on an old yellow legal pad, sketching out sample problems and actually coding up an algorithm for solving it. And then shortly thereafter, I went into my lab to actually do the programming of it. And I coded it up. And it didn't take that long. It was actually a really interesting experience because I went in there about the same time all my friends went in, and I coded it up and I debugged it, and I was out of there in about 4 hours. And I found out that my friends were in there for about 12 hours that day, and they kept struggling with it. And I figured out the key piece was that I had to think it through really carefully before I ever started coding it. And it seems really obvious now, but it's an essential step in trying to solve program projects.
So one thing that I have and still do struggle with is when I have a really great idea for a program that I want to run, and I know exactly the algorithm, and I know the data that I'm going to use, and I know what I want the output to look like. And then I sit at my computer and I have to start, and I have a blank screen in front of me, and I need to start those first Java files. And then I decide, okay, now I'm not going to sit at my computer. First, I'm going to plan. And I'm going to plan my classes. I'm going to decide what methods I need. I'm going to decide what fields to have and what the relationships will be. And then I keep planning. And I keep planning. And I never get around to actually writing the code because I get so caught up in what the beautiful structure is going to be in that code and how to optimize everything. And really, I just need to do a simple task, and I need to get myself to sit down and start coding. And so my strategy is to learn and remind myself to be okay with a good design, and it doesn't always have to be the best design. And remember to optimize for the amount of time I want to spend planning versus doing, and think about those trade-offs as I go.
When you're designing a project, you're walking a balancing act. You have to deal with, on the one hand, being worried about putting so much time into trying to come up with the perfect design that you never get anything done. And you need to ship code sooner or later. On the other hand, you want to make sure that you've got enough time in your design that it will support extensibility, it's open to changes, so that you haven't boxed yourself in where you have, this is an excellent design for exactly this. Oh wait, you need it in the color blue instead of red? Well, now we have to throw everything out and start over again. So, silly example, but that's the kind of balance that we have to follow. We need to make sure that we don't code ourselves into a corner, but we don't spend all of our time designing this perfectly open thing that will handle everything for everyone, because that's impossible. One example of where I've had to deal with this in the past was in a project that I worked on where we were writing a control system for some custom hardware. And we had to go ahead and plan for, this is the function that was going to be executed, here was how we were going to interact with the hardware, no problem. What we wound up doing at that time was we put a little extra work into the design so that we had what's called a hardware abstraction layer. The idea that rather than talking to the hardware directly, we'd have a set of classes that were abstract classes and then concrete classes derived from them that actually did the talking to the hardware. The rest of the system was all written in terms of the abstract types, with the actual hardware instantiation being done just once at the beginning of the program, and then everything else used those base classes. The original plan I called for the hardware to be available 4 weeks into the project, at least prototype hardware. Wound up not being available until 6 weeks before the end of the project. By putting that original time into the initial design, this meant that our design was open enough that we could go ahead and write simulated versions of the hardware abstraction layer objects. So here is this sensor, here is this motor controller, and so on. And write code that would simulate their presence rather than having to depend upon the actual hardware being there for us to talk to. We got most of the code written using those simulations. And then when the real hardware came online, what we had to do is write just the actual implementation, or at that point it was written, we had to test the actual implementation using unit test drivers to make sure that that looked okay, and then change the main program to, instead of creating our simulator objects, to create the real objects. Plug them into the framework that expected only the base classes and didn't care what the real types were, and go from there. Then it was just a question of iterating over, change the, make sure everything works. Where there were differences in the real hardware versus the simulation, fix it and move on. We did make sure we fixed the simulations as well to match the hardware. This came back again later on, a year and a half later, where our customers came back to us and said, well, this is great. We've got a whole new version of hardware now that we want the same software to run on. What this meant was that it was easy for us to extend it to deal with that. All we had to do was write one new hardware abstraction layer. The new hardware was radically different than the old one, but in terms of the functionality it provided, it was much the same, and so we could just write these tiny little classes that talked directly to the hardware, but presented as the same interface that we had before, and then change the main program so that when it was targeting hardware A, we used these classes to talk to the real hardware, and pass them up as instances of the base. When we were building for the new hardware, we created these objects as the things that would talk to the real hardware and pass them off to the rest of the system as instances of the base. And so we'd walked that tightrope. We had something that we could extend and reuse, and gave us flexibility for testing and others, and original development and other stuff like that. But at the same time, we were able to ship the code. So, woo, big win.
All right, so now we're going to talk about another really important aspect of class design and basically code design, which is refactoring and redesigning, because you're never going to get everything perfect the first time. So it's very important to know when you should take a step back, look at your code, and redesign it so that it's better. And I'm going to look at how I'm going to do this to my own code in this video. So by the end of this video, you'll be able to explain the concepts of refactoring and redesigning. You'll be able to critique aspects of my code design and of other people's code design, and hopefully your own. And you'll also be able to redesign and refactor code to improve the design. So we left you last time, in the end of the last video, with this class design. We had a maze class and we had a maze node class, and we were going to represent the graph as an adjacency list where we stored the nodes in a two-dimensional array inside the maze class, and then the lists would hang off of the nodes themselves. Okay, and we gave you some code and told you to check it out and prompted you to look for these aspects of good code design. And I told you too that not everything was totally perfectly designed. So let's look at a couple places where the design really could have been better, and let's look at fixes for that. So the first thing that may have jumped out at you is that one of the criteria were that our methods should be short and relatively easy to read and understand. And if you look at depth-first search, which I'm showing you here, don't worry if you can't read that code, that's the point. It's really pretty long. And that's not good. We really want our methods to be shorter than this. This is kind of very extreme on the length of what a method should be. So we want to fix this problem. So what's the solution? We're going to jump over into the code, we're going to look at what this method is doing and figure out how we can break it apart so that it's shorter and broken down into subroutines, submethods that do more specific tasks. All right, so now let's jump right over into the code, and I'll show you the code here. Here's our depth-first search, and if you scroll down, you can see again that, yes, this method is very, very long. However, I've added some comments that'll help us understand what exactly this method is doing. So if you look at this first line right here, I say that the first step we have in our depth-first search is really to initialize everything we need in order to do this depth-first search. So that's our first step here. We initialize everything. And it's not until way down here when we actually start doing the search. So all this stuff up here is just basically initialization and some error checking to make sure we have a start and a goal to actually go to. And so the search part takes up a good long ways. And then ultimately at the end, we're going to reconstruct the path. So that indicates that we've got three sort of very different tasks all lumped together inside this method. So that's a good indication that I can pull this method apart into helper methods that do these more specialized tasks. So let's start with this first piece first. I'm going to leave the initialization code in the DFS method itself, but I'm going to look down here and say, well, I think what I want to do is I want to pull the search code out into its own method. So let's go ahead and think about what that method might do. So let me jump down here below depth first search, or DFS, and I'll write a new method, and this is going to be a private method because it's really not intended for anyone on the outside to call. It's just going to be used in my own method here. So I'm going to say private, and I'm going to make this a Boolean method, and I'll call it DFS search. And what it's going to take is it's going to take a start node, and a goal node. And then it's also going to take that parent map, because remember, part of the task of depth first search is to recover the path that we want from the start to the goal. And in order to do that, we need to keep track of the parents where we discover nodes from as the search proceeds. So I will pass in the hash map, and I'm actually going to go up here and copy and paste. So let me pass in as a parameter this parent map. Okay, and that gets a little long, so let me get this on the next line down. Oops. All right, so there's my method header. And let me tell you about what this method is going to do. This method is going to, it's giving me an error because I haven't returned anything yet, so let me just make it happy. Return false. What this method is going to do is it's going to do the actual depth first search. It's going to return whether or not the search was successful. And as a side effect, it's going to fill in that hash map, which is the parent map. So that after this method is over, we'll have all the parents stored in that parent map, and we'll also have the information about whether or not the search was successful. Now, fortunately, most of the code, in fact, all of the code I need to do this process is already written. So I can just go up here, and in fact, I can just copy all of this stuff here all the way down to there. I can cut it out of there, and I can go ahead and put it down here. All right, so now I've got my, my parent map comes in as a parameter. I do my depth first search, my depth first search, and then at the very end, I already have this variable called found. I'll just return it. Okay, so now my method is written. That's really all I need to do because it's just doing what it was doing before. And let's go call it. So instead of having all that code here, all I need to do is call the code here. I still made my Boolean, found equals DFS search, and I'll be going from start to goal, and then passing in the parent map that I created already. All right. So that's great. I've already made my method a lot shorter by taking that conceptual piece and breaking it out into its own method. Let's do the same exact thing for this piece down here. So I've got this code here that I say reconstructs the path. And there's no need for me to have this in the main DFS method. I can do this in another helper method. So let me make another helper method. It's going to be private. It's going to return a list of maze nodes. And it's going to be called construct path. So what does it need to take in? Well, it needs to take in the start again. It needs to take in the goal. And it needs to take in that parent map, because the parent map is really what is going to allow us to reconstruct the path. If we don't have the parent map, we can't get from the goal back to the start. So again, let me copy that that header here because it's kind of cumbersome to type. All right. And again, I already have all of the code that implements this method already written. So let me just go up here and copy it out. In fact, let me just take all of it. There we go. And now I just need to call it. And in fact, this is what's going to be returned by the method. So I'll just go ahead and return what gets returned from this method call. So return construct path, and let's see. So we want to pass in start, goal, and parent map. Okay, so we're done. And we've refactored our code. And if you look up here at our depth first search method now, it is much, much shorter and cleaner. And so it's just much nicer all around. All right, so that's the idea behind refactoring. We've taken our code that was very long and not very well designed, and we've broken it up into methods that have a clear conceptual purpose to make everything much easier to read and understand. Moreover, we've got an added bonus. This construct path method that we wrote, that's actually going to come in very useful for breadth first search as well. So instead of having to repeat code, we can just call that method again. So that's an example of refactoring, where we've changed the structure of the code without changing the interface to the code at all, without changing its overall external functionality. But let's take another look at a way this code could be improved. And this is through looking at whether the interfaces are clean. So do we have clean interfaces that don't expose private data or data structures? And are they clean and not very cumbersome? Well, if we look at the actual header to breadth first search or depth first search, they both basically look the same, we can see that, well, things aren't maybe as clean as they could be. For starters, we have the user pass in a starting row and column and an ending row and column as 4 separate integers. Maybe that's okay. Maybe there's a better way to do it. But the real problem comes is that what we're returning. We're returning a list of maze nodes. But maze nodes are really internal objects. They're internal structures that we're using in our graph representation. They're not designed to be returned to an external user, especially because this method is public. So anybody could be calling this method, and they might not know what to do with a maze node. Why should they care about a maze node? What they want are the coordinates of the path. So instead of using the start node or start row, and start call, end call, as well as returning this maze node, what I'm going to do is I'm going to create a new class. And this class is going to be called coordinate. A coordinate is just going to store a row and a column in a single object. And this is going to make my code much cleaner because I can replace all those clunky bits there with just objects of type coordinate. This makes everything much nicer. So I would go back and I would redo my code, replacing everywhere I had 2 different integers with this coordinate object and replacing exposures of maze nodes with lists of coordinates instead. This is a slightly more significant change. It's also not quite a refactor because we're actually changing the interface, the external interface to our code. So it's more of a code redesign. And this is really good to do when you're in development. It's more difficult to do after you've released your code. So you want to get all these redesigns done when you're in the process of development. All right, so when you're doing your own design, these are the things to keep in mind. Keep these thoughts in mind when you're doing your own design as well as when you're reviewing your peers' design. And the message that I want to leave you with is, don't be afraid to redesign and refactor as you go. You're very encouraged to do this. In fact, it's a mistake not to do it. A common scenario when people are coding is you're writing some code and you're like, this isn't so great, the design's not so good, but oh, I'm almost done. Let me just keep going, push through. And 6 hours later, you've done acrobatics to try to make your code work and it's still not working. And at that point, you slap yourself in the head and say, I should have just redesigned in the first place. That hour of investment would have saved me 6 hours of frustration. So redesign and refactor as you go. It's totally expected. Every professional software engineer does this. So we expect you will too.
So in this support video, what we're going to be doing is actually looking at the class hierarchy that you're going to be doing for your project. Now, I first of all want to say that this is a major spoiler. So I encourage you to do this on your own first, or at least try to do this on your own first before you watch this video. But if you want some extra help or you just want some tips to get started, feel free to keep watching. The other thing I want to mention before we get started is that this is actually a fairly authentic environment. So whenever I'm trying to do a major project, I always do this at my whiteboard. And my whiteboard is going to look very much like what we're about to do here by the end. Now, I also want to be quite honest about what my whiteboard looks like. my whiteboard ends up messy at various points in time. You almost always have a really clean idea of what you're going to do when you start sketching it out, and then you make mistakes. Or you don't necessarily make a mistake, but you are working in the code and you go, oh shoot, I need access to this from here, but I don't, and how am I going to get access to it? And whenever that happens, you end up changing around your class hierarchy. That kind of refactoring is completely normal and is completely okay. At various points in time, you may end up having to clean things up a bit, but it's completely okay to change your code. All right, so without further ado, let's start diving into how would you lay out your class hierarchy for the project in this in this week. So you have a map graph class that's provided to you. You know the methods that you need to write there. And all we're going to do is essentially sketch what should be in this class and what might be in other classes. And now there might be a temptation really early on, which is to essentially put all of the information you want to know in this class. And the way that you might do that is you might say, okay, well, I could keep, say, a list of all the vertices. And then for each of the vertices, I could keep another list which maintains the other vertices that they're connected to. Now, I'm not even going to sketch that out because pretty quickly you're going to recognize, if you take this approach, that it's unmanageable. There's way too much complexity being put in the map graph class, and you need to move this into other classes. And again, that's the main principle of object-oriented programming. So what should we keep? Well, it would make a lot of sense to have nodes or vertices in my graphs potentially have their own class. And then instead of trying to keep that list of vertices and then some other list of things that are connected to it, we might be able to put that all within, say, a vertex class. So let me do that. What we're going to do then is add a new class called a map node. And the map node class is going to contain a few things. It's going to contain the location of the node. And this might be a geographic point in the hierarchy that we've given you. And then you might also want to maintain other features about it. Now, if we're doing an adjacency list representation, what you'd be really tempted to do is to say, well, I should keep a list of more map nodes. So list of map nodes, and these are essentially my adjacency nodes. Now, you might keep a list like that, and then what's going to happen pretty quickly is you're going to say, well, is it enough for me to know all the other nodes that are adjacent to me? I know that's how we sketched it out in week 1, but is all the information about an edge contained just in the start and the end? Well, not really, right? What you'd have almost certainly is essentially the names of the streets are missing, right? At the very least, you're missing names of streets. So what you do then is say, well, maybe I should maintain a list then that I'll keep in parallel with the adjacency list of the street names. And it could be a string for street names. And the problem there is going to be maintaining the consistency between these, but let's just say we could do it. And again, kind of at a high level, what this might look like is, say you had a node, your node is A at location A, and you're connected to B and C. Well, I'd have to maintain the street names for B and C, and maybe that's Main and Park. And I have to make sure that B is always associated with Main, and the path to C is always associated with Park. And then I go one more step, and I go, that isn't everything I need to know, right? The edge is not always a straight path from one location to another. We actually need to know how long it is. How long is that path on a real road? So now I'd have to maintain another list of double distances, double lengths, which are essentially how long are these. So now I go, okay, well, my distance from A to B on Main Street was 3.2 kilometers, and my distance from A to C via Park Avenue is 6.7. And you could actually make this all work this way. You could have these essentially parallel arrays that you maintain consistency between. But what's going to go wrong here is the second you try to insert something, or you try to move something, or try to remove something, you're going to make mistakes. It's really going to be easy to lose the consistency between these. So even though this looks like a good idea when I first started sketching it out, this is actually going to be a mistake. And I'm going to cross this out, and I'm going to start again thinking about this in a more object-oriented way. I'll be right back. All right, so what I've done is I've taken away that essentially wrong direction that I'd done. So we'd again tried to have our distances, and we tried to have our vertices and all these things in different parallel arrays, when really we could put them all in one other class, right? I could just make a class called an edge that would maintain all these pieces. So let's just do that. So let's make a new class called map_edge. And within the map_edge class, now I'm going to contain all those pieces that we just talked about. I'm going to contain a location for the start. I'm going to maintain a location for the end. I'm going to maintain the name of the street. So this would just be a string, street name. I'm going to maintain potentially the street type. I could also maintain the distance, just like we just talked about. Distance or length. And now I've encapsulated all these pieces all within the map_edge. Now I can hook this all back together. So a map node, so let me draw some boxes around these. So a map node is going to have a list of edges connected to it. So now I just do a list of map edges. And I could call these neighbors or edges or some whatever variable name works for us. And that would then point to a list of these objects. So for each of the edges that I have, I'd have a different map edge. So for example here, if my location were again A, one of the map edges it would have would be B with the street name of Maine and a distance of whatever value we want to put there. And likewise, I'd also have in this list another edge which contains the edge from A to C that uses Park Street and some other distance. So it's a nice way of encapsulating this, and I can have this be the other class. And now the last piece I have to do is again relate this back to how my map graph is actually going to contain this. And then my map graph is going to just have a list of these map nodes. So now I can just do list map nodes. And I could call this my vertices or nodes. So I have some choices here. And then in terms of how I might lay this out, I could just have my vertices, but it actually might be useful to have my edges. But we'll talk about that in just a second. So my usual general use will be go to my list here, look up my node that I'm looking for right now. And now with a list, you're going to say, well, wait a second. If you're doing a lookup on a list, maybe you shouldn't have done a list, right? Lookup on a list, if I'm looking for a certain vertex, it's going to be O of n. I could just rearrange this to be pretty quickly a hash map, right? Do a hash map and have it be a vertex or a location and a map node. And now that will be my vertices. So I can get rid of these. Now I can do an efficient lookup. So now we do an efficient lookup of a location in my hash map. That tells me the one I'm looking for, say A. And then I can essentially traverse the graph from there. I can go to A to say, well, who are your neighbors? Well, I've got a list of edges. My edges tell me that I have neighbors B and C. And we could just continue traversing this way. So there are a number of different ways to solve this project. You don't have to use the classes that I've described here. But this is the way that we went about solving it. And it actually worked fairly cleanly for us. We added one other piece, and that was that we actually kept track of the edges here, essentially just for a quick lookup and in case we want it for debugging purposes. But you don't necessarily have to have that there. All right, I hope this helps. Good luck in your project.
Refactoring code is a really common part of software development. Software design practices evolve, tools for instrumenting and debugging code change, and most importantly, the use cases for a code base will evolve over time. So code written without extensibility, testability, and maintainability in mind often needs to be refactored. My team has a component that is both server-side and component-side, and over the past year, we've been refactoring both of those. For the server side, the legacy code base was really old. It was written by someone who was no longer on the team. In fact, the team had turned over a couple times. It wasn't well commented, so it was really hard to understand what was going on in the code and how it worked. And so we couldn't really add new features or really even debug any issues because it was so hard to understand. We refactored it to be modular, to have better logging, and to have a more extensible architecture. The application performed several functions, and so throughout the course of last year, we replaced each one of those functions with new code. The advantage of replacing one function at a time is that it allowed us to validate the new design with real traffic in production and have limited scope to debug and troubleshoot any sort of issues we ran into. If we had rewritten the whole application in one big bang and found there were performance issues or a lot of bugs, it would have been really hard for us to troubleshoot. We've also been refactoring our client code to increase testability. Our original code was written without test coverage in mind, so we've taken on an initiative to increase our test coverage to a very high level. In order to do this, many of the classes actually need to be rewritten or refactored because they weren't written with testability in mind, and so there aren't hooks for us to actually wrap unit tests around the classes. I think this is a really common practice that people want to launch software really quickly, and as a result, you take a penalty, you incur this technical debt. So you have to really think about that when you're trying to launch software and balance long-term maintainability with the software with time to market. It's a natural human tendency to prefer our own coding style to other people's. We have to be really careful not to refactor just because of the not invented here syndrome. Just because the code doesn't look like the code you would have written, that's not a very good reason to refactor. Instead, we only refactor when we have something that is going to be a tangible benefit or a tangible positive impact to our users. So we often refactor when we need to be able to add more features, when we want to be able to resolve issues more quickly, or we want to improve the quality. We never refactor just because.
In this video, we're going to do a walkthrough of the project for week 2, what's required and what you're going to need to do. So first off, there's really 4 key steps to this project. The first is you need to be able to design a class hierarchy in order to implement a graph. And if you're curious about how to do this, you can always watch the support video earlier on how to design your own class hierarchy. The second step is you're going to be authoring your own classes to implement this hierarchy and to implement our map graph class. Your third step is you're going to verify it works by uploading to our submissions, and there it'll be tested. And then once you've already run your code and you know it works, you're then going to get feedback on how your code is structured and how it's written, as well as give feedback to other learners. So what I'm going to do now is I'm going to walk through each of these steps, and I'm going to start off with the first step, which is design your own class hierarchy. But first off, you have to kind of understand where this all fits into play. So looking at our class hierarchy, we have within our UCSD graphs folder, we have within source, we have row graph, and then we have map graph. So mapgraph.java is what you're going to be writing, or spending most of your time working on this week. Now you're actually going to add a number of other classes here potentially to support it, but for right now we'll just focus on mapgraph. Now the way that mapgraph fits into the big scheme of things is actually comes clear right here. So if you notice, we have graphloader.loadRoadMap. So what's going to happen is, and it takes an argument, a file of a format that we've provided, as well as a map graph object. Now what this method does is it parses or goes through that simple test.map file, and what it looks for vertices and edges. And if we actually go into the code itself, I can show you what it's doing. We don't have to dive into the main details here, but what you can notice is it's going to go through and add all the nodes to the graph, and then it's going to add all the edges to the graph. And in doing so, at each point, it's taking the graph, which is our map graph object, and it's doing add vertex for each of the vertices. And if you notice down here, it's doing add edge for each of the edges. Now right now, that actually isn't doing anything. So all it's being called is a method that we put a stub in that hasn't been implemented yet. And the reason why is because you're going to need to think about how you want to lay this out. Now, as I mentioned before, there's already a support video about how to lay out potentially your class hierarchy. But I want you to do this on your own. One of the key things being a computer scientist is being able to lay out a class hierarchy and organize it and structure it. So part of the reason there isn't as much content in the videos, both this week and next week, is because you're going to be putting that time into working on the project itself. So you're going to want to lay out the class hierarchy on your own. And to do that, you're going to want to figure out how do you want to represent vertices, how do you want to represent edges. And again, if you want more details about that, check out our support video on laying out your class hierarchy. After you've got that class hierarchy set up, what you're going to do is you're going to come back and you're going to start working through this assignment. What I'll do is I'll talk through this assignment real quickly. So again, what's already been mentioned is the fact that you're going to be structuring your own class hierarchy. So the goal in this assignment is to complete the implementation of the MapGraph class, and you're going to do this by adding additional classes potentially to RowGraph, adding additional methods, most likely private, but perhaps public, and you're going to add potentially member variables to your MapGraph class. Now there are some restrictions to this in order for our tester platform to still work properly. You cannot change the signatures or the semantics of any of the methods that already exist in MapGraph. Please also do not change any of the other code provided in any of the other classes. So here you're just restricted to working within the RowGraph package, modifying the MapGraph class, and potentially adding some new classes and certainly some new methods. The methods that you're going to need to support within MapGraph are these. And I'll walk through these just at a really high level. So add vertex and add edge. These are the methods being called by that code that we just looked at, the graph loader. Those are the methods that are being called to essentially construct your graph. Now what your graph might look like may vary based on your implementation details. But for all practical purposes, this is going to be what constructs your graph, is the act of adding vertices and adding edges. And once those methods have been called for all the intersections within the file, you're going to produce your map. Once you have your map, you're then going to want to be able to return the number of vertices in it and the number of edges within it. You'll also want to be able to return a set of all the edges in case you want to inspect them. So as a hint, a hash set might be a good choice for your vertices. And the last piece that you're doing for this week in terms of code is implementing breadth first search. Now in the next week, you're going to do some more advanced search methods, but for right now we're just doing breadth first search. So what you're going to do is implement this method right here, which takes in a start point and a goal point, and you're going to do a breadth first search for a path from start to goal. Now there's a third object that is passed in, and that's this consumer object. The consumer object is used for us to essentially do our visualizations. If you look in the source code, we have an example of how you can call node searched to essentially notify it that you've explored a certain node. Now notice that we do have a class which doesn't take that consumer object, that just takes the start and the goal. All it does is construct a dummy consumer object, and then it calls your breadth first search method. And the reason for this is that's highly useful for testing. So if you want to do your testing outside the nice user interface that we provided, you can do this essentially by command line or within MapGraph main to call this method and inspect the output of your breadth first search. Now, we also have included both Dijkstra and A-star search within your MapGraph class, but you will not, I repeat, not be implementing those this week. That is the project for next week. So, some hints. This is a big open-ended task. Again, a lot of the times when you're working on programming projects, much of the structure is provided for you, and we're not doing as much of that here. This is open-ended in the sense that you're allowed to set up your classes however you want. Now, although you're able to set those up however you want, we are going to give you some hints. So first off, you're going to want to decide whether or not an adjacency list or an adjacency matrix makes sense. And remember that neighbors are intersections that are connected by streets. And since in general, each intersection is only connected to a handful of other intersections, that should lead you to thinking about which format is more appropriate. You'll probably also want to include some method that allows you to print your graph or some representation of your graph so that you can verify that your graph representation is correct before you try to start doing a breadth first search. And we've given you a couple small artificial files, including test.map, to help you with this debugging process. You should also read through all the code that loads in the graph, for example, that method that I showed you right at the start in Graph Loader, to help understand how this is working. Now, you don't have to understand all the different packages that we provided to you, but this one could be quite useful. And the last thing is you'll want to use this public breadth first search method that I just mentioned to help you debug your breadth first search algorithm. In order to debug your breadth first search algorithm, you're going to want to have some tests built in. And let me talk that through right now. So how are you going to test your implementation? So we provided you with a simple test graph called simpletest.map, and this is the visual representation of that file. Notice that even though this is just showing a single connection, you can assume that this is essentially, each street of these are bidirectional. So node 4,1 connects to 7,3 and vice versa via front street. Now, obviously these points don't actually represent real latitudes or longitudes. That would be a really big distance between these nodes. So what you want to do with this graph is work through, if you want to do a search from a start node of say 1, 1, to arrive at node 8, -1, what path should breadth first search find you? It should find you the one that visits the fewest nodes. So this should essentially find you the path from 1, 1 to 4, 1 to 7, 3, and then down to 8, -1. Now, the way that you're going to test this is you're going to add almost certainly some print statements to your breadth first search method that prints out which nodes you're visiting in what order as you visit them. There are other files within the data maps folder that have real-world state data from cities around California. And you can use these maps to test your solutions, and you can also use them to help visualize the paths in our front-end interface. And just make sure that your search option in the interface is set to breadth first search, because we haven't implemented those other search algorithms just yet. Once you've coded all this, and once you've tested it and you're sure it's all working, and again, this is a significant project, so you're going to want to take your time with this, you're going to come to the submission instructions. To submit, you're going to take all the code from your row graph package, put into a zip file called week2.zip, and then use that file as your submission. And you'll just do the same thing as you've done in the past. You're going to go up to My Submission, and you're going to create a submission, and you're going to add that week2.zip file that contains all your classes from roadmap package. These, again, at the very least, will contain that map graph.java, but it'll also almost certainly contain the other classes that you use to implement your solution. Now, the one piece we've added for this programming assignment is a peer review component. And the reason we're going to do this fourth and the last step for this project of peer review is that you can get feedback about your layout of your hierarchy and your code. Now, this doesn't happen very often, both within online courses and within in-person courses, that someone actually goes through your code and gives you a critique. But here's our reason for doing this. When you're out in industry and you're programming, having your code structure be readable by other people and understandable by other programmers is absolutely essential. Your style and your logical ordering of your code is incredibly important. It's as important as getting your code correct. So you've already gotten the feedback that your code works. You know your code's correct, but did you lay out your structure in a way that other programmers can understand it? That's where this peer review comes in. It'll also be beneficial in the fact that you'll get to review 3 of your other classmates' code, and you may see some good hints or some tips about how to structure your code by reading theirs. So for this, you're going to submit your code, and then you're going to review someone else's. So first, let's talk through your submission. So what you're going to do is you're going to walk through your code and make sure that you have sufficient comments so that someone else can understand what your code's done. You're going to create a rich text document which contains which classes you have, why you made modifications to the map graph class and why. You may want to mention which methods you've added to map graph. You also have other classes that you may have added to your hierarchy, and you'll want to talk about what the purposes of each of those classes and what methods exist in those. Then you're going to justify why you designed your hierarchy this way, why the interfaces were set up the way they were, and you want to keep this down to 4 to 6 sentences or so. You'll submit that justification containing all those details that we just talked about, as well as all your code for peer review. So within this peer review process, you're going to be looking at someone else's code, and they're going to be looking at your code. So giving feedback on a design can actually be fairly difficult. You're going to have to spend some time reading through someone else's code, figuring out how it worked, as well as reading through their design document, and piecing together, was this a clean interface? Was this understandable? Was it not? Now, let's talk through real quickly the pieces that we want you to be reviewing, because I think that actually clarifies a lot of this. So the feedback we want you to be giving are, first off, was the overall class design reasonable? The objects make sense? Do they hold appropriate data? Do they have the right methods for those objects? And are there appropriate number of classes? Did someone try to put all of their code in one class and it became really difficult to understand, or did they divide it up reasonably among a number of classes? Within each class, you should be saying whether or not the class interfaces are clean. Do the methods and the ways that you access the data make sense, and are private data or data structures protected from misuse by the classes? And did they use the correct data structures for the problems that they're trying to solve? Lastly, think about the code style and comments. Is our code readable? Are the methods short and easy to read? Do they have comments at the header to describe what their methods do? Essentially, if you had to take over this project and you need to keep working on this at the same company, could you do so? Or would it be really hard to pick up their code and keep working? Again, please be constructive in your feedback. Everyone's code has both positive traits and negative traits. And the goal here is just to give some feedback about how someone could restructure their code to make their code better when they try to do so in an industry. That's the last piece. So after you've submitted your code for peer review, you've done peer review for other folks, we can move on. So again, this is a large project. We've recognized that this and next week's project are fairly large, and that's why the video content is a little bit less these weeks to help give you more time to work on your projects. I wish you luck, and I hope you enjoy the project. In this week, we're going to add more real-world components to the graphs that you've already learned, and then we're going to start using some new algorithms to solve problems within that space. In this video, we're going to be going over the features you're going to add to your project in week 3. Just like with week 2, much of your work is going to be actually working on the back end, so modifying mapgraph.java, and what I'm going to be demoing you here is what it looks like in our front end, the graphical user interface. So let's pull up that utc.map data, and let's do find a route from here, press the start button, to here. Alright, now if I do show route using Dijkstra, again Dijkstra and A star, which we're going to code this week, if I do it with Dijkstra, let's see the route. It's going to find me that shortest route. And then what we can do using the hooks to our graphical user interface is watch what happens as Dijkstra does the search. So let's start this visualization and see how it progresses. Now, as this is running, you're going to notice that a number of nodes are being visited. For example, this node down here, that's not really on the path to what we're looking for. It actually takes a fair amount of time for Dijkstra to find our destination. There we go. So Dijkstra's found the destination, but look at all the nodes it visited on the way. What we're going to do next is repeat the search using A star. Alright, I've chosen the same start destination and the same goal destination as we did in the previous example with Dijkstra. Let's do this now with A star. Now with A star, if I show the route, it's going to find me the same route, same shortest path. But to see the real differences, we have to look at the visualization. So let's do the visualization of A star now. Wow. It's already done. That took a lot less time than Dijkstra's did. And that's the power of A star search. So what you're going to do this week is add Dijkstra and A star, both of which are going to find you the shortest path on a weighted graph. And then A star search is going to do so more quickly than Dijkstra. I had a lot of fun with this assignment. Good luck. In this video, we're going to be re-examining breadth-first search and looking at its implications essentially for finding the shortest path through a graph. So by the end of this video, you should be able to describe depth-first search's value for unweighted graphs. To do this, we're going to work through an example. What I have here are a number of vertices and edges. We're going to look for a path between vertex 0 and vertex 4. So how are we going to do this? Well, if we apply breadth-first search, as you already learned from the previous week, what you're going to find is I've set up a queue. I'm going to insert v0 into that queue, and I'm going to mark that one as essentially as distance 0 from itself, right? Then what I'm going to do is I'm going to remove v0 from the queue. I'm going to look at all the neighbors of v0 and add them into the queue. So v1 is 1 away from v0, so it's going to have a distance of 1. I'm going to mark it as visited, and then I insert v1 into the queue. Next, I'm going to look at I'm going to remove v1 from the queue, and then I'm going to look at its neighbors. So what I'm going to do is I'm going to look at v2 I'm going to say that it has a distance of 2 because it's 1 greater than the distance of v1. The distance of v1 was 1. So the distance for v2 is 2. I'm going to mark it as visited, and I'm going to add it to the queue. Next, I'm going to look at v4. I'm going to mark its distance as 2, and I'm going to realize, wait, I'm looking for v4, right? This is the thing I was looking for from the very start. So now that I found it, could I just stop now? Are we done? Go ahead and answer this as an in-video quiz, and we'll come back in just a second. So in your in-video quiz, I hope you realize that we're actually done now. We can stop. But I want to explain why we can stop, because understanding why we can stop at this point is going to be essential for developing the next algorithms going forward. So let's think about it this way. So at this point in time, after we push v2 onto the queue and we're looking at v4 and we've recognized v4's distance as 2, what's going to happen next? So let's mark that point in time, essentially at where we recognize v4's distance is 2, and let's just keep exploring. So the next thing we would have done was pushed v4 onto the queue, or inserted v4 into the queue. Then we would have looked at v2, we would have removed v2. We would have looked at the neighbors of v2, marked v3 as a distance of 3, and then inserted v3 into the queue. And at this point, then we'd keep emptying the queue, but you recognize we've already visited all of our nodes, so this would actually be pretty clean. What I really want you to pay attention to is that point in time again, where we found v4, and we recognized its distance was 2. If we label distances for each of these elements in the queue, I think we're going to understand really cleanly why we could have just stopped right there. So if I put these distances here, you're going to recognize that v0 has a distance of 0, and then they essentially ascend in distance. So at that point in time, when you saw v4 and you knew its distance was 2, the only things that are going to be added to the queue after that are going to be as distant or further distant. So we know we've essentially found the shortest path, and that's why we're able to stop right then. Now the big question is, does this work for all graphs? And we're going to find that out in the next video. In the last video, we started looking at breadth-first search. And what we're going to do next is start applying shortest path algorithms to geographic maps. So in this video, you should be able to represent a geographic map as a graph with a few more details than we've talked about in the past. And you should be able to explain why breadth-first search has some limitations when we're working with graphs that have weighted edges. So let's take an example graph. What I have here is essentially some of the cities in the west coast of the United States, focusing in on San Diego and La Jolla, which is where we're at. So this is essentially a graph. We have the cities here represented as vertices. We have rows that connect the cities as our edges. And this is essentially a working graph. But if you look at this carefully, you're going to recognize that there's something essentially missing. And what I want you to do is just pause for a few seconds and think about what might be missing from this graph. So when you're thinking about this, you almost certainly identify the fact that this graph is missing distances. In fact, there's kind of this joke within the United States that if you live on the East Coast and you ever visit the West Coast, you think everything on the West Coast is right next to each other. So we have friends coming from the East Coast visiting us in San Diego, and they always tell us, oh, well, we're there, let's pop over to San Francisco. San Francisco is a long ways from San Diego. You don't just pop over there. And likewise, I've done this when I visited a friend in London. I remember telling him I'd really like to go visit Munich, and he said the same thing. Munich isn't close to London. It's some distance away. So unless you actually have distances on your graph, we're going to have some real problems. And we can see this essentially if we pull up a map from Google Maps. You can tell that La Jolla and Tijuana are essentially right next to San Diego. Further away is Los Angeles. Way up to the northwest is San Francisco. And way out to the northeast is Las Vegas. So what we're going to do is essentially add these distances to our graph. So what I'm going to do here then is from San Diego to La Jolla is about 12 miles. So I put 12 there. La Jolla to Los Angeles is 112 miles, and so on. And right now my distances are strictly miles. But we could do something different if we want to think about this as essentially the weight of the edge. What I could do to improve this would essentially take into account, say, speed limits. So 112 miles at a 25 mile per hour speed limit is very different than 112 miles at a 75 mile per hour speed limit. Likewise, if you're going to go through Los Angeles on, say, a Friday afternoon at 4 p.m., it's going to be really, really slow because of traffic. So what we might want to do is augment this to take into account traffic. Lastly, San Diego to Tijuana is a very close distance, but depending on the time of day, trying to cross the border from San Diego to Tijuana can take a fair amount of time. So what we want to do is essentially augment this graph and essentially improve it with these other cost metrics. But we'll save that for later. For right now, let's just stick with the distances in terms of just raw miles. My question to you is, if we use breadth first search like we have before, what would I find for essentially the shortest path from San Diego to San Francisco? All right, what I'm hoping in taking the in-video quiz is that you recognized breadth first search is going to look for the shortest path essentially just in terms of number of edges, not really distances. And as a result, what it's going to find is a path from San Diego to Las Vegas to San Francisco is two steps away, so essentially the shortest path. But this is a really long distance. This is 901 miles. There's no way, if you're trying to drive from San Diego to San Francisco, that you drive through Las Vegas, unless you want to stop and, say, play poker at a casino. If you're going to go straight from San Diego to San Francisco, you're going to go through La Jolla, then through Los Angeles, up through Bakersfield, and into San Francisco. So how could I have done better? How could I have made it so that I found that shorter path from San Diego through La Jolla, through Los Angeles, up to San Francisco? Well, we'll figure out how to do that with a new algorithm that's coming next. In the last video, we saw how breadth first search has some limitations when you start working with weighted graphs. So what we're going to do now is start looking at Dijkstra's algorithm, how Dijkstra's algorithm is going to solve the shortest path problem for, again, weighted graphs. So in this video, you should be able to apply Dijkstra's algorithm. You should be able to write the code to implement Dijkstra's algorithm. You should be able to explain how a priority queue works and how a priority queue is used within Dijkstra's algorithm. So looking back, when you first saw breadth first search code, you recognize that this was using a queue as the main core data structure as part of the algorithm. We also knew the algorithm looked something like this. What we're going to do now is use a different data structure called a priority queue. Now a priority queue, the analogy here that works quite well, is a hospital waiting room. So there's a queue of people waiting to be seen, and maybe these people all have a cold or a flu. But if the ambulance shows up and someone's having a heart attack, they get higher priority. They're going to be seen by the emergency crew a lot faster than the people with just a cold. And this is the way the priority queue works. So it's just like a queue, except each person in the queue has a priority attached to them. So whenever you enqueue an item, you're going to enqueue the element as well as its priority. And when you dequeue, you're going to get back the person or the item in the queue that has the highest priority to be served right now. Now, priority queues are actually implemented using heaps. And you can prioritize either based on low values with min heaps or high values using max heaps. But we're not going to get into the details of how to design a heap in this module. So now we can start looking at how are we going to change our code from breadth first search to now work for Dijkstra's algorithm. First off, we're going to use a priority queue. So all the places that you saw in breadth first search that used a queue are now going to be replaced with operations using the priority queue. We're also going to have to keep track of essentially the best distance we've seen so far for each node. And I'm going to initialize that at the very start to be infinity for each of the nodes. Again, I'm going to be working with the priority queue, so we're always going to be enqueuing S, which is the start node, along with the priority of it, which is 0, because it's the start node, into the priority queue. And then as long as the priority queue is empty, we're going to keep working. Now there's some changes here in that you can actually have a single node be in the queue multiple times at different priorities. So what you have to do right at the very start is just to check, have I visited this node yet? And if you haven't visited the node, you do all the work. If you've already visited the node, this is just a duplicate. You don't do any work. So we'll do that test first. If it hasn't been visited before, now you mark it as visited. We'll still check to see if this is one that we're looking for, just like we did with breadth first search. We're still going to go through each of current's neighbors that aren't in the visited set, except now we aren't adding to the visited set anymore because we do that only after we pop an element from the queue. So that piece has been removed from breadth first search. Next, we're going to check if the path to current n is shorter than one we've seen before. So remember, we're keeping essentially the best found path to each node's distance associated with each node. Again, right now all of them are marked on this map on this graph as infinity. So if it's better, then we're going to update the distance potentially, update the parent map, and then enqueue, and again, instead of just doing enqueuing the node, we're going to enqueue the node plus the distance to that node from the start node into the priority queue. Okay, so a lot of changes there. I think this will all make a lot more sense once we start working through the example. So what we're going to try to do is we're going to start with essentially node v0. That's our start node. We're going to initialize its distance to the node v0 to be 0, and we're going to insert into the priority queue, again, is that pair of v0 and a distance of 0. Vertex, distance for each time in the priority queue. Next, we're going to remove v0 from the priority queue, and we're going to make that the current node that we're looking at. And when I'm doing this in these slides, I'm going to always mark the current node as essentially the red one. First thing we're going to do is, because v0 hasn't been visited before, we're going to mark it now as visited. And I'm going to mark it as visited by making it blue. Next, I'm going to look at all the neighbors of v0 and find that v0 has an edge to v1, and its distance is going to be 2. And the reason I know its distance is 2 is because the distance to v0 is 0. The edge weight from v0 to v1 is 2. You add those, and you get a distance of 2. In doing so, I'm going to mark the distance of v1 to be 2, and I'm going to insert into the priority queue v1 with a distance of 2. Next, we're going to remove v1, 2 from the priority queue. We're going to make current be v1. Just like before, v1 hasn't been visited before, so I'm going to mark it as visited. And then I'm going to start looking at its neighbors. So first thing I'm going to do is I'm going to recognize that v2 can be reached at a distance of 3, not a distance of infinity. And the reason I got 3 is that the distance to v1 is 2, and the edge from v1 to v2 has a weight of 1. So 2 plus 1 is 3. I'm then going to look over at v4 and recognize I can now reach v4 with a distance of 8. And again, the reason I know I can reach it with a distance of 8 is because I have v1's distance is 2, and the edge from v1 to v4 is 6. You sum those, you get 8. And then I'm going to add both the v2, 3, we already did that, as well as v4, 8. And again, recognize that the larger distances here are going to have a lower priority. So v2, 3 is essentially at the front of the list because its priority is 3. Next, we're going to go to the next node. So we're going to remove v2 from the list. We're going to mark that as our current. And just like before, because v2 hasn't been visited before, I'm going to mark it now as visited. And now I'm going to look at the edges from v2. And I'm going to see that I have a way of going from v2 to v3 that's a distance of 5. So I'm going to update that infinity, change it over to be 5. I'm then going to insert v3, 5 into the priority queue. But because 5 is less than 8, it's going to be pushed to the very front of the queue, even though v4 has been in there longer. So again, we're basing this on priority, not how long the element's been in the queue. At this point, we're essentially done with v2. So we're going to go to the next step, which would be to remove v3 from the queue, make v3 the current node. Because v3 hasn't been visited, we're going to mark it as visited. And then I'm going to look at the neighbors of v3. And I'm going to see that 5 plus 1, the distance from v3 to v4, through the path from v0 to v1 to v2 to v3, is shorter than the previous distance of 8 that v4 was marked with. So what I'm going to do then is change that 8 to be a 6. And I'm going to enqueue that into the priority queue. So now we have v4, 6 being enqueued into the queue. It takes a higher priority because 6 is less than 8. I want to point out, at this point we have 2 entries for v4 in the queue. Well, that's totally okay. If you remember right at the start of this video, I said we add this extra clause, which was to say if you dequeue an element, you check, has it been visited before? If it already has, you don't do anything. So it's okay for us to have multiple entries for v4 essentially in our queue. That's totally okay. Next thing I'm going to do is I'm going to remove v4, 6 from the queue, make v4 our current node. I'm going to mark v4 as visited because it hasn't been visited before, and we're done. We found our shortest path from v0 to v4 to have a distance of 6. And just like when we talked about looking at BFS, we don't need to look at anything else in this queue because everything that's in the queue after this is going to have a higher distance. So it's going to have a larger distance. We don't need to look at those anymore. One thing I haven't covered through this video, and I know there's a lot of details that we just worked through, I didn't work through the details of how to maintain that parent hash map. And I want you to think through that on your own because you're essentially going to be doing this code for the assignment for this week. Good luck.
All right, in this concept challenge, we're going to look at Dijkstra's algorithm, and we're going to do some runtime analysis. So you'll need your big O skills out and ready for this concept challenge. You know the drill. I'm not going to dwell on it. You'll have a couple chances to answer the question. You'll get to see the UCSD learners discussing, and you'll get to hear our explanation. So here's your question. Here's Dijkstra's algorithm as Leo presented it. And the question we have for you is, what is the running time of this algorithm in terms of the number of edges and the number of vertices in the graph?
Hi, my name is Huang.
Hi, I'm Miguel.
Hi, my name is Yumei.
So let's get started.
For this question, I don't think the answer should be A or E because they're both having scores on them and it's too much.
Yeah, I definitely agree. Just because it says for each of Kerr's neighbors n, so that's saying like, oh, it's the edges between Kerr and n. So we're working with the edges and not the vertices.
I think the answer is C. If you look at the while loop, it loops through every single edges, and inside the loop, we're popping from the queue, which takes about O of n, and that n in this case is edge E, right?
That's a good guess, but why don't we consider vertices, which is D, because C doesn't include V?
Why do we need to include vertices?
Because as talking about running time, like, we have to go over the vertices.
Oh, we need to include vertices because we're adding all the vertices to the priority queue first.
Oh, that's right. I forgot about initialization.
Now that you've watched the UCSD learners discuss the problem and thought about it, let's go over the answer here. So the way we solve a big O problem is, of course, we're just going to trace through the code and think about all the steps that need to be done and how long they take. So let's start with the very first step, this initialization step. And if you think about the initialization, a lot of these steps are very fast, but there's one that's going to take a little bit longer. So what we have to do in the beginning is we have to set all of the distances in our graph to infinity. So we have to set that distance on every single node. So it's going to order the number of vertices or nodes in the graph. So that's how long that first step is going to take. Then we go on to the next step in the graph, and we can see that that's a constant time operation. So how do these two steps combine? Let's just take a moment and pause and think about how these first two steps combine before we move forward. So whenever you have two steps that execute in sequence in an algorithm, you do one after the other, then you're just going to add together their running times to figure out the total running time. So at this point, we would have a running time of the number of vertices in the graph plus 1. But of course, you know that O of the number of vertices in the graph plus 1 is just equal to O of the number of vertices in the graph. So we don't really need that plus 1 at all. Consequently, we can kind of disregard this line that only took one operation as well. So we're just going to omit that from our analysis for now, as well as omit explicitly counting any of the other lines that have just constant time running time. So let's continue. Let's go down now, and now we're into the meat of the algorithm, this while loop that's going to keep doing something, keep doing stuff, as long as the priority queue is not empty. So this is a really big question. How many times does this loop run? Well, for a clue, we need to figure out how many nodes go into this priority queue. How many entries, not just nodes, but how many entries? Because as you remember, the entries are going to be nodes plus distances, and the same node with a different distance is going to be a different entry in this priority queue. So let's look at where these entries get enqueued. It's down here. Okay, so what exactly are we doing down here? Well, if you look at where we are in the algorithm, we're in the for loop that's going away from a particular node, finding its neighbors. And the neighbors are basically just the edges of a particular node. So effectively what we're doing is we're adding one entry for every edge in the graph. because for every node, we're exploring out along all of its edges to find the neighbors. So each edge will lead to a new entry in that priority queue. So that priority queue, that while loop then, is going to have running time order the number of edges in the graph. Okay, so that's how many times this loop is going to run. But now we need to take into consideration how long does each iteration of the loop take in the worst case. So now we're going to go inside the loop, and all of these costs are going to be multiplied by the number of times the loop runs. So most of these operations inside the loop have constant time. So I've grayed out all the operations that have constant time. So we can focus on the operations that may or may not need to be considered explicitly. So let's consider this first statement here, dequeuing the node from the front of the queue. Well, if you remember back to what Leo said about priority queues, dequeuing and enqueuing nodes in a priority queue, so if we go down here as well, can be done in log n time, where n is the size of the priority queue. Well, our priority queue could be at worst the number of edges in the graph. So the time it could take to enqueue or dequeue into or from or into that priority queue could be log of the number of edges in the graph. So that's going to be our running time bound for these two steps of dequeuing and enqueuing into the priority queue. So now we're left with this for loop statement. And the question is, what should we do about it? Do we need to somehow account for it, maybe multiply that enqueue operation by the number of times that this for loop iterates? Well, in fact, we don't, because we've already accounted for this for loop's iterations when we talked about accounting for the overall iterations of the while loop, because this for loop is basically just adding stuff to the priority queue. And it's the while loop that's going to keep running while the priority queue is not empty that's going to basically govern the total work that this part of the algorithm is doing. So this for loop here has already been accounted for in our total number of calculations of how many times this while loop is going to run. So we can, for now, disregard it. And then we get to the final answer here, that the while loop, in total, taking into account what it does in its body, takes the number of edges times log of the number of edges. Putting that together with the first step, the initialization step, we get to that the total running time is order number of edges times log of number of edges plus the number of vertices in the graph. Now that's a fine answer, but if you go look online, you might find that the answer is slightly different from what we just derived here. You'll probably see an answer that looks like this statement here at the bottom, that the running time is order of the number of edges times log of the number of vertices plus the number of vertices. So what just happened? How did we go from log of the number of edges to log of the number of vertices? Well, as you may recall, the number of edges is equal to, at most, in the worst case, the number of vertices squared. Well, the number of vertices squared is inside a log term. So a log term will pull out the squared part, and that'll just go away as a constant factor. And we'll be left with the order number of edges times log of the number of vertices, still plus the number of vertices. And that's it.
In the last video, we saw a very powerful algorithm known as Dijkstra's algorithm, and it's quite useful in finding the shortest path between one node and another in a weighted graph. In this video, we're going to explore a more advanced algorithm called the A-star search algorithm. So at the end of this video, you should be able to describe a limitation of Dijkstra's, and then apply A-star algorithm to a weighted graph. And then you should be able to write the code for an A-star search algorithm. So let's go back to our original problem. Let's say we're trying to get from San Diego to Seattle. How would I get driving directions there? Well, I know from having both lived in Seattle and San Diego that you just drive I-5. You're going to take I-5 up through Los Angeles, up through Sacramento, up through Portland, and get straight to Seattle. And if you do a search on Google Maps, you'll find the same thing, that this is about 1,255 miles. Now, Dijkstra's algorithm, if applied to the graph, would actually find this just fine. It would find us the shortest route. But I have some questions about how it's going to find that route. So when we use Dijkstra's, what it's going to do is it's going to start at San Diego. And then it's going to start exploring out. It's going to keep looking until it can find Seattle. So it's going to explore out, 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 and then eventually find Seattle. And that's okay, except in the path to finding a route from San Diego to Seattle, it's going to have explored a route through Denver, Colorado, it's through Dallas, Texas, and even through Mazatlan, Mexico. And if you were planning your own route from San Diego to Seattle, there's essentially no way you would have looked at Denver or Dallas or Mazatlan. And what I want you to do is take a few seconds to think about why you would have never considered Dallas, and I'll see you back in just a second. All right, my hope is that you said something along the lines of, well, Dallas is going the wrong direction, right? I'm headed east, and east isn't going to help me get any closer to Seattle. In fact, by going all the way out to Dallas, I've made my distance from Seattle even further than I started. In fact, the straight line distance, essentially as a crow flies, from San Diego to Seattle is 1,064 miles. And going all the way out east to Dallas actually made me further away. I'm now 1,680 miles away. So what should we have done differently? Well, Dijkstra only considers the distance from the source, from San Diego, on its way to trying to find Seattle. But what we really want to do is also consider how far away we are from the target as well. Now, when working with Dijkstra's algorithm, what we had was a priority queue that had its ordering based on essentially G of n, where G of n is the distance from the start vertex to my end vertex. To change to the state A star search algorithm, all we're going to do is add a second component, which is called H of n, which is going to be the heuristic estimated cost from vertex n to the goal vertex. And all we're thinking here is that G of n is essentially going to be the distance from the start to my current vertex. And then H of n is my guess as to how much it's going to cost to get from vertex n to the goal, or my distance from the target. I'm just going to sum those, and that's going to give me my function that I'm going to use for the priority queue. Now, a couple of pieces to this. The first is that you can really see Dijkstra as a special case of the A star search algorithm, where H of n is just essentially 0. The second thing I want to point out is that you're guaranteed to find the shortest path still in this graph only if the heuristic estimated cost is never an overestimate. So you want to make sure it's always an underestimate. And this works really well for geographic data, because we can essentially just use that straight line distance as an underestimate. You can't get any faster than if you fly essentially straight there, just as a crow would. And that's essentially all we need to do to change the A star algorithm. But what I want to do is real quickly show you what this might look like during a real search. So you start at San Diego, and you essentially just start exploring out from San Diego, but closer to Seattle. You're going to go up I-5, you're going to go through LA, you're going to keep going all the way through Sacramento. And I want to point out at this point, I'm looking at Sacramento, but I haven't looked at Las Vegas yet, even though Sacramento is further from San Diego than Las Vegas is. And the reason for that is we'd have to look at the equation itself. So for Sacramento, f of n is going to be 504, that's the distance from San Diego to Sacramento, plus 625, where 625 is the straight line distance from Sacramento to Seattle. Las Vegas, on the other hand, its function is 331, which is the distance from San Diego to Las Vegas, plus 871, which is that straight line distance from Las Vegas to Seattle. So even though Las Vegas is closer than Sacramento, I'm not going to look at Las Vegas before I look at Sacramento, because Sacramento is essentially a higher priority because it has a lower distance. So A star search algorithm is really just a minor change to the code that you already wrote for Dijkstra. And all you're going to do is just change the priority function.
There was a struggle for me when coding is that I really want to get my programming done by a certain time. And then firstly, my strategy is to plan a whole day holiday to code for that day. But I just ended up lying on bed and watching videos on YouTube. And I don't think it's productive or efficient. So later on, I tried another strategy, which is code whenever I can, break my long coding assignment to many chunk of pieces, and code whenever I feel comfortable with. And it really helps a lot. When I break it down to many pieces, I'm not struggling about how hard it is, because every time I'm so energetic, and because I just switched from other things, other homework or other works, my mind feels like I need to get in down with coding, because it's fresh and I like to do it. And then later on, every time when I code, I don't think it's hard as I thought it would be, because I'm just not tired. I'm concentrated on coding. So it definitely helped me finish the coding assignment by the time.
So one thing that I really struggle with is just remembering the details of algorithms. One algorithm in particular that we're doing in this course is Dijkstra's algorithm. And I've learned this algorithm, I've used this algorithm, I've taught this algorithm many, many times. But every single time, if it's been a while since I've seen the algorithm, I have to go back and look it up. I just forget the details. So I end up doing that, and then I remember, and then I can work with it again. But pretty much every time I approach it, I have to go look it up again.
This video is the project overview for week 3, extending and improving graph search. Specifically, we're going to be doing shortest path on a weighted graph. There's 2 key parts of this assignment. The first is Dijkstra's algorithm, and the second is A-star search. Now again, both of these methods are going to find us the shortest path within a weighted graph. A-star search will just do so a little bit more quickly than Dijkstra search does. You're going to be working with the same code as you did in week 2. You're going to be working with mapgraph.java and the roadmap package. Now you may find that you have to revise more than just mapgraph.java. You may have to modify some of your other classes within your class organization in order to support these methods. And we'll talk about those details in just a little bit. If you weren't entirely happy with your week 2 solution, you can feel free to use our week 2 solution as a starting point for week 3. But I do encourage you to use your own code, as it's likely that you'll be more comfortable with your own code. So again, you're going to be authoring 2 main search methods that we've learned about this week. The first, again, is Dijkstra. The second is A-star search. Both of these methods take a start point and a goal point, and your goal is to find the shortest path from that start to the goal. You're also going to take this third parameter that we recognize from the breadth-first search, which is this consumer object. Now, again, the consumer object exists so that you can report the nodes as you're visiting them in order to visualize them with our application. And we'll talk about the details of how to do that in just a little bit. For testing purposes, you may want to just use the Dijkstra or the A-star search that don't require this consumer object. You can just call these methods and we'll create a dummy consumer object, and then we'll call your appropriate method. You don't need to modify these methods. These are just useful for testing. Your first step is going to be authoring Dijkstra's algorithm. Now this shouldn't be too bad. You'll be able to use your breadth-first method from week 2 as a starting point, and you can use the pseudocode from the videos from this week. The biggest changes that you'll need to make for this week are actually modifying your map graph class along with your support classes to be able to facilitate this search. Specifically, right at the start of Dijkstra's algorithm, we say initialize the distance to each of the vertices or nodes to positive infinity. And that essentially allows us to keep track of a current distance from my start node to each of the nodes. It's likely that within your class structure, you didn't keep some kind of distance like this associated with each of the nodes. Now, whether or not you want to add a current distance to the nodes, or you want to make a wrapper class to store that, or you want some entire other data structure to keep those current distances, is all up to you. You'll just need to keep track, again, of this distance from the start node to the vertex as your algorithm progresses. So the second piece is this is likely your first time working with a priority queue. Now, when you insert items into a priority queue, you need to have some ordering of their priorities. In this case, you're going to be using the distance from their start node to prioritize them, with a shorter distance being a higher priority than a longer distance. In order to do this, whatever element you're inserting into the priority queue, and this element's likely going to store both the node itself as well as the distance to that node, needs to implement the interface comparable. And to implement the interface comparable, you need to author the compare_to method. You're going to look at the Java docs for comparable for more details. If you want to use the visualization tool in the provided GUI, just as we did in our project overview video, you're going to need to report the removal of nodes from the queue to this consumer object. And you're going to do so by using the accept method, and that takes a geographic point. So for example, you may call the accept method on your node searched, and then pass it a geographic point, where you're assuming here that next is the element that you just removed from the priority queue, and the method getLocation gets you that geographic point associated with the node that you just removed. Next step, just like with all other methods in this course, you're going to want to test your code. So after you've coded up Dijkstra, I encourage you to try a number of simple test cases. Let's look at the example that we just looked at from week 2 for breadth first search and figure out what should Dijkstra return back as its shortest path. In this example, breadth first search found us the shortest path by visiting the fewest number of vertices. Breadth first search found us the path from 1, 1 to 8 minus 1 by going through 4, 1, then 7, 3, and then to 8 minus 1. But this actually isn't the shortest path. So what we hope Dijkstra will do is actually find us that shortest path. And the shortest path here should be from 1, 1 to 4, 1 to 5, 1 to 6.50 to 8 minus 1. Now that we have a good idea of what it should do, let's look at how we would do this with our code. In order to test Dijkstra on this example, we provided you simpletest.map as a data file which contains this exact example. So what you could do is run Dijkstra on this, and it should find the same shortest path as we just worked through. Now I encourage you to try some additional test cases to check to make sure that your algorithm is actually working properly. Your next step in the project is going to be authoring A** search. So you can always look back at the videos from this week for the pseudocode for A* search, and you'll likely be able to use your Dijkstra method from this week as a starting point. Now, there are some critical changes to be made going from Dijkstra to A* search, but again, much of the work that you're going to need to do for this part of the project is in changing around your classes to be able to support now the storage of 2 distance values, not just 1. You'll still need to maintain that actual distance from the start, just as you did with Dijkstra. But you'll also now need to keep a predicted distance, which is the actual distance of the node, added to the straight line distance from this node to the goal. And you're going to use the predicted distance in the priority queue to prioritize better paths. As a hint, be sure when you start your algorithm to initialize both your actual and your predicted values to positive infinity, and to set both of those values to be 0 for the start node. Just like we did with Dijkstra, if you want to use the visualization tool, you'll again want to use this accept method on the consumer object. We'll want to test A** search in 2 ways. The first is that we want to make sure that A** search returns the same answer as Dijkstra, so it should be finding the same shortest path. But the biggest distance between A* search and Dijkstra is the number of nodes that get visited on the path to finding your solution. So you could look at the previous example. What you see in our previous example is that Dijkstra's algorithm is actually going to visit all the nodes in this graph in the process of trying to find its path from 1, 1 to 8 minus 1. A* search is going to do this much more efficiently. It's going to find the path from 1, 1 to 8 minus 1 by only exploring nodes, in fact, on the shortest path. In order to test this, you can use the simple test.map file in the data folder, run Dijkstra on it, and look at the nodes that it visited. It should visit essentially these 9 nodes in this order. You can run then A* search on it, and it should visit these 5 nodes in this order. You might be asking, well, how do I know which nodes are being visited? And the best way to do that is to just print out nodes as they get visited to help with debugging. And then you'll want to comment out whatever that print is before you start running it on larger examples. I encourage you to run your code not only on this example but on others to see if A* search is in fact finding a short path by visiting fewer nodes. In fact, one of the best parts of this assignment is running this in the GUI, and you'll see Dijkstra exploring tons of nodes on the path from finding the shortest path from one location to another, whereas A* search does such a more efficient job, looking at only the nodes on a reasonable path from the start to the goal. Once you're happy with your code for both Dijkstra and A* search, you're going to submit your code just as you did with week 2 by zipping all the files in the row graph package into one zip file called mod3.zip. And then you're going to go, just as we did with previous assignments, you're going to go to My Submission, you're going to create a new submission, and you're going to submit your zip file, and you'll get feedback about how well it performs. You can always look at the feedback from the graders to see what went wrong, and you can always look at the graders themselves in our source code to see what tests are being performed. There is one last piece to this assignment. In the quiz that's coming up, we will ask you to provide the number of nodes that are visited using Dijkstra's algorithm, as well as using A* search algorithm on one of our test cases. This was one of my favorite assignments in this course. I hope you have a lot of fun with it. Good luck.
This week we'll be talking about a really concrete question we might want to ask about our graph, and then talk about some algorithmic consequences of it that lead us to a question of complexity and then back to applications.
So far we've been talking about a lot of algorithms for graphs to find distances and to find paths and to represent the graph itself. And in this last module, this last week, we're going to start to talk about some more sophisticated graph algorithms. The first algorithm we're going to start talking about, or first problem we're going to start talking about, is called the traveling salesperson problem. So by the end of this video, you'll be able to describe what the traveling salesperson problem is. First, I'm going to start with an example of what the traveling salesperson problem is. So imagine that there's a salesperson, and this person happened to be somebody who took our course 1 in this specialization, and they made a really cool project for their final project, and they turned it into an app, and now they want to sell this app. And they know that they could put it out there online, but the best way to get people to adopt a new technology and to buy a new app is to actually go visit them in person. So this person wants to travel the world and try to get people to buy their app that they created in this first course. They live in San Diego, so they start in San Diego, and they've targeted a number of cities where they know people and they know that some people are going to be interested in their app. So they've made a list of these 7 additional cities where they want to travel to try to sell their app. And their goal is to do this with the minimum cost, so the minimum amount of time and the minimum distance traveled, to visit each of these cities exactly once and then return back to San Diego. So how are they going to do this? Well, there are a number of different paths they could follow that would complete this visitation of each of these cities. So they might follow a path like this, starting in San Diego, going to Paris, to Lima, to Chennai, to Cairo, and so on and so forth. And you might look at that path and go, well, that doesn't look like a very good path. That's going to take them way out of their way. They're going to have to do a lot of backtracking. So maybe they shouldn't pick that path. Well, let's try another one. Maybe this one looks better, where they kind of just do a circular tour of the cities they want to look at and then come back to San Diego. Maybe that's the shortest path. Or perhaps a better option would be to kind of zigzag up and down the globe and then come around the other side of the world once they get to Australia. Is that the best path? Well, that's the question that we want to answer in this traveling salesperson problem. It is, of course, a graph problem. If I take away the world map, you can see that those cities are just the vertices in a graph. And we're going to imagine in this problem that you can get from any city to any other city. That there, in this world we're considering, there's a flight from every city in our graph to every other city in our graph. So that graph is going to be fully connected. There are edges from each city to every other city. Those edges are undirected, meaning you can go both ways between the cities. Now, importantly, these edges are weighted. These edges have weights, and that weight is the distance between the cities. Now, it would be really messy if I wrote all those distances along those edges in that graph representation I have there. So what we're going to do instead is we're going to represent those distances in a table, where each row in the table is a particular city that you're starting from, and then the column entries in that row are the distances to the cities that you see along the top. So for example, from Lima to Paris is 10,248 kilometers. The formulation of the traveling salesperson problem is, given n cities, you can see we have n cities here, and one hometown, and we have all pairwise distances between those cities, we want to plan a tour starting and ending in our hometown that visits every city exactly once, such that that tour has minimum distance. Okay, so that's our problem. And it's good for planning a tour to sell your app that you created in our course 1, but it's also good for lots of other things. This is a very popular problem and a very important problem to study in computer science. So what else is it good for? Well, I'm sitting here filming this video in early December, and if you celebrate Christmas, you know that Christmas is coming up. And what's one problem on Christmas? Well, the problem is that Santa, who lives at the North Pole, has to go visit every single child in the world and give them presents. And Santa only has one night to do this. So obviously Santa needs to find a very efficient path that visits every city, every home exactly once, and then returns back to his home at the North Pole. So there's a very straightforward application of the traveling salesperson problem, the traveling Santa problem. Okay, if you want an actual application, that's a little whimsical, but if you want an actual application, here's another one. The problem of bringing children to school on a school bus. The school bus starts at school, it has to go collect a number of children, visiting each of their stops once, and then return all those children to the school, do the same thing on the way home. So that's an example of the traveling salesperson problem, a real world example. Other examples are less related to transportation and route planning. There are actually several examples in creating circuit boards. So there have been applications in where to drill holes on circuit boards and how to do wiring on circuit boards. These can be mapped to instances of this traveling salesperson problem and then studied along with studying solutions for the traveling salesperson problem. So speaking of solutions, that's where we're going next. Mia's coming up with a concept challenge on how to come up with potentially one solution to this problem.
Okay, so Christine introduced this problem that we're trying to solve, the traveling salesperson problem. And in this concept challenge, we're going to try to solve it. So we'll ask you a question, we'll invite you to think about it, watch a discussion, confirm your understanding, and listen to the explanation that we give. So let's think back to the problem that we have. And in this traveling salesperson problem, we want to start at our hometown, walk around a graph, and try to do that with the least possible distance. Now, one good strategy for solving a problem would be to say, I want to make sure that the distance I go at any one step is the smallest possible. So this is called the greedy approach because we're making choices that try to improve our situation as much as we can at this particular moment, thinking about just the present and not the future, just right now pick the best next choice. And so in this greedy algorithm, at each vertex that we land, what we do is we look at all the edges that lead us to vertices that we have not yet visited and pick amongst those the edge that has the shortest distance. And traverse that edge, go to the next vertex, and do the same thing. Look at the edges that go to all vertices that we haven't yet visited, look for the minimum distance edge there, and follow it to the next hop. And keep on going until we end up back at home. So let's think about how this greedy algorithm behaves on a warm-up graph. So take a look at this graph, please, and think about if the green vertex labeled number 1 is our hometown, what tour would the greedy algorithm construct for this graph? So how do we know that this is the best possible tour for this graph? Maybe some other tour would give us a smaller distance. In order to compare the greedy tour with other tours, what we want to do is list out all the possible tours. And so for each possible tour, what we're doing is we're starting at 1 and then thinking about what are the next possible hops. And at each point, we can visit any of the vertices that have not yet been visited because this is a complete graph. And so we could go from 1 to 2 to 3 to 4 back to 1. And then we could also instead go from 1 to 2 to 4 to 3 to 1, or, well, maybe our first hop wasn't to 2, but it was to 3. And so over here we have 3 possible tours that are listed. And notice that there's actually 6 possible tours, but the 6 possible rearrangements of the vertices 1 through 4 are paired off by symmetry. And when we're comparing these tours, the way that we want to compare them is to find the distance that's traversed, the distance that's traveled along these tours. And so in order for the distance calculation, we don't need to worry about the direction. So we can just look at, half the tours, save ourselves some calculation. So these 3 tours that we've got listed represent all possible tours through this graph that start and end at hometown 1. And now if we want to compare our greedy tour, which was that top one, with all others, we can compute the distances along each of these paths by adding up the weights of each of the edges. And so the first one gets edge 21, the next one would be 22, the next one is 23, and yay, 21 is the smallest. So our greedy algorithm actually worked for us, which is awesome. It's a very simple to state algorithm, and it found the smallest distance path. Now my question is this always going to be the case? Will the greedy algorithm always find the best, in the sense of smallest distance, tour through the graph?
Hi, my name's Kevin.
My name is Ashley.
I'm Annie.
And Annie, I don't think that the best possible graph would be found if we use the greedy algorithm, because if we change node 2 to 3's edge weight to 10, I don't think, and if we go around the outside again, I don't think that's the best possible tour for the traveling salesman.
I don't think it's the best, it will always work, but for a different reason. I believe that when you have covered all the nodes and you want to go back to your starting point, what if a previous node that you visited has a edge that is lighter to go back to that starting node? So maybe backtracking will be better and provide a lighter, short path.
Well, I'd also like to say that when you're at your last node, you'd have to go back to the beginning, right? So there's a possibility that you can take a lot of different paths, but then when you're at the very last one and you have to get back to the beginning, you're stuck because maybe that edge back to the beginning is really, really long. So that's my biggest concern with whether there is a better path than the greedy algorithm.
Right.
What do you think?
So would a counterexample be from node 4 to 1 if that edge weight was changed to something like 10?
All right, welcome back. As you saw when the UC San Diego learners discussed this question, there was concern that if we fiddled around with some of the edge weights, we can fool the greedy algorithm. And what we'll do right now is we'll construct a counterexample, an example graph, a specific, concrete, small graph where the greedy algorithm just makes the wrong choice. So let's see what the greedy algorithm does with this graph. We start at vertex 1. And we look at all the possible next steps. And we might go to vertex 2, 3, or 4. Now, vertex 2 is the one that we get to from the smallest distance edge because that edge has just label 5. So we go there. And now from vertex 2, we want to go either to 3 or to 4. And we compare its distance 6 to vertex 4, distance 7 to vertex 3. 6 is less than 7, so we go over to 4. Now, from vertex 4, we're forced to go to 3 before we go back to 1 because we want to visit every vertex before we head back home. And so that means that we have to take that really expensive, long, heavy edge over to 3 and spend that time going through the 10 units that it costs us to go through that edge before we get to head back home to vertex 1 from vertex 3. And so the greedy algorithm would go from 1 to 2 to 4 to 3 to 1. And it has cost 27. Now let's compare this tour and this cost to the other possible tours through the graph. And we can look at all of the other possible tours just like we did before. And for each one of them, add up the weights along those paths. And we see that the one that went 1 to 2 to 3 to 4 to 1 has cost 29. Okay, that's a little bit worse than the greedy algorithm. Maybe the greedy algorithm is going to help, except if we were clever and went from vertex 1 directly to vertex 3 in the hopes of having to avoid that heavy weight 10 edge later on, then we could go 1 to 3 to 2 to 4 to 1 and only cost ourselves 26. And so what we see in this graph is that sometimes making the less than optimal choice right now will lead us to better global performance later. Now what that also means is that the simple algorithm we hoped would help us solve TSP doesn't do the job, it doesn't cut it. And so what we need to do is come up with more sophisticated algorithms, and that's what Christine will talk about next.
All right, so Mia showed you a greedy algorithm to try to solve this traveling salesperson problem that didn't quite work. It didn't find the optimal solution for all graphs. So in this video, we're going to look at a different algorithm that hopefully will work a little better. So by the end of this video, you'll be able to describe a brute force algorithm to solve this traveling salesperson problem. So again, here's our graph. Here's our graph of 8 cities. We want to start and end in San Diego. And we want to find the minimum cost tour that visits each city exactly once and then comes back to San Diego. Here's again our graph represented as this adjacency matrix, where each entry in the matrix is the distance between the city in the row and the city in the column. So what is our approach here? Instead of greedily choosing the next best edge, which could get us into these dead ends that Mia talked about, where you'd be forced to take these really high weight, high cost edges, what we're going to do is we're going to allow our algorithm to just try all possible tours, just try all possible paths through the cities that start and end in San Diego. So that's our approach. It's pretty simple. We'll try them all. We'll just pick the one that's the minimum cost. This is what's known as a brute force solution, because we're not doing anything tricky. We're just going to pound it out. We're going to say, all right, I'm going to tackle this problem basically the hard way. I'm just going to try everything and then pick the best. And it's a very straightforward approach, and a good approach, as we'll see, for some description of good. We'll also see it has its limitations. So let's give you an example of how this brute force solution is going to work. It's pretty straightforward. We're just going to pick one path through the cities from San Diego back to San Diego, calculate its cost by adding up all the distances along those edges, and then say, okay, the cost of this initial path from San Diego to Lima to Paris to Cairo to Perth to Beijing to Johannesburg to Chennai and back to San Diego is 72,211 kilometers. So that is currently our best path. But that's just our first path. So let's try another one. Let's switch the last two cities. Calculate the cost of that path. Well, that one's only 67,115 kilometers, so that one's better. So we'll record that one as our best path so far. We'll do another switch around some more cities. This is a new path. We'll calculate that cost, which is 70,016 kilometers. That one's not better than the one we had before. So we'll keep the one we had before as our best so far. And so on and so forth. So we're just going to generate all of the different paths that exist, keep track of the best one at each point, and at the end of the day, once we've considered all the paths, we'll have the best. And so this works. It's going to find us the best path. And in this case, I implemented a solution for this problem, this brute force solution, and I found that the best path is actually to go from San Diego to Lima to Paris to Cairo to Johannesburg to Perth to Chennai to Beijing and then back to San Diego. And that has a total path cost of 55,242 kilometers. All right, so this works. Great. But the problem is, how long is it going to take? You might be thinking, I don't know. There seems to be a lot of possible paths we could take between these cities. Is this really a feasible solution? And if you have that concern, you'd be right. So in the next video, we're going to consider the running time of this solution, as well as the greedy solution that Mia presented. All right, so now it's time to figure out how long does that brute force approach take to solve the traveling salesperson problem, and how long does a greedy approach take? So by the end of this video, you'll be able to analyze the running time for both of these algorithms. Just to remind you of that brute force approach, what we're going to do is we're going to just generate every single path through the cities, calculate their distance, keep track of the best one. So and we said it works, but we were a bit concerned that maybe it was going to take a long time because there might be a lot of these paths to consider. So let's take a look at the algorithm a little more formally in some pseudocode here. So here's the algorithm. We initialize our best path and our best distance variables, and then we have this central loop. And the loop is just going to execute as long as there are more permutations of cities, different paths to consider. Inside the loop, we'll just calculate the distance of the current path. And if that current path distance is less than the best distance we've seen so far, we'll keep track of that as the best path, and we'll keep track of that distance as the best distance. When the loop finishes, we'll have a hold of the best path, and we'll just return it. So in our analysis, of course, we have a loop. We just need to figure out first how much is happening inside the loop, and then how many times is the loop executing. So that if statement there and what's inside the if statement, that's just constant time. But the one piece we have to worry about inside the loop is this one right here. How long does it take to calculate the best distance of a particular path? Well, that's just order n, because we basically just need to figure out along each edge between the cities what is the distance and add them all together. So we've got an order n operation inside the loop. Now it's time to think about how many times does this loop run? And the answer to that question is going to be the answer to how many different permutations are there? So let's think about this question. So we want to figure out how many different permutations or how many different paths through these cities could we possibly have. So I'm going to leave this for a question for you to try to answer. All right, now that you've had a chance to think about this on your own, let's go over how many different permutations we could have here. The first question we want to ask is, how many different cities can we start from? Well, there's just one. We said we were going to start and end in our hometown, which in this case is San Diego. The next question is, how many cities could we go to from there? Well, if we take away San Diego, because we're not going to go to San Diego, we've got 7 cities remaining. So we could go to any of those 7 cities next. Then we ask, from the first city we go to, how many cities could we go to after that? So let's just arbitrarily assume that we go to Cairo next. And then ask the question, from Cairo, how many cities could we reach? Well, there are 6 remaining cities to go to, so we could reach 6 cities next. So we've got the start of some potential paths through our cities. And I want to pause for a moment here to think about how many starting paths do we have so far? Well, for each of these first 7 cities that we could pick, we could then go to 6 different cities from that first city. So we have 7 cities we could start from, and for each of those 7 cities, there are 6 options for where to go next. So in total, we have 7 times 6 possible starts to our paths. So we have 42 starts so far. And then each of those 42 paths is going to expand in many different ways. So as we go from city to city to city, we are going to multiply the number of choices we have at each point by however many paths we had before, because each of those paths can expand out in the same number of directions. So let's continue. We know that after we have 6 cities to consider, the next time we're going to have 5 cities to consider, then 4, then 3, then 2, then 1, and finally 1 remaining city for our hometown back to San Diego. So overall, what we have is 1 times 7 times 6 times 5 times 4 times 3 times 2 times 1 times 1. And this is equal to 5,040 paths, or in mathematical notation, you may have seen the factorial function. This is 7 factorial. 7 factorial is just 7 times 6 times 5 times 4 times 3 times 2 times 1. For any n, the factorial function is n times n minus 1 times n minus 2 times n minus 3, all the way down to times 2 times 1. So here we have 7 factorial different paths to consider. In general, if we have n cities, where one of those cities is our hometown, we're going to have n minus 1 factorial permutations to try. Okay, so this allows us to go back to our algorithm and fill in the missing details. We know that this loop is going to run over all the different permutations, and there are n minus 1 factorial of those permutations. If we multiply that by the order n work we do inside the loop, we get that overall this algorithm is order n factorial. Okay, that looks simple enough. How bad is that really? Well, let's think about the factorial function. How bad is the factorial function? How fast does it grow? At first it doesn't seem so bad, right? 7 factorial was only around 5,000, so maybe it's not so bad. Well, if we look at some values of n as n gets big, we can see that it actually is really, really bad. So 10 factorial is already starting to get pretty big at 3.6 million or so. By the time we get to 19 factorial, we're at 1.22 times 10 to the 17, which is roughly the age of the universe. Up to 23 factorial, we've got a number that's equal to the number of stars in the universe. And by the time we get to 59 factorial, we have a number that's equal to the number of atoms in the known universe. That is a huge number, totally unreasonable. And that's only 59. That's 59 nodes in a graph. You've been working with graphs that have thousands of nodes in them. So clearly, we're not going to be able to use this brute force approach on the graphs you've been working with. So this brute force algorithm only works for very small graphs and won't be practical for anything even remotely bigger than small. Which brings us back to our greedy algorithm. Now, our greedy algorithm isn't optimal in all situations, but is it fast? Let's see. So here's the greedy algorithm. We're going to build our path from city to city, and at each city, we're just going to make the greedy choice and choose the edge that's smallest to a node that hasn't yet been visited. So there's the algorithm right there. We're going to apply the same analysis technique. We're going to look at the loop itself, how many times does the loop run, and then how much work is done inside of that loop. So it's fairly straightforward to calculate how many times the loop runs because there are n minus 1 cities that we need to consider inside that loop if we subtract out the hometown. So that loop is going to run n minus 1 times. But how long does it take to do the work that's inside the loop? How long, the step that we care about here, the most important step is how to select the closest city to visit next. Well, if you think about it, from any city, it's a fully connected graph, so we have n minus 1 nodes that we could visit. And we need to figure out what's the closest one that hasn't yet been visited. And that could take at most n minus 1 steps. So that's about an order n operation. So putting this all together, we have n minus 1 times the loop is going to run, order n steps each time inside the loop, and overall our total algorithm time is going to take order n squared. Whew, n squared, much better than n factorial. So although the greedy algorithm doesn't always find the best solution, sometimes it does. And it's much, much faster than that brute force approach. It's practical for even large problems. And the better news is that sometimes we can even improve on the greedy algorithm, not necessarily make it optimal, as Leo's going to talk to you about it next, but at least make it better, but keep it really fast.
In the last lesson, you saw from Christine that coming up with an optimal solution for the traveling salesperson problem using a brute force method can be fairly difficult. And in this lesson, beginning of this lesson, we're going to start looking at this in more detail. So by the end of this video, you should be able to explain the value of being able to, and limitations of being able to classify a problem as being NP hard. So let's go back to where we were at the end of Christine's lesson. So what we saw is a brute force solution for traveling salesperson is n factorial in terms of runtime. And n factorial is super scary because as a problem size gets bigger, you just can't solve it anymore. I mean, even at an n of 19, this is going to be difficult. And by an n of, say, 23 different cities you're trying to solve the traveling salesperson problem for, this is really not solvable anymore. So what do we do now? We know that the brute force method doesn't work very well. What should we do? Now, we may be thinking we should think really hard and try to come up with some better solution to this problem. And oftentimes, that's actually a pretty reasonable approach. But in this case, I'm going to tell you that's actually probably not a good idea. In fact, it could be quite futile to take that approach. And to understand why that's the case, we have to get into an area of computer science known as complexity theory. Now, complexity theory is a huge area of computer science. It deserves a specialization itself. I'm just going to give you some brief details about it, which apply to our traveling salesperson problem. What happens within complexity theory is we attempt to classify problems by their inherent difficulty. So let's take a couple of problems that we've solved before. So searching a linked list we know is O of n, sorting an array we know is, or we think is O of n log n, and matrix multiply right now is something like O of n to the 2.3. So these are all problems, and can we classify them as being related to each other? Is one more difficult than the other? And essentially all of these problems can be put into the classification of polynomial time solvable. So we can take all these problems, put these all into one classification, and this classification just says that all these are solvable in O of n to the k. And k can be something really big here, but it's still better than something that's, say, k to the n. Now that's a really big, scary thing. But n to the k, a little less scary. And that would be within polynomial time. So the question then is, are there other kinds of classifications that are more difficult than, say, those that are in polynomial time? And there's one fairly well-known classification known as non-deterministic polynomial time, or NP. Now, we could spend a whole bunch of time diving into non-determinism versus determinism. It's a fairly complex topic. It's a lot of fun, but it's beyond really the scope of this course. So I'm going to talk a little bit of a high level about what we mean by saying a problem is an NP. And all we're really trying to say is that some problems seem harder to find solutions than those that are NP. But if you happen to have a solution handy, someone gave it to you through an oracle, you could actually check its correctness pretty easily. That's what it means to be essentially in NP. Now, again, I said we believe this. NP is believed to contain problems harder than P. And you're going to say, well, wait a second, that's pretty wish-washy. Don't we know? Well, no, we actually don't. So this is one of these really classical problems in computer science. Does P equal NP? Are these two classifications the same? It's unknown. It's one of the Millennial Prize problems. In fact, if you could solve this, it got $1 million prize associated with it. But more importantly than the $1 million prize, if you could show that P is not equal to NP, you'd essentially confirm what a lot of computer scientists already suspect. But if you could show that P equals NP, you'd essentially change the field instantly. It'd be incredibly powerful, and it's a great topic. But now that we have this notion then of P versus NP, let's try to expand our classifications just a little bit to talk more, to eventually get back to the traveling salesman problem. So beyond NP complete, we also have a classification known as NP hard. Now within NP hard problems, these problems are at least as difficult to solve as those within NP. Now, what's neat is, if you could come up with a polynomial time solution for any NP hard problem, you could actually solve all problems in NP kind of instantly. It's pretty amazing. So why then are we talking about complexity theory? How does this relate back to our traveling salesperson problem? Well, it relates back because traveling salesperson is within these classifications. So the original traveling salesperson problem that Christine described is a traveling salesperson optimization problem. And by optimization, what I mean is we're going to try to find a solution that has the minimum distance, hence the optimization piece. It has to have the minimum distance. We could also write our traveling salesperson problem just slightly differently to make it a decision problem, which is there a solution that has a distance less than L? So does this solution take less than, say, 2,000 miles to accomplish? Now, these seem very similar, and they are incredibly similar in terms of trying to find a solution. But they're very different in terms of being able to check whether or not a solution is actually correct or not. So if you're trying to check whether or not the solution for the NP-complete decision problem is right or not, all you do is just check the distance of the path that someone gave you. Does it actually visit all the cities? And does it have a distance less than L? If it does, we're done. That's pretty easy to check. But if someone gave you a solution for the optimization problem, well, you could check that it visits all the cities, but does it have the minimum distance? Well, I don't know. I'd have to compare against all other possible paths. And now that gets hard again. So the TSP optimization problem, as we've described it, is actually an NP hard, and the decision problem is an NP complete. So these are essentially considered hard problems. And it may not only be difficult to try to solve this in polynomial time, it may be impossible. So spending your time trying to come up with a polynomial time solution for this may not be the best use of your time. The good news is the story doesn't end here. In the next video, we'll talk about what we can do next. In the last video, we saw that the traveling salesperson problem is provably in the space of NP hard, which means it's likely very difficult to solve. But as computer scientists, we often come into these problems. And one of the things I love most about being a computer scientist is that we don't stop there. We still need solutions to the problems. We just have to come up with some way to find a solution which maybe isn't the best, but is reasonable. And we do this all the time. And this introduces us to the notion of essentially approximations and heuristics. So at the end of this video, you should be able to apply heuristics to come up with a reasonable solution to a hard problem. And you should be able to apply the 2-opt heuristic to the traveling salesperson problem. So again, at the end of the last video, we'd shown that the traveling salesperson problem as an optimization problem was in the space of NP hard. So if we're trying to find that minimum distance, this is going to be really difficult. But all we have to do is relax our constraints just a little bit, and we can actually work much better. And the way we're going to relax is just to say, instead of finding the minimum distance, could we just find something that's reasonable? Now, definitions of reasonable can change, but for right now, let's just see if we can come up with a solution which will work for us. And that leads us to heuristics and approximation algorithms. Now, heuristics and approximation algorithms have a fair amount in common. The idea is essentially you have some intuition about how you might find a decent path. It may not lead you to the best path, but it's going to at least eliminate some of the bad paths out there. And sometimes you might include in this some kind of randomization. So you try a whole bunch of different things, then you kind of pick the best randomly. Now, the big distinction between heuristics and approximation algorithms is just the bounds. So heuristics, you're not really sure how well this is going to do, whereas with approximation algorithms, you often tend to bound the algorithm to say it actually can do at least this well. So what we're going to do is look at a number of these. And in fact, you've already looked at one. So the greedy algorithm that we talked about earlier, where we try to just pick the next best choice as we work through the traveling salesperson problem, was a heuristic. This is a constructive heuristic. So let's talk about these different kinds of heuristics. Well, the first category are constructions. And with constructions, what you're trying to do is essentially build a solution. So you're going to do something to construct the solution as you go along, and once you've got that solution, you're done. So with nearest neighbor, or the greedy algorithm, you're just constructing it by finding the closest neighbor. There are other approaches to essentially try to break down the graph into other pieces and then reconstruct a solution from that. The other approach you can take is come up with a solution and then iterate on it. So with an iterative solution, what you do is take that initial solution and just keep improving on it. So algorithms in this space are like k-opt or genetic algorithms. And again, what they do is they just take a solution and just keep fixing it. Keep making it a little bit better, a little bit better, a little bit better, until some point where they can't really make it better. Now, I do want to remind us that in both of these cases, we aren't going to be guaranteed to find the best, but it's going to help us find a decent one. So what I want to do is give us an example, essentially, of both of these. So what we're going to do is work through the greedy algorithm again, and then apply the 2-opt heuristic on top of that to improve it. So here's a basic graph. And I do want to say that these heuristics and these approximation algorithms are far more interesting with much, much larger data sets. But we're going to work with a really small example so we can see how this works. So with this small example, we'll apply the greedy algorithm to it. And what we'll do is find essentially the path We'll start at A, and we'll find the shortest path out of A, which is 5, which leads to B. Shortest path out of B is 6, which leads to C. Shortest path out of C is 5, which leads to D. And then you only have one node left that you haven't visited. That's A. And you're going to have to follow that path back to A. Now, this is going to come with the length of 28, which isn't the best, but it's also not the worst. And the idea here now with 2-opt is to say, well, I have a solution. Can I make it better? And that's what we're going to do with the 2-opt. So the intuition between the 2-opt heuristic is to examine pairs of edges, remove them from your solution, and try to repair the solution in a different way, and then see if your new solution is better. So I'm going to do 2 examples of this. So first, let's try to select the edges between AB and CD. Let's remove those edges and then try to repair our solution. We'll repair that solution by adding in AC and BD. So what this will look like then is essentially A to C, C to B, B to D, and then D back to A. And if I check the length on that, it's going to turn out to actually be worse, right? I'm taking out 2 edges that are cost 5, and I'm putting in an edge that's cost 6 and an edge that's cost 8. That's a mistake. This is worse. We're not going to do this. So I can essentially scratch out that approach and go back to my original solution and start working from there again. The next thing I'm going to try to do is remove edges AB and CD. And again, I'm going to try to fix it by adding in edges AC and BD. And what I end up with then is a path from A to B, from D to C, and then from C to A. And this is actually a better path, right? Its length is 24 versus the length of 28 for our original. So what we would do then is recognize that this is better, and then select the better solution. So I'll get rid of my old solution, and I'll start working with this better solution, and then I'll just keep doing this until I can't find any more improvements. So this happened to find us the optimal solution. So greedy plus 2-opt, for this very simple example, worked. Found us optimal. But that isn't going to be true in the general case. So if you have larger data sets, larger graphs, it's very possible that greedy plus 2-opt will actually find you a non-optimal solution. But we like this because although it doesn't find us the optimal, it's actually pretty fast, and it'll come up with fairly effective solutions. So what I encourage you to do then is to step back and look at some of these other solutions. So look at the different constructions out there, look at some of the iterative solutions out there, look at some of these on your own just to see how they work. And I encourage you to think about what the limitations are and what the benefits are of trying these different approaches. But at a high level, what I want us to realize is essentially changing the problem itself can be incredibly powerful. So when we stated our problem as having to find the exact minimum distance, that was really difficult. But if we just relax this constraint to say, well, I want to come up with an answer that's good, but doesn't have to be the best, that allows us to just come up with an answer that's reasonable. And that's often good enough for what we're trying to do.
Okay, so we've talked about one graph problem, the traveling salesperson problem, and now let's think about other questions we could ask with graphs. So by the end of this video, you'll be able to talk about what it means for a graph to be Hamiltonian and to determine whether for small examples that particular graph is or isn't Hamiltonian, and then we'll think about algorithms for answering this question for bigger and more systematic graphs, and we'll talk about the efficiency of that algorithm. So let's jump in. So we were talking about the traveling salesperson problem where our graph really represents cities, and we've got n cities, one of which is our designated hometown, and we know all of the pairwise distances between the cities. And what we'd like to do is find a tour that starts at our hometown, goes around all of these cities, and comes back home. Now, we know that this is possible. We've talked a little bit about some algorithms for solving traveling salesperson, but what if we change it a little bit? So for example, what if now we don't care about distances so much, but we just want to go from one vertex all through all the vertices in the graph and make sure we arrive at each vertex exactly once. Well, is this doable? Now, if as before we have edges between every pair of vertices, then of course it's doable. We can at each point just hop to the next vertex that hasn't been visited, and because our graph would be complete, we can always go along it and find a path that visits each vertex exactly once. The question becomes, though, what if some edges are missing? And in many of the graphs that we're thinking about, we don't have a complete graph. We don't have edges between every two vertices. And so we could ask the question, is there a path through the graph that visits every vertex exactly once when our graph is a general graph? May or may not be complete. Now we're just going to focus on undirected graphs, so we're not worried about the directions of the edges. And so let's think about some examples on how this works. And with each one of these, I'd like you to try thinking about whether the graph is Hamiltonian or is not Hamiltonian, and then we'll think about it together as well. So a graph is Hamiltonian if there is such a path through the graph which visits every vertex exactly once. And so let's look at this particular graph. Is it Hamiltonian? All right, well, come back. Let's confirm that it is indeed Hamiltonian. And what we could do is we could just start at the top and then come towards the front and go along the front vertices, then go back and go down and go to this back bottom corner. And we've got a path that starts at some vertex and visits every vertex in the graph exactly once. So this graph is Hamiltonian. Now, how about this one? Is it Hamiltonian? All right, well, come back. This graph is not Hamiltonian. And in order to justify that a graph is not Hamiltonian, we have to do something a little bit more nuanced than our justification that a graph is Hamiltonian. Because think about what the definitions are saying. In order to prove that a graph is Hamiltonian, we just need to produce this tour or this path that goes along the graph and visits every vertex exactly once. All right, but to prove that a graph is not Hamiltonian, we have to say that no such path exists, that no matter how we try to visit each vertex exactly once, we're going to fail somehow. And so we can make that argument with this graph. If we start in the middle vertex, then we're going to have to visit one of the periphery vertices after that. And so maybe we jump up top, but then we're stuck because we can't jump back to the middle because we already visited the middle, and Hamiltonian paths aren't allowed to visit vertices more than once. All right, so a Hamiltonian tour can't start in the middle. Now, could it start in the periphery? Well, the problem with starting in a periphery is that the first step of the path will have to be to go to the middle because the periphery vertices just have degree 1. They're only adjacent to the middle vertex. And then once we get to the middle, then we're in the same situation as before because our Hamiltonian path would have to visit both of the periphery vertices, but we can't get from one to the other than by going back to the middle, which we can't do in a Hamiltonian path because we've already visited the middle vertex. Okay. This graph is not Hamiltonian. And so now we've seen an example of a Hamiltonian graph and one that is not. And then the question is, how do we decide this in general? If we have a huge graph, like maybe think back to the graphs that you've been working with in the project, how do you decide if those graphs are Hamiltonian, if we want to visit each of their vertices exactly once? And it seems a bit daunting if we have a graph that even has just hundreds of vertices, thousands of vertices, millions of vertices, to try all possible paths or to do this reasoning about these graphs. And so really, our first, naive best guess at how we might test is to just generate all possible sequences of vertices. And for each possible sequence of vertices, what we could do is say, does it constitute a path through the graph? What we are asking there is there really an edge in the graph between every pair of vertices in this sequence? And then once we've checked that, we can say, is this sequence of vertices denoting a Hamiltonian path? Does every vertex appear exactly once? And we could do that. We could code up a brute force implementation, just like you've seen before in Christine's brute force implementation of Traveling Salesperson. But brute force implementations are not efficient. They're going to take a really long time. So is there a better way than just trying all possible paths? Now, the piece where we verified whether a particular sequence of vertices is a Hamiltonian path, that part was efficient. The problem was we just had to generate too many such sequences. There's so many possible sequences of vertices that we're just going to get in trouble if our graph has any sort of realistic size. And this is exactly what Leo was talking about when he was talking about NP completeness. So the Hamiltonian path problem is a classic example of an NP complete problem. It's a problem where we don't know of an efficient solution, which given a graph tells us whether there is a Hamiltonian path through that graph or not. But if someone was to produce a candidate Hamiltonian path for us, we would be able to check whether that candidate Hamiltonian path is indeed a Hamiltonian path. So we're stuck with this graph question, which is a very natural graph question, but for which we don't have an efficient solution. So we could say, what's next? What do we do? Are any graph problems really this hard? We saw the Traveling Salesperson was hard. We're seeing now that Hamiltonian paths are hard. is it just going to be a problem that every time we ask a question about graphs that we have to maybe do heuristics or deal with a really slow algorithm? And so in the next video, we're going to tweak this graph problem just a little bit and see if maybe we can get a slightly easier graph problem to work with. So we're ready to talk about a slightly different graph problems in the hopes of maybe finding one that is tractable. And so in this video, we're going to be defining an Eulerian circuit for a graph. We'll be determining whether graphs are or aren't Eulerian, and we'll be talking about the algorithmic questions surrounding Eulerian graphs. Now, it's worth saying that this lesson is very abstract, and this whole week's material really does feel a lot more theoretical than what we've been doing in the courses up until now. We're a little bit more removed from the projects, we're a little bit more removed from applications, and there's two reasons for that. One is that at least I think theory is really, really cool. It's what I study, it's what I do research in, and it's what I love, and so it's really wonderful to be able to share that with you. But the other reason is also that the theory and the concepts that we're talking about really do end up having some very concrete applications to real problems, and we'll actually be able to have a guest visitor tell us a little bit about that at the end of this module, so stay tuned. All right, but back to Eulerian graphs and back to these somewhat abstract notions. We talked in the previous video about Hamiltonian graphs, and a Hamiltonian graph was a graph where we could walk along all the vertices, visiting each vertex exactly once. And so let's tweak that a little bit, and we say, okay, well, with graphs, we've got vertices, we've got edges. What if we change the definition to ask about an Eulerian graph where we can walk along the whole graph, visiting each edge exactly once? And so in this setting, we're allowed to visit vertices more than once, but what we want to make sure is that each edge gets traversed exactly once. And so let's think about some concrete graphs and think about whether they're Eulerian. And so what about this one? Can we traverse this graph visiting each edge exactly once? Okay, so let's see an Eulerian path through this graph. It is in fact Eulerian. We start at the top, we can go around the side and then come to that middle vertex. Now we want to make sure we get that edge between the middle vertex and the top vertex, and so we follow that edge up and then we go back around the other side. And so this graph is Eulerian, but notice that it's also Hamiltonian. And the Hamiltonian path that we could take through this graph has to be different from the tour that we just did. And so a Hamiltonian path through this graph could just go around the periphery and visit each vertex exactly once, but notice that that Hamiltonian path will not traverse that middle edge, and so it won't be a witness of being Eulerian. All right, what about another graph? Let's take a look over here. Is it Eulerian, and is it Hamiltonian? All right, so in this graph, we see that there's an Eulerian tour through the graph. We can start in the middle and follow all the edges in the top triangle, then follow all the edges in one of the side triangles, and then follow all the edges in the third side triangle. And so we get an Eulerian graph, but it's not Hamiltonian, because think about what that description that I gave for the Eulerian tour just did. It had to keep coming back to the middle, and any attempted walk through this graph that tries to visit all the vertices or all the edges will still have to come back to that middle vertex, and that's going to be a problem with being Hamiltonian, because we're not allowed to visit any vertex more than once. Okay, so we've got a graph here that is Eulerian but not Hamiltonian. One more. Is this Eulerian? All right, so you saw that this graph is not Eulerian, and we can do an analysis that if we try to traverse any one edge, then what we do is either we get from a periphery to the middle or from the middle to the periphery. If we went from the middle to the periphery, then we'd be stuck. We'd be at a periphery vertex with no way of getting back other than going along an edge that we've already traversed. Bad news. If we went from a periphery vertex to the middle vertex at the beginning, then we can have one more hop from the middle to a periphery, but then there's one edge and one vertex that we won't have traversed, and so there's not going to be any Eulerian tour through this graph, and similarly no Hamiltonian path through this graph, as we saw in the previous video. All right, one last example. It's really useful to see all the different combinations that we can get. And so in this graph, we saw before that it is a Hamiltonian graph. And is it Eulerian? Okay, so you saw in the quiz that this is not an Eulerian graph. So we have an example of something that's an Eulerian graph, but is Hamiltonian. The point of these four examples is to show that all possible combinations of being Eulerian or not and being Hamiltonian or not are possible. And so even though all we did was tweak just that one word in the definition, we get very, very different notions when we're talking about Eulerian graphs and we're talking about Hamiltonian graphs. And so now we can ask the same question we asked before. Is there an algorithm that determines, given a graph, whether it's Eulerian or not? And that brute force approach that we talked about before would still work, right? We could still generate all sequences of vertices, check whether they're paths, and check whether they're Eulerian. And that's fine, but we talked about how it wasn't efficient. And in fact, for Eulerian graphs, there's an easier way. And so if we think back to our 2 examples of Eulerian graphs from those just toy basic examples, we can think about how we may have come up with the Eulerian paths that visit every edge exactly once in these graphs. And notice that when we were thinking about these Eulerian paths, it was important which vertex we started with. So for example, in the one graph, we can't start at one of the side vertices. We have to start in one of the 2 middle vertices, because if we try to start on one of the sides, then we're going to get stuck and not be able to come to visit every edge. And the algorithm is based on the observation that when we have an Eulerian path, we have to have each edge traverse exactly once. And so we can think about these edges as taking us to and from vertices. And so what we're doing is we're partitioning all of the edges in the graph based on the sequence of edges that we traverse in the path. And some of these edges bring us into vertices, and some of these edges take us out of vertices. And so if we're focused on any one vertex, in order to have an Eulerian path, we have to have the same number of edges going into that vertex as are going out of that vertex. And so what that means is that most of the vertices in the graph need to be of even degree in order for there to be an Eulerian path through this graph. And we might be able to accommodate 2 exceptions. Our starting vertex is allowed to have just more outgoing edges than incoming edges, and our ending vertex is allowed to have more incoming edges than outgoing edges. And so the criterion for being Eulerian is that there's at most 2 vertices of odd degree in the graph. And it turns out that if we have at most 2 vertices of odd degree, then we can come up with algorithmically an Eulerian path through this graph, just starting at one of those odd degree vertices and figuring out how to go from there. And ditto, if we know that our graph is Eulerian, we can guarantee that it has at most 2 vertices of odd degree. And so it's a really cool theoretical theorem that you can prove about this equivalence between this notion of Eulerian and the degree structure of the graph. And, well, who cares? One reason is that it gives us a much faster algorithm for determining whether a graph is Eulerian, but again, who cares? And the reason we care is that A, we see that small changes in the definition lead to really big algorithmic differences, and B, what that does is it gives us a direction to go. If we're trying to use graphs to solve real-world problems, then what we want to do is to model our real-world problems in ways that lead themselves to solutions via looking for Eulerian paths or looking for other graph properties that are efficient to determine or that have efficient algorithms for them. And so what we notice is that when we're looking at the theory of the graphs, that's great, but we want to keep in mind when those theoretical choices lead to efficient implementations. And those efficient implementations can help us in practice, as you'll see next. All right, so now that we know what Hamiltonian graphs and Eulerian graphs are, we get to see how they are used in practice to really solve a very important problem. Now, to set the stage, we're really happy to have colleagues from UC San Diego talking about their research work in genome assembly. And so I'll let Pavel take it from here.
As we speak, there are thousands of genome sequencing projects that is being conducted all over the world. Personal medicine and personalized genomics have important implications in medicine, and in 2010, Nicholas Walker has become the poster child of personalized genomics. His life was saved by genome sequencing. We expect that very soon, the cost of sequencing the human genome will fall under $1,000 mark. To accomplish this genomic revolution, we need to develop algorithmic techniques for sequencing genomes.
So this is the overall picture of the genome sequencing and assembly. You have multiple copies of the genome, the sequencing machine generates reads, and the task of the genome assembly is to, from these reads, to reconstruct the original genome. Now, we are ready to put the genome assembly problem into the language of computer scientists.
Now, as Sean said, we need to translate the problem of genome assembly into the language of computer science. And here's where a lot of magic and creativity needs to happen. Because when we do this translation, we have lots of options. And in particular, if we're thinking about translating some big problem into graphs, we need to choose what are the vertices and what are the edges. Now, the classical way of translating genome assembly to the language of graph theory is to take those reads, those little pieces of the genome that we read off, and put them as vertex labels. And then what we want to do is look for ways that those vertex labels overlap. And so we have an edge between two vertices if we have vertices whose labels overlap. And then what we want to do in order to reconstruct the genome is to find a path through this graph that visits every vertex exactly once. Now, we're looking for a path that visits every vertex in a graph exactly once, and that's exactly the Hamiltonian problem. Thing is, though, that when we talked about Hamiltonian problems just 2 videos ago, we saw that they're intractable. We don't have efficient algorithms for solving the Hamiltonian problem on an arbitrary graph. Now, the beautiful, brilliant insight of Pavel and his team was that we could model the situation in a completely different way. We could instead have a different collection of vertices and edges that I'm not going to get into in too much detail because it gets a little bit technical, but you can learn more about later, and I'll tell you how in a minute. But with this new graph formulation, what ends up being the problem that we're trying to solve is looking for a path through this graph where we visit every edge exactly once. That's an Eulerian path. And Eulerian paths, well, they're amenable to solutions with efficient algorithms. And so by reformulating what it is that we're trying to solve and how we represent the problem at hand, all of a sudden these algorithmic tools that we've developed really help us out and help us solve really hard problems. And so to wrap up this conversation about translating the genome sequencing problem to graph theory, I'm going to hand it back to Pavel.
Let me ask you a question. If you were given the possibility to choose between the Hamiltonian path problem and Eulerian path problem, as presented at this slide, what choice would you make? Sean?
Well, I would like to solve the Eulerian path problem because the graph on the right looks simpler and maybe it's easier to find a path that traverses all the edges in the graph.
Sean just gave a very wrong answer. It doesn't matter that one graph looks simpler than another. In real life, this graph will contain millions, if not billions, of edges. And it doesn't matter that one of them contains 2 million and another contains 1 million of edges. What matters is whether we have efficient algorithms for solving these problems.
So I hope you're really excited, or as excited as I am, about these amazing applications of graph theory to bioinformatics. And if you want to learn more, Pavel and his team have put together an amazing specialization here on Coursera, and we invite you to look into it further.
Congratulations on having completed the course. The project in this course, like the previous courses, was large and complex, so I applaud you at having succeeded at it. And it's also some fun. You've created your own version of Google Maps, and that's pretty cool.
Yeah, and along the way, you learn a lot about graphs, that fundamental data structure in computer science. There's so much more to learn about graphs, so we hope you'll continue to study them as you move forward with your learning. And in fact, you'll have an opportunity to go deeper with graphs in the capstone project coming up at the end of this specialization.
Before we get to that capstone project, though, there's still one more course that we're offering. And in that course, we'll go deeper in graphs, but also all the concepts that we've been thinking about and talking about in this Java programming and data structures specialization. Now, what we'll be doing is going deeper into the technical details, but also thinking about how to communicate and talk about these data structures and algorithms with colleagues, and also en route to success in your technical interview. So we hope you'll join us for that.